Recording. Okay, hello my friends, how are we doing? This is my first YouTube video, so I might be a bit nervous as I'm recording because I haven't actually uploaded anything to YouTube. But today's video is about the No-C compiler, which is a language I made for myself, but it's going to go into has a lot of features that I really like about programming languages. The stuff that we're looking at today is a complete breakdown on how the compiler works, from type checking to garbage collection to virtual threading, how closures work, how generics work. Before that, I'm going to give you a quick demo of the language, and then we're going to break it down into how everything works. So today we're using Miro, which is a board that we can draw on. I think most of this video I'm going to one-shot it, so I'm not going to edit it. I'm just going to explain as best as I can as I walk through the code. We'll be spending most of our time on the whiteboard explaining things, and then I'm going to switch between that and the source code of the language, which is right here on VS Code. Of course, in the description you can find the public repo for the source code. And yeah, a couple things beforehand. Apologies for the quality in the video, and also because the camera's pointed to my chin, but this is my best angle, so you know, it's not too bad. And yeah, because it might be a bit grainy, this is something to do with Dell's monitor and OBS. It just doesn't, it loses sharpness when I actually publish the video, but I hope it's still okay. This image is created by Nano Banana, so Google's Gemini, and obviously that's me. I'm wearing the same outfit with the same cap. I just made the image, and yeah, we're fighting the compiler dragon. If you've read some compiler literature, you'd know there's a very famous book, very old book actually, which is one of the first like compiler publications from the 70s or 80s, and it has a dragon on it. So yeah, I told Nana Banana make it look like the dragon book. It literally drew a dragon on a book, but this is quite fantastical. Before we start, actually I'm just going to start right now. What is the language? Let's just go. I made this board yesterday. Apologies for the handwriting, because I realized that that is really bad. So, but what is the No-C language, and what does it actually support? Before that, I'm actually gonna open up the documentation for this language. So with this we've there's a whole documentation PDF that covers everything as well. I decided to make the video because the documentation is lacking depth, and you can read the book as to why that is, but let's see exactly what the language actually supports. So No-C is a struct-based language. It's I guess any language can be an object-oriented language. There's no classes or inheritance. There's full generic support for struct definitions and functions, full functional program support with closures and high-level functions. You can pass functions to other functions, return functions. You can make closures. There is a different kind of error handling, which is similar to Zig, the way Zig does error handling. And there's virtual threads as the basis for threading with non-blocking I/O. And not included here is actually the garbage collector. And also this is a garbage collecting language. And we're going to go through all these steps in detail. I'm going to explain to you on the board how they work, and also look through the source code to see how it works. But the first really question that I want to answer is why create the language. I wrote this in the documentation book that you can read, but it's actually a threefold reason why I wanted to make my own language. The first one, because I like programming, and I always wanted a language that I would enjoy writing programs in. And I wanted the features that I just enjoy writing programs in. I think the closest language that I like, or was almost complete, is Go, because of the simplicity of the language. And there's so many programming languages, but the syntax is always so complex, and there's always stuff that you just can't recognize. So I want a programming language where you can read a program and you immediately know what that program does. Go is the closest language to that, but Go made error handling a different way than I do it, which I'm more of a fan of exceptions, and Go's obviously doesn't support exceptions. It kind of does with Panic, but the way it does error handling is you return an error code and you handle that error, and the way it does it is really nice with multiple return types. But I'll show you in the demos why I prefer the way I do it, which is I believe the way Zig does it as well. So that's one of the main reasons why, because I just wanted my own language. The second reason is I wanted to understand more about the runtime of the language, more about virtual threading, more about garbage collection. And in order to do that, you do have to build the language. In today's software climate, obviously the AI systems like Claude are amazing. They're insane, and they can do so much that that you wouldn't. Honestly, it's quite jaw-dropping what they can produce. Recently, there's been quite sensational post. I think it's by Claude or it's by Windsurf, where they managed to make a browser with it. Now, there's much debate as to how good the browser is and the fact that, you know, but at the end of the day, and apparently it costs $5 million worth of tokens to make it. But at the end of the day, these systems will get better. What they could not do last year, they can do now, and they are getting better, and they can make really sophisticated software solutions. That honestly, if you were to write it by hand by yourself, it would take months of study. You can just vibe code it yourself. However, the reason for making the language is to expose myself to the materials, expose myself to the runtime, expose myself to garbage collection, and expose myself to how the scheduler works in a programming language. Those materials force you to dive deeper into those areas of studies that you would not be able to get had you vibe coded the solution yourself. Vibe coding is amazing because you can get something working, which is much quicker than you could if you just typed it by hand, but you don't get the depth and you don't get the ideas that can come out of that. You know, when you're working on something and you write every line of source code yourself, you understand the entire system, you're able to iterate the system easily, and you know, you have depth of understanding. And today I really want to share that understanding with you guys today. If you guys want to know how programming languages work, how generics work, you know, how a virtual instruction set works, and how runtimes work, then this is the video for you guys. I'm going to go into depth with that. This video might be quite long, and I'm already rambling about a bunch of stuff. So yeah, those are the main reasons why I wanted to create a language. And yeah, so what we're going to be covering today is we're going to be looking at the stages. Let me get my pen out. We're going to be looking at the stages of compilation. The stages of compilation are basically four things that we need to be doing. We need to be doing tokenization and parsing. I'll explain what each of those ones mean. Then we're going to be doing type checking, because NoC is a statically typed language. We're going to focus on code generation. The code that's generated is a virtual-based instruction set. The runtime is interpreted. So it interprets that virtual-based instruction. This language does not have direct code generation, so we don't directly emit assembly code. Although this is quite easy to do and quite easy to extend, I decided not to do it because I ran out of time to work on this language, and I wanted to publish it even though it was incomplete. So we're going to be looking at code generation, which is really simple. And then we're going to be looking at the runtime, which is the smallest part of the actual language is the runtime in terms of the amount of lines of code, because it's not sophisticated and it's quite simple. We're going to be looking at virtual threads and you know how we create threads and what's the threading model of NoC, if that's a phrase that I can use. We're going to be looking at activation frames, you know, how are NoC objects created, you know, how are primitives represented, how are structs represented, how are strings presented, arrays. We're going to be looking at how closures are represented in the runtime, and you know how it supports high order functions and anonymous functions. By high order, I mean you can pass functions into other functions and you can return functions. I guess this is like higher order, or whatever you want to call it. But closures is really the mechanism of having what No supports is the asynchronous no routines. If you're familiar with Go, or maybe other languages certainly have this, but Go has Go routines, which is you can spawn a asynchronous task just by writing Go and a function. You know, obviously no, I mean in NoC it's the same thing, but it's just no instead. So instead of saying Go, you write no. How no routines are supported, and closures are the real mechanism between how they're supported. The idea actually comes from a paper called coroutines, and I'll link it in the references of the book. And with no routines, when you spawn an asynchronous task, obviously you want to await on that. And we're going to look at how features are supported. When you spawn a no routine, you get a feature back, you can await on that feature. And then we're going to be looking at non-blocking IO and how that's supported within the runtime, We're going to be looking at locks and mutexes, and that's really going to be covering the runtime. And that's everything there is in the runtime. And then finally, we're going to be looking at garbage collection, which is the last thing that we're going to be looking at. Because when you make a language, the garbage collector you can punt it to the end. And you can just, when you're making the language, you can just use the standard allocator that your language supports, and then eventually you move to the allocator that you have for the language, which is an allocator that would support garbage collection. So we're going to be looking at how we allocate. We're going to be talking a bit about virtual memory, not too much, but you do need to understand just a bit about virtual memory to get your allocator to work. The standard algorithm for allocation is mark sweep. You might already know this. You might be quite familiar with mark sweep. And we're going to be looking at private heaps and concurrency models. If you know Go, then you might also be quite familiar with different concurrency models that are available. Obviously, there's shared memory and there's message passing, which is what Go really does. Is just message passing. You have a channel, you communicate data between threads or Go routines through channels. Other languages have similar things. I think Erlang has message boxes or something, and in other languages that don't support it, there's also frameworks around it. So in Java, I think it's called Arca, where it's like they call it actor models, but it's the same kind of concurrency model. Instead of actually having all Go routines or no routines or threads see the same shared memory, you communicate with them by passing messages. But if that doesn't make sense, that's totally okay right now. We're going to be looking at it at the end, because it makes sense once we look at it in the context of private heaps. But don't worry if none of this stuff makes sense. We're going to be looking at all of this stuff in detail. And I hope that preamble was a good introduction. Let me see now what I need to be doing first, because I did write it beforehand. So first we're going to be looking at the complete tour of the language, and I'm going to show all the features of the language, and maybe I'll expand upon some features. And then we're going to be diving into the source code, explanations, looking at the source code, looking at the explanations. So we're going to be coming back and forward between this board and the source code. So first, let's actually look at what NoC is, what it supports, and we're going to be jumping right into VS Code for this. Let me put my pen down, and let me just look at OBS quickly. So I'll be fuming if OBS is not recording. OBS is recording, so that's great. How long is this video? It's already 12 minutes. My apologies. It's going to be a very long video. Okay, so let's look at the complete tour of the language. Cool. Again, in the source code, you'll find the documentation, but the documentation, again, is quite surface level. There's a detailed breakdown of everything I'm talking about, so you can complement it with the video. But let's look at NoC. Okay, so the first stuff that the language is pronounced NoC, is that the name actually wasn't created by me. It was created by one of my colleagues, but I decided to use it for the name of the language. So I'm going to show you some of the features of the language, and we're going to be looking at the integration test, which is tests that are written in the language to test itself. So let's open it up quite quickly. And I'm not going to bore you with how different things work in the language, like how you create like an if loop or a for loop, or if statement or a for loop, or things like this. We're actually going to be looking at the integration test file, and just going to show you all the features of the language. So the main real features that are of the language, of course, is structs are the only thing that are supported. There's no inheritance. There's no nothing above that. Structs are supported, and the base types are obviously string, integer, boolean, some of the stuff that you come to expect. There's no unsigned stuff in the language. Those are the primitive types, but structs are the only way. There are no member functions, so it's like a C-style kind of, when you call a function, you have to pass in the object. It's not like test case dot. There's nothing like that in the language. So here's how you represent a struct. Here you can see it has a name. Obviously, because we have the language supports high order functions, it also takes in a run test function, which is a function that takes in nothing and returns a void. So it's a test case function, and then you can actually add it to the struct and then call it when it happens. I spoke about generics, so let's just look at how generics actually have. So this is the array list representation in the language. Here you can see there's an array list, generic of type T, so it takes in some T. This is a T, and it has a number of elements. So this is how, if you look at the Java source code, it's almost the same as it. So there are no constructor functions, so I kind of wish I added it because it causes so many problems because you forget to initialize some object. But here, when you create an array list, you initialize it by calling the initialization function. And that's how generics are supported for structs. And obviously you have also generic functions, because this takes in an array list that has some type T. And you can see all these functions are generic because they take in some type T, some T of value, and this array list at returns some generic of some type T. And we're going to be looking at that. A really good one actually that I can show you is array utils, just to show the power of generics and also lambdas. Let me go back to integration tests, and let me just copy this one just for now. Okay, otherwise it won't compile. So here's a function that is a map function which takes in an array of type T, and then it takes in a mapping function that takes in some object T, and then returns an entirely new object Z. If you're used to functional programming, then you're very familiar with this kind of mapping function. And I'll show you an example of this. There's two ways that you can create. I'm just going to call them lambda functions, like an argument that takes in a function. You can actually create a type def and then put the type def here, or you can actually just do it inline by using this kind of syntax where the name of the function is there, colon, and then the arguments, and then the return type. So just to show you how that looks, let me just look at functional demo. And don't worry if this is a lot of information for the language. We're going to be breaking them down into parts. So I'm just giving you a tour of the language for it. So here we have an anonymous function demo. Actually, maybe this is there you go. This is a good one. Okay, here we go. This is a functional map demo. Here we create an integer array of 5 elements. I think I'm initializing the array, just looping over it, and then we're going to map it. So we're going to take in the array, and then we're going to double it. So this is the map function where it takes in an x, and then we're just going to double it, and then the output is just the map of that. So here we can pass in a function that's declared here as an argument for the map function. If you did not want to create another function, you can obviously inline your function with anonymous functions. So here's another one. It's the same exact example, but here we just anonymously create the function. Where a function, it takes in an int, obviously returns an int, and it just times it by 2. And that's the functional demos that I wanted to show you. So far we've shown. Let me just tick the control flow, structs. I've shown you higher order functions. Let me just show you local functions quickly, and obviously simple control flow. I'm going to show you local functions. Okay. Remove that pen here. Integration tests. And don't worry guys, the video will be timestamped either by YouTube or I'll manually do it myself. So if you can always skip over this stuff. So local functions are one of my favorite features in programming languages. I start using them quite heavily in NoC, and yeah, there's a really good article by an email thread by, oh my gosh, I can't believe I'm forgetting his name, John Carmack. Yes, I don't know how I forgot his name, but John Carmack, and he's in favor of having larger functions, but nested inside, but having larger functions, not breaking them up and exposing them outside into the source code, because when you put them inside, no one else can see them, no one else can be confused about if they should call them, and nested functions are just a really good way to do that. So here you have one all test cases, and then it has a nested function inside it, which is one all test cases inner. This test case creates a new array list of test cases, And the test case is just a function. Sorry, it's a struct, which takes in the name and it takes in a run test case function. So we can see here that we're just going to be adding test case add. If you look at test case add function, it creates a new test case, assigns the name, assigns the function, and then it appends it to that array list. And we're just going to loop all over the test cases, and then we're going to get the test case function and run the test case. And yeah, like that's the really nice thing about sort of inner functions. And then, you know, we can just call the inner function ourselves. And local functions are my favorite for that. Just to show you how this works, we're just gonna run all test. We're gonna call this function from integration tests, and let me exit, run compiler, and we can see here that if you look at the output, okay, so I'm going to get the integration tests. So you can see here that if we're just looping over through this list, we're running test. So you can see here, we're running test case name, which is collection demo. We just run that test, then we loop through. We're doing a bunch of tests for here, a bunch of demos. So for each test case, we're just running that function. Again, higher order functions called in a local function context. So you can see that kind of stuff. And then it's running a pretty large test for GC collection. And then, yeah, so that's a good working example program. There's tons of examples in the NoC directory that you can look at. And yeah, so let me just take off local functions as a demo. This is Omar coming from the future to explain error handling in a much more succinct way. Now, errors in NoC are just like exceptions where you can throw something. When you throw something, you have to mark the function as throwing. And it can also return, the function obviously can return its own return value. Here we see that the result function is called several times, and the try keyword just means that I do not care about handling this error. If there's an error, just throw that exception back up one level and let someone else handle it. So here we're going to just run the compiler, and we're going to see that there's an uncaught NoC error object. This error was thrown, and nothing here caught this error. The try keyword is really nice because it allows at least the reader to know that you don't care that the exception is being thrown. Explicit error handling I don't really care for, because in application level programming, you just actually don't care about handling the error. You're just going to return it anyway. Like in most Go code that you'll find, it's always if error does not equal null, return the error. And that's not really doing anything. You'd rather just throw it up. At least with the try keyword, the reader can know that you're actually being intentional about throwing this error. Like you just don't care to handle it. And that is really, really succinct. Now, if you did care about handling it, the way you would do that is you have to write a catch statement. And this is how you write a catch statement in NoC. Right? This is how you write a catch statement in NoC. In the case where you throw and there is a non-void return type from the function, you get multiple return values. And this is how you actually have to write the catch statement. If you do not write this and there's another statement after it, then the compiler will complain saying you did not try the function call, you should catch it. So we can see that the compiler is explaining expected catch statement, but got some other expression and printing out something else. You need to handle that immediately. And this gives you that balance that I want to see in error handling anyway. In most cases, my error handling code would look like this, and I'll have a top main loop that's actually going to catch that exception. So that's the one reason why I like this kind of exception handling mechanism better than Go's, because in Go, in most cases, nearly 99% of the cases, I do not care about being explicit in my error handling. At least in this case, you have that kind of balance. And I believe Zig has the same mechanism. Now, in embedded system context, you probably do care about explicit error handling and you want some determinism. But unless you're in that constrained environment where you really care about proving determinism in your control flow, then for me, that this is the preferred way I'd do error handling. Cool. We're now going to move on to async tasks and features. How do you run an asynchronous task? Again, we take the ideas from Go, and we have no routines. Now, a no routine is just an asynchronous function. It's like a Go routine. As to why it's called a no routine is because I just wanted to kind of copy the syntax of Go, but also make it fit to NoC, and that's why it's called a no routine. It's for no reason whatsoever, apart from the fact that I wanted to use the keyword no. So here's we want an asynchronous function. We want two asynchronous functions. Here's one asynchronous function that we want. Here's another asynchronous function that we want. And it returns a future. And a future is, if you're familiar in other programming languages that have like a future construct, Java has the same, where you can look at a future object and it has a status. That's essentially what a future is. It's just a status of the asynchronous task in the background. Because the asynchronous task can fail. There can be a null pointer exception inside it. There can be a bad array index inside it, or there can be an error that the user actually throws. In this case, the future is going to hold all of that information. And what you can do, you can await on the future. And this is a non-blocking await. Now in Java, the similar thing that you can do is future.get. It's okay if you don't know Java or anything like that, but that's essentially what it is. But it's non-blocking, whereas in Java, it blocks the entire thread. And we'll go into what that is. In the most latest version of Java, I think Java 22 or something, they now have virtual threads. I have not looked at the runtime, but yeah, they support virtual threads now. And we're going to look at virtual threading and what that is much later when we look at the runtime section. But here we have two asynchronous tasks running. The await actually returns an error so external. So we're going to look at threading. So I'm just going to move that here to the side. Now this is actually stuff that we can look at an external await. So here we go. Now the await function, it throws. So it returns an error and it returns the result. Now what is the result? The result is the return value of the future. Now in this particular instance, there is no return value. This function is void. So there is nothing to store. That's why I'm not storing the result of an await. So here we just wait for these two features to complete. If an error happens, we don't care. And remember what we spoke about with error handling, with try. We just don't care. This error is going to be returned back to the thread that's waiting and then thrown up. We just don't care. Some error happened within that. And then we wait for both node routines to complete. And if the box integer result is 20,000, then we know that the mutexes are properly working. So here you can see that all these node routines do is they increment something 10,000 times. To do it safely, because these node routines run concurrently, they take a lock. And we're also going to look at how locks work and how we build up locks from the atomic intrinsics that are available to us. And here it takes a lock. And then when this function finishes, we're going to unlock the mutex. Now, if you're not familiar with the defer keyword, the defer keyword is used to call functions when the function exits. So anything that's marked with defer is called when the function exits. So as soon as we hit defer, we're not going to run this unlock mutex. We're going to run it when we actually exit out of the function. And that's really makes it really nice for lock-in, for file handles. If you like open up a file and you don't forget to close it, you just defer. And once the function falls out of scope, or once the function exits, I should say, then those defer functions are actually called. And the first time I have seen this is in Go, and I think it was so popular that I pretty much believe like every language has this kind of construct now because it's so nice. And the great thing about defer is if a function throws an error, as we've seen previously in error handling, the defer is still called. So anything that that has the defer before the exception is thrown, then those things will actually be called to clean everything up. So that's what's really, really nice about defer. And we're going to obviously look at how defer works and how you compile the defer, or how no-C compiles defer instructions. And that's it for the threading and the asynchronous stuff. So that's this stuff done right here. Okay, one thing we want to look at is non-blocking I/O. So now we look at asynchronous tasks. Let's look at non-blocking I/O. Let's look at another demo. By the way, you can run all of these demos yourself. You can just pull the source code and these demos are actually part of the integration tests for the language. We'll now look at I/O demo. Okay, now let's look at this server socket demo. In this particular instance, we create a server socket and then we accept any connections coming from it. Again, you can see that let's look at on the right side, we're going to see io.noc. So is it socket.noc? Here we go. Here you go. So when we create a socket, and we'll go into external function calls much later. But when we create a socket, we get a socket object back, but it can also throw an error because the socket creation can fail because we have to ask the OS to do this for us. But that can also that can return an error. So in that case, we don't care. No, we don't care. If it fails, then who cares? And if you can't accept a connection, then who cares? In both cases, this is the demo. Of course, if you can't accept a connection, you don't want your entire server to crash. So you might want to handle the error. But again, it's at the top level where you want to handle errors, and it will be in that specific case. But in this case, we don't care about the demo breaking or anything, so there's no point handling this error. So we accept it, and then we read from the socket, and we read 10 bytes. So you can see read socket takes in a socket or a connection or a socket connection, and how many bytes we want to read from that connection. Now, when we read from a socket, those bytes might not be ready because the client or the person that we're trying to receive the bytes from might not send it immediately, or there might be some delay. And here is where non-blocking IO is the mechanism here. Now in C#, or I believe Rust has the same thing, all asynchronous calls return some async task, and then you decorate each function call with the async task, and you await on the async task. It is really, really ugly. And Go is superb at this because it built into all IO calls is non-blocking IO, meaning that if no bytes are ready, this thread does not block. It yields itself and something else can run. And this is the mechanism of non-blocking IO. Now it yields itself, it captures the state of where it was in the program. So I said this line. And when the bytes are ready, then this thread, wherever this thread was running, would resume. And this is non-blocking IO. And that's how we can achieve concurrency. Even if we have one thread running, we can actually multiplex across this thread. Because imagine that we just have one thread. I mean, imagine we have one physical CPU core. And at this point, only one instruction stream can run. If we did not have non-blocking IO and we tried to read it and it did not yield, then until those bytes were ready, nothing else could run. Because we'll just be waiting for the bytes to be ready. But when the bytes, now that we have non-blocking IO, we can actually yield and let something else resume or continue or start. And this is how we get non-blocking IO. There are probably many, many bugs in the non-blocking IO implementation, but we're going to go through that. And there's many, many bugs in this compiler. But all the feature sets, well, the point of this language is to show you how everything really works. So it's at the stage right now where everything, you can read the code and you can understand the code. And although there might be bugs, the spirit of the intent is certainly there. And we're going to break down that spirit and figure out what's happening. So that's non-blocking IO. I don't know why I'm talking about spirits and stuff, but as I'm trying to figure out the next word, whatever comes to my head, I'm actually saying, break down the spirit of the language. That doesn't even make sense. But okay. So hopefully that was a good tour of the language. Again, you can look at the source code for that. It's totally okay if you did not understand some of the language features. When we actually look at the implementation of everything, we're gonna write some source code, see how it compiles, see how everything works, and that's how we're gonna learn how the runtime actually works. Now, step 1. So now that's all done. Okay, I just quickly paused it just to collect my thoughts. Yes, let's continue on. Okay, that's amazing. I hope I'm calling my own language amazing, but that's a good introduction of everything that's supported in the language. And of course, something that we did not show is that it's garbage collected, but I can't really show that in the language as part of the runtime. But now we're going to look at the internals behind the compiler, build up the intuition, look at the source code, and then build up everything that happens in order to make all of this stuff actually work. We're going to be revisiting a lot of the demos that I showed during the introduction, so it's okay if they didn't make sense. They'll make perfect sense once we look at how those things are broken down. Now, there are 4 things that happen during compilation before we can actually run code. Now, to do that, I'm actually going to look at the main CPP file of the compiler, and this would give you a perfect understanding as to what's happening. Okay. Now, the first thing that we do is we tokenize and parse the files, or parse and tokenize. So every no-C file that we can find, we parse and tokenize the files. If there's no parsing errors, then that's great. And we'll get into what parsing is. The next thing that we do is we do type checking. So, is everything type checked? Does everything actually make sense in the program? One of the things that we also do is we configure the layout of the objects, how the runtime is going to represent them. Like say a struct of a person, say something like struct person, god damn, I couldn't even spell it, integer x, integer y. What is this layout and how should it look in the runtime when we actually run it? So we configure the layout. You can ignore the dependency order and stuff like that. That's not really important. Then we generate the actual virtual instruction code. This is the code that we're actually going to run. And we're going to give that entry point, which is the actual instruction stream, and we're going to give it to the virtual machine or the runtime or whatever you want to call it. We're going to boot it and we're going to run. And that's the 4 stages of compilation to runtime. The stage that we're actually going to focus on is how do we get from text, which is, if you look at main.noc, how do we get from text, which is what this is, into something that we can execute? Now, really what we're focusing on is main.cpp. How do we get from files, text that we read from the files, to the entry point that we get, so up to this point that we get. Now I'm going to put a debugger here, and you can see I'm going to actually ignore that because I don't want it to blow up. Let's just say printf hello world. Okay, and there's a reason why I commented out the integration test. We're actually going to run that. Okay, on compiler, and here above you can see that these are all the instructions that are going to run. This is the virtual instruction set. How do we get from text to this virtual instruction set? And that's the kind of challenge that we want. We don't really care about how the virtual instruction set works. It's just instructions that we're going to run in a virtual machine, and we're going to look at that. That's not really important. But we can see that the first stage of compilation is getting to this point, getting to instructions that we can actually run. Now, we can actually look up some stuff. Let's look at main. So here's the function main, which is is labeled main. We can see, hey, we want to load a non-native string. So I assume it's hello world. Non-native, that should be kind of a clue. It's not a string constant that's managed by the no-C runtime. Then we want to change that into a native string. So you can see that something the runtime is doing is changing it to a native string. Then we want to, well, we load an immediate value, but that's not important. And then we call printf. And that is what the main function is doing. So you can see that, okay, cool. We look at the main function, it's some text, and these are the instructions that are generated from that. And these are the instructions that we're going to execute. So how do we get from text to instructions that we can execute? Now, before doing that, let me just run it in the debugger. I'm going to get rid of all the debug symbols and main.cpp. So I'm just going to now put it on this point. So just to show you that again, we're going to wait for the debugger to start. Sometimes it takes a while to happen. I'm going to pause the stream so you don't have to wait. Okay, now we're back. So the debugger was taking a while to start. Okay, now how do we get from reading the files, reading the text from the files, and then getting to this point where we can actually generate the instructions that we actually want to execute? So essentially how we get from here to at this point where we can actually start generating some instructions. We don't care about how the generation of instructions works. It's actually really, really simple. We care really about how do we get to that representation where we can generate code from plain old text. So here I'm just going to step through it. So how do we get from here when we read all the files to then at this point where we can generate some code? Okay, so we're going to stop the debugger at this point. And the debugger is really, really useful. I think the debugger it comes part of the Docker file, so you don't have to configure it. If you use VS Code in the README, there's a there are instructions on how to connect the debugger. So definitely connect the debugger, step through the code, and see how these things work. But it's okay, we're going to go through that as well. And I'm going to use the debugger to step through the source code as well. But let's focus on this part. Step one that we want to look at is how do we get from text to instructions? What's the motivation behind tokenization and parsing? And we've probably heard if you've studied a bit about compiler literature, you've definitely heard tokenization and parsing. And I'm going to actually explain it probably here. It's going to be a good space. Yes, very good. Okay. Now, oh, 1 second. Okay, perfect. Okay, now we have some text. So let's just say we have a function, returns it in, takes in an int. Oh, I forgot to name the function. 1 second. Okay, we're going to call this the identity function, and the identity function is something that just returns itself. 1 second. I'm trying to write this in no C syntax to keep it quite precise. And then obviously it just returns itself. Now, this is some text in some file. We want to create a programmatic representation of that text such that we can manipulate it, get all the information out from that. Now, you might have already heard of the representation that we're going to use is the abstract syntax tree. This is a tree representation of the source code. So from text, we're going to make nodes that represent a tree. Now, why do we do that? Because let's actually write some kind of a program with many things inside it. Okay, so the same thing again. We're going to call it identity, but identity integer x. But we're going to have many things running inside this. Okay, so let's just have fx. If x equals 2, let me just cancel that out. If x equals 2, we're going to print f yes. And then regardless of that, we're going to print f yes. Apologies for the handwriting. Okay. Here we have a function, you know, it has the function itself, and it has 2 statements or 2 pieces of control flow inside the function itself. And we want to get all of that information out from the function. So the first thing that we want to capture in the function is let's just say we make a struct or a class. This struct is going to represent all the information that we can get programmatically that represents a function. Okay, so if you look at this function, what can you see? Okay, we can see what the return type is. Okay, that might be something that we care about. We can see what the name of the function is. That might be something that we care about. Obviously, we see that how many arguments the function has. It has 1. What's the type of the argument? Okay, so that's quite interesting. Let's actually create that struct. Okay, so the name of the function is going to be a string. And remember, we're going to go from text to a programmatic representation, and this is how we do it. We're just making a struct that's going to contain all of that information, such that when we look at the text, we're going to get all of that information out from the text. We're going to come back to abstract syntax trees in a second. Okay, here we go. We've got the name, we've got the return type, and for the return type right now, we're just going to put it as a string as well. Because remember, it's just text that we're looking at. Return type. Return type. God damn, the handwriting is awful. And we're going to look at how many arguments there are. So this probably will be a list, or in C++ is a vector. So vector of, we're just going to say it's a string. And how many arguments there are. This is all the information that we're trying to plug out. Okay, now, here's where we get to more things inside it. How many children are there in this function? Now you're going, children, okay, well, where are you going with this? It's the relationship between the source code and how we want to map it to a tree. Now, we look at how many children there are, how many statements. There's an if statement, there's a printf statement. And there could be many statements in a function. I mean, let's look at some examples, quite literally. Here's a function main, it has a function call, another function call, and then another function call, and then it has an if statement. So a function can have many, many things inside it, right? Okay, we're not going to really focus on that. Let's just say right now, a function can only have a function call inside it. There can only be one thing inside a function. Okay, let's erase it. Let's just say there can be only one thing inside a function. Okay, oopsie daisy, let me just erase all of that stuff up. And the one thing that can be inside the function is a function call itself, okay? Okay, and we can have, let's just get the pen out again. And we have the function call itself. Function call. And then we're going to see this is a function call. Just going to call it a call. Now, what's the information that we want to capture in a function call? Well, we want to know, let's make another struct, right? Struct. Function call. By the way, you can use struct or class. In the code I use struct, but they're the same thing, struct and class. I think in C++ there might be one difference in them. I remember asking Claude, what's the one difference in them? And I remember it saying something, but I can't remember. But effectively, they are the same thing. I just use the word struct just because in NoC the keyword is struct, and I wanted to make the C++ code quite similar to NoC code. As I was writing out the C++ code, I wrote it in the style of NoC, so this could it was kind of a litmus test to see if I'm enjoying writing the kind of grammar that I was trying to construct with the language. Okay, so what's inside a function call? Well, let's just say the function call has a name. Again, another string. So string name. And then again, it would have like a list of arguments that you could get. So again, a vector, we're just going to put in strings right now, of arguments. And then, okay, now we have two things. Now we have two representations that hold information from the text of the programming language. Okay, and it's like my handwriting was so much better. Okay, fair enough, it actually was not. So, okay, cool, now we have two things. Okay, now, instead of a function just having the one thing, let's just say a function can have, it can have an assignment as well. So it can have two things now. Okay, so it can have a function call and it can have an assignment. Let's just say it has to have those things. So we have a function call here, and then we're now going to have an assignment. And hopefully you can see what we're trying to do here. We're just trying to, look, we have assignment. Okay, and then the assignment, let's just have it here. It's another struct. Again, it's going to capture all the information related to an assignment. An assignment can have, obviously, it has two sides. An assignment has the left side, which is the name. So again, we're going to say it's a string, left side, or left side identifier, or left side symbol. And then we're just going to have let's just say assignments can only have numbers for now. And then obviously we're going to have the number, so it's the right side. And that's the assignment. Okay, let's see more things that can happen. And you can probably see what we're trying to do now. Anything that we can represent in our programming language, any statement that we can represent, or any control flow, is going to have a representation that we can capture inside a struct, inside a class. Anything that we can have. Okay, let's just do another one. Okay, let's do an if statement. Okay, so let's just say a function call has to have an assignment, has to have a function call, and then has to have an if statement. Now, I'm not going to write it here. I'm just going to write it underneath here. So again, what are the constituents of an if statement? You have an if statement, and we have a conditional, x equals 2. And then we have however many things are inside the if statement. So how are we going to capture the if statement? Okay, interesting. Let's make another struct to capture the if statement. If statement. And as you can see, we're just building up a programmatic representation of every construct in our language. What's the only thing that inside the if statement that we actually care about right now? The conditional, right? And what is a conditional? Okay, let's break it down. More than or less than, equals, not equal to, less than or equal to. So we have the operation that separates the two operands, right? So what kind of expression would this be called? We can call this a Boolean expression. So a Boolean expression has the operand, has the operator and the two operands associated with it. So an if statement has itself a Boolean expression. Let's now represent this as a struct as well. Again, we're just capturing everything that we can get from the text, parsing that text out. And that's the key insight right there. We're parsing it out. And a Boolean expression has what? Has the operand, the two operands, left side and right side. So we can say, okay, operand. We can say that it's just a string for now, because we just grab the text, left side. God damn it, left side. That doesn't even look like English. So left side. And then we have the right side. And then obviously we have the operand, and the operand again will be a string. And the operand is the Boolean expression. Is it equals equals? Is it less than or equals? We're going to capture that. And then obviously we can now add this into our struct, Boolean expression. Okay. And then we're just going to say expression. Okay. Let's now trace, right, from the function call that we have here. Let's trace down all of these things, okay? And we're going to see that it looks like something, right? And also we'll just say a function call also has to have an if statement. So there has to be an if statement here as well, okay? If x equals 2, okay? It has to have it, okay? It makes the if statement. If statement. Let's trace it down. Let's say somehow we churned that text and we made it into this object, this function object. How would this function object look in terms of the hierarchy of objects? Okay, let's, I think I can actually just grab this and just move this entire thing. Okay, that looks good. Oh, yes, I can move it. Beautiful stuff. Okay, let's now trace it. Let's trace this function, okay? Okay, let me just get the pen back. So here, if we actually look at it, so like into a debugger, if you looked into it, a function has a function call, right? A function call. That function call has a name and it has an argument. Name, argument. The function also has an assignment. And that assignment has a left side and a right side. Right side. And it also has an if statement. And that if statement has a Boolean expression. And that also has the fields that we spoke about. And these are those three things. So can you see that here, it kind of looking like a tree, where each top level node has children, and each node itself also has children. But children only just means fields, right? So here we have a Boolean expression, right? Okay, now let's actually make it realistic. Obviously, a function call can have many, many things inside it. It can be many, many things. So a function call, instead of having a hard-coded fields, like it can be function call on assignment, it would have a list of these. It would have a list of these. And the if statement itself, inside its body, would have a list of all these things as well. The assignment as well would have the left side, and the right side doesn't have to be a string. It can be a function call as well. As you can see, we're making a tree. And this is why the abstract syntax tree is the representation of the text that is used in compiler literature, because it captures the textual representation of the source code, because the source code is already a tree. What do I mean by that? right? Let's look at some no-C code. Let's look at, I don't know, like demo. This is not really a good one. Integration tests, maybe this. Okay, here you go. We have a for statement, okay? The for statement has children. What are the children? It is an assignment. Left side. What's the right side of the assignment? A function call. There's also another child, which is a function call, and another function call. So the tree representation is the natural representation because it captures the representation that's already in the text. You can see that. Well, there's our children here. You know, that's why we can indent it out. There's children here. So here we can, if you can break it up, this function call has 3 top level children. I mean, you can see in the source code, we have an inner function, we have a function call with an assignment, and then we have an if statement, and then we have a final function call. And that's the representation that we want to capture. We want to go from text and then make these objects, make these function calls, assignment objects, if statements. They're going to capture all the information that is relevant to that specific node in the tree. And this is why it's called abstract syntax tree, because each node refers to some construct in the programming language. And a node, depending on whether it's a function call, can have many children, or it can have 2 children, or an infinite number of children, like a function call. So a function definition can have many, many things. I mean, the function can be 1,000,000 lines long, so it would have many, many children. The function call itself can have the name, obviously, and how many arguments. The arguments themselves don't have to be literals or booleans. They can be expressions, 2 + 2, right? Well, we've seen a boolean expression, so there could be an arithmetic expression. So each node represents some construct within the programming language, okay? And that's why we have the abstract syntax tree. Once we have the tree in place, we can traverse the tree, right? And this is called tree walking, but we can traverse the tree, and that's the programmatic representation that we need. Okay, now we're going to go into the source code. I hope that made some sense. We haven't looked at how we get from text to a tree yet, but assuming that we can somehow capture that information and then put it in an object, and that will be the final object. This relationship that we want to show is a tree relationship. Now we're going to make it quite official by looking at the source code. The first thing that I want to show you is the nodes that are all the nodes that we can have. So here's, obviously we have many, many different kind of nodes. Here's one node, another node here, another node here, another node here. I'm going to walk you through all the nodes that can actually be part of a tree. And depending on the parent node, they're going to be different kinds of children that can be put in there. And we're going to take a quick pause, and we're going to let that digest, and I'm just going to come back. Okay, we're back, and it's quite dark and it's quite late because I keep running out of charge. I'm jumping through recording it throughout the day. Hopefully the charge lasts this time around. Just before I left off, we were just talking about the tree, the abstract syntax tree, and how we can represent each top level node has its own children, and each node itself can have a number of children depending on what kind of node it is. We're now going to look at the source code, and I'm going to show you some of the nodes in this tree as we build out this abstract syntax tree. To do this, we can just go to ast.h, and the first node I'm actually going to show you is actually all the node types that there are in this language. Each node type refers to, like in Mara that we can see, whether it's a function or a function call or assignment, if statement. So let's just see that there are many node types. I'm not sure if all of them are in use. I think there's one that says interface or something. Like, for example, interface node, this is not used anywhere. There was a time where I thought I'd have interfaces in the language. And you can see yield is not used anywhere. So this is not every single node, but I think maybe 2 nodes here aren't in use. So you can see interface here. But we can see that, we have a node for an if statement, a function call, a closure creation, a lambda call, a function parameter, anonymous function. You see each construct in our programming language has a node type associated with it. And each node type has a struct representation that has everything that we might need to know about that. Continuing on from the example in Maro, let's look at the node type for a function definition. So there you go. So we have the node type for function definition. We're now going to look at the struct for that. And remember when I showed you here. That function has a name, a return type, maybe some arguments, and has a series of things that we can put inside the function itself. Let's see what we have. We have an AST function definition. It extends from AST node. We'll come back to that in a second, but we have a function name, the parameters for that function. You see it takes a vector of a declaration, and declaration is, in this language, it's let me see where I can find the function. It's this, when you declare a type, integer x, boolean y, that's a declaration. So we can see we're just trying to chunk out the text into these nodes. And then we can see some additional information, like if the return type is void, if the return type is an array, does it throw? So you can see in main.noc, does it throw? So if you see throws, yes, it does throw. Has a polyargs, we'll go back to that. Is it an external function? And you might have seen this already in some of the demos. If you look at here, we have an external function. And I didn't explain what an external function is, but I'll explain it way at the end. An external function is stuff that the language itself cannot implement. So this is like creating a socket. This cannot be implemented by the programming language because I have to call the OS. So I call externally, I call an external function. But that is, let's go back to ast.h. And that's what those fields are really tracking. And then of course we have the body. Now previously I mentioned that, we imagined the function call only has 3 things. We have an assignment, an if statement, and a function call is, so a function definition can have 3 things: a function call, an assignment, or an if statement. But really a function definition can have an infinite many of these nodes. You can have an if statement inside it. It can have a function call. It can have a for loop. It can have a list of these things. Now this is where this inheritance hierarchy starts to make sense. Now, everything in this programming language is represented by a node and a node. If you're not familiar with inheritance, I just assume that everyone is familiar here with inheritance, but everything extends from an AST node. All programming language in constructs is a node in the actual abstract syntax tree. Each node has a type. So you can see here, a struct definition, a function call, and we just have some line number information, which file it came from. And all of these things are representative of some construct in the programming language. So here we have, let's just see a function call. So here's a function call, and when we actually made the struct for the function call, if I have it here somewhere, here, you can see I have a name and it has the arguments, right? So here, the AST function call has a name and it has an argument, right? Let's just see some other things that might be quite simple to map up. Let's say we have a Boolean expression, because again, we've created some Boolean expression here, right? A Boolean expression is also represented by some node in the tree. And again, it has the operand and it has the left side and the right side. But in specifically, the left side and the right side are of type AST node. And everything extends from an AST node, which means that the left side and the right side can be anything. Whereas in this particular example, when we wrote in Miro, it could only be a string or some literal value. But a Boolean expression can be, right, we can say like if it can be x equals foo. So that this one could be an identifier, this one could be a function call, or it could be if true equals false, both of them being literal values, or it could be 2 function calls, if foo equals foo. Right? So the Boolean expression can have anything on either side of it, and this is where the inheritance hierarchy in AST or abstract syntax tree structure starts to really, it makes everything really convenient, because everything can extend from AST node. So you can actually replace left or right with any construct in the language. Now, because everything extends from AST node, technically, it can be an inside the if is another if, because if is an AST node. But the type checker would stop that from happening. In some publications, you might see the difference between an AST node expression and an AST node statement. I have not done any of that. Everything is just an AST node. Let's look at the if statement that we have here. If statement, here we go. So the if statement that we defined here, if I can find it, an if statement has a Boolean expression inside it, and it has some statements inside it. Let's see what this is. There you go. So you can see the if statement has a Boolean expression, and it has the body that's inside it, and it has a bunch of other stuff that's associated with it, like the else chain and the else body. Because you can have an if, else. So all of that information is captured here. One node that we're going to look at is the AST body. All an AST body is just a list of AST nodes. So here, and that's how we actually how we nest nodes that can have a list of things inside it. Now, let's just look at a function. Okay, and we're going to just map it back. Function, foo, just a void function, but you can have a list of things inside. Maybe it has an if statement, then a function call, right? Then maybe it has an expression, right? Then maybe it has an assignment. Then maybe it has a no routine that runs inside it, okay? Maybe it throws, right? A body is exactly what it is. It's the body of some block, basically. So a function definition has a body, an if statement has a body, a for loop has a body. A body is just a list of statements that you can put inside it. So that's really is, and anything can go inside it. So you can see here that anything, you can have anything that can go inside it. And this is how we're building out the structure. This is the abstract syntax tree that we're building out. It's a tree because it traverses like a tree. I mean, if we actually, it's almost literally a one-to-one mapping with what we drew in Marvel. But so here we have a function greet, right? And inside it just has one function called with printf. Now, if you look at the tree that we generate from this, it's very similar to the kind of tree that we generated by hand in the mirror examples, but we're going to be using our constructs that we have in the language. We have an AST function definition, that's the top level root node, because it has a function name. It has no parameters. It does not, it is a void, and it does not throw an error. And now inside the body, a body is just a list of statements. How many statements are there? There's one function call. So the function call has a name, has an argument. What are the arguments? It's a literal value, which is a string. Can you see that it creates a tree structure? And that's why it's called the abstract syntax tree. We're getting that textual representation, and then we're creating the AST function definition node, or any node that's relevant to the piece of text that we're looking at. And depending on the piece of text that we look at, we can infer whether it needs to be a function definition, a function call, a literal value. It all depends on the context of what the user's written, and whether that is something that is correct in the grammar of the language. Because a function has to be defined first by having the function word. It can't just be greet by itself. There's no such thing. The grammar would not be recognized by the language. This is what we mean by creating an abstract syntax tree. And there's just so many that capture pieces of information and that we compose to create a bigger and bigger tree. Once we have this tree, we can actually just traverse over this tree. And we're looking at, we're going to be looking at traversals a bit later. Let's look at this one with an addition. Okay. Again, we have to create the root level node, sorry, which is the function definition. We add, it's called add. The parameters are two things, A and B, and they're both typed in. The return type is a type string. The return type is also void. And what's the body? Well, the body is a return statement, again, by this one. See, each construct in our language has an associated node with it. And then we have an arithmetic expression, which is A plus B, and the left-hand side are just identifiers. Identifiers is an identifier, whether it's, foo, bar, it's just considered an identifier. So each particular thing has a AST node associated with it, which then creates the actual tree that we can have. imagine that we can also traverse this, because the body is just a list of statements. So we can just loop through the body, and then for each node in that, we know the structure of that particular node, and then we can also just iterate across that as well. And that's what the AST really allows us to do, is create that representation that we want from text into specific nodes that are going to represent that text. Now, before we can actually represent nodes, initially when I explained it, the text was magically somehow created into these AST nodes, right? It magically happened. That part is just called tokenization, right? And I'm just going to explain tokenization right now. Okay, now that we've actually explained the AST, and I hope that the AST makes sense. It's just a node, and each node represents some construct in our language, and we can nest nodes together to create the abstract syntax tree. And with that tree, we can traverse it, and we have a programmable thing that we can actually manipulate. We're going from a text representation to the AST representation, which is a physical thing that we can program against. Obviously, you can't program against text, it's just text, but that's what we're trying to get at. Now we can actually explain the first part, which is tokenization. Is here this is the end goal that we want to be, but how do we make sure that we can actually parse out this information? That's why it's called parsing, that we can actually parse out this information from the text. The first thing is tokenization, is actually turning these pieces of text into tokens. Now, here we have a function that's foo, but I'm going to write it again actually. Let's zoom in. Function foo. And a token for the tokenizer is breaking up each particular, I'm going to say word in the programming language or punctuation, and instead of actually having the text representation, we have a token representation of that, which is a struct. And a token has a type associated with it, like what token is this? Like what word does this represent? So token type, and it also has the text associated with that. So we're just going to say string text. Some places called lexeme, but you know, associated with that. And that's all a token is. So we're going to break up the actual characters in the text file into these small pieces of tokens. With this token stream, we can then give it to the parser, and then the parser can then generate the correct node structure for it. And don't worry, we're going to debug it and look into how that works. But just try to keep that intuition to your mind. We're now trying to just break this piece of text into tokens. And this is what the tokenizer does. And it's probably the simplest part of writing any programming language. The classical literature is very dense into mathematical formalizations of tokenization. There's NFAs and DFAs and all of that stuff. We don't really care about that. We'll just have a handwritten tokenizer, which basically we keep looking at characters and try to build the largest token that we can. So I'm now going to look at tokenizer.cpp. Okay, let's just go into, maybe we can actually look at tokenizer.h. Okay, how many tokens types are there? So if you were to like chunk the text down, how many different chunks can we get? So let's look at main.noc. So the first part is to break up this piece of text into chunks of text, and each chunk is a token. Okay, so we can have a token for function, right? Function, so function, okay. Maybe we can have a token for throws. We can have a token for open curly brace, open curly bracket. We can have a token for a string literal. I think it's called a literal or something. Number literal or real literal. What the heck was it called? String, there you go. A string literal token. And all these other tokens that we can have that don't represent key grammar in the language. Like function is a reserved keyword. We can just call them identifiers, right? Everything else that's reserved for the language, no, for, return arrow, underscore, defer. These are reserved keywords that actually mean something in the grammar of the language. Like if we were to put the grammar of the language, it would actually have to be these consecutive tokens. Otherwise, the programming language doesn't make sense. Like a function has to start with a function text. Then it has to be followed by some name. Then it has to be followed by some open brace. Then it has to be followed by some closing brace. It potentially could throw, so the throws. So tokenization is just getting those pieces of text together, clumping them up into the biggest token that we can find, right? And it's easy just for me just to show an example from the documentation. Okay, so now here is the same kind of example actually. Let me just change it. So no c, x equals 1. Okay, here's the same example. Now, the tokenizer is just going to chunk these pieces of text together. So we can see function, that's a function token. Identifier, which is that main. And then we see open round bracket, close round bracket, throws, open curly bracket, identifier, equals, there's a number literal. And then we have a semicolon. Then we have a close bracket. Now we're chunking up the pieces of text together, and then we're going to feed this token stream into the parser. Then from the parser, depending on the token, we can generate the correct AST node. And that's why I wanted to first explain AST nodes, because tokenization is really super simple. We just loop over the text and we try to find out the largest token that we can find. And as you can see here, the token stream is the output, but it points to these literal pieces of text. We clump them together, and then now we have a token stream. We give that token stream to the parser. Now we're just actually going to look at debugging this piece of code to then create the token stream. Then after that, we're going to debug the parser to then create the AST function definition that's associated with that. Okay, so this is the tokenizer source code, and the tokenizer source code is really small. It's about 700 lines, and the output is a token stream, a list of tokens. And just to look at the top, what is a token? Again, a token is, if it's just code out here, a token is just a clump of text which has the token type and the literal and some other file information that we might be concerned with. And a token type represents either a reserved keyword in the language or an identifier. And these are basically all the keywords that we might have. We're just clumping up pieces of text together. Now the tokenization, or the tokenizer source code, is incredibly simple, okay? We loop over the character stream. If the character is a letter, then we try to identify whether it's a reserved token or if it's just an identifier that the user made, okay? Is the character a number? If it's a number, then we do something else. Is it non-tokenizable, meaning that is it some hidden characters within inside the file that you can't see? Like, for example, if I do a tab, you can't see that character, but that character is still in the file. So we just skip over those. Is the character a speech mark? If that's a speech mark, then it could be a string. So we make the token string for it. And this is the kind of the loop behind the tokenizer. We just loop over the characters and try to clump up together. I'm going to put the debugger on, and we're going to tokenize this function. Okay, let me just add the debugger. Yeah. Okay, now we're just looping over this piece of text. Now the first character, if we actually look at it, the first character is not a single quote, it's not a speech mark, but it is a letter. Okay, so we're just going to jump here. So if you actually jump over the code, it is a letter, okay? And while it's a letter, so while there's not a space, maybe I can move that. While there's not a space, we keep reading over the characters. If it's a letter, we keep reading it. We allow underscores, so you can have underscores, so you can have a snake casing, so you can see if it's an underscore. So we keep reading until we see something that's not a letter. And the first thing that isn't a letter is a space, right? We break out that loop, and then we see whether we can add a token for a keyword from this raw piece of text, from the function text that we just got from this file. Let's see if we can add a token for keyword. First, we search a token for a keyword. Now, these are all the keywords that are supported in the language, right? It's just a keyword mapping, which is it's just an array of these things. So new. These are all the keywords, and we're just going to match the text that we just captured with any of the keywords that are here. And there is one, which is the function declaration literal. So we're going to loop over all these keywords and then find the token that matches it. If nothing matches it, then we're just going to return null. But something is going to match it, and that is the function token. So we can see that the token type for this is a function. So here we're clumping up that piece of text. Okay, now we return a token for a keyword. We're back now to the main tokenization loop. The token is not null, so we know it's a keyword, so we know it's not an identifier like a named variable that the user might have. Okay, we do the same thing. Okay, each non-tokenizable character is just, we just skip over any white space that they might have added, and then again we go back to the main loop. So now we've got the first token, which is function, and now we're going to look at the next one, which is main. Right? In this particular instance, we do the same thing, but we're going to arrive. The character is a letter, but we're going to arrive here because there is no keyword for main. It's just a user-defined function name. So it's not going to be considered an identifier. Okay, and everything else we just carry on. Right? Now, in this case, the next character is not a single quote. It's not a speech mark. It's not a character. It's an operator. Well, I call it an operator, but really it's a punctuation or an open bracket. Right? And we go in here, and this is exactly what we're doing. We're just looping over the text, clumping the text together, and to produce the final token stream. Now, the documentation has a good example of this here. If I can just close it. Can I? Maybe I saw the debugger. There you go. It's exactly what we're doing here. We clump together this piece of text, so we get a function token, identifier token, open round bracket, close bracket, throws. Again, it will be clumped together, but there's a keyword for this, throws, and then we have open bracket. So instead of having just a text stream that we can give to the parser, we give a token stream, which is a mapping from keywords to actual tokens. And a token is just this. It's just something that has a type. A token type is one of these things, a keyword, an identifier, something that's considered as part of the grammar of the language, and has the literal inside it, and some file information. Now, tokenization is just that, not complex one bit. The only thing with the tokenizer specifically, it only supports ASCII text. So if you write in Arabic or something, that's not going to work out because it doesn't support Unicode. So if you wanted to support multiple languages, you'd have to support Unicode encoding because I believe Unicode encoding has support for non-ASCII, well, non-English languages, and English can be represented in ASCII. But that's really it. That's the first part of tokenization. Now we can feed that into the parsing stage to then create the AST function definition. We're going to look at that right now with the debugger, but I'm out of charge, so I'm going to charge my laptop right now. So it's going to be even later when we have the next part. Okay, we just spoke about tokenization. Let's now see how the AST node for the function is parsed out and built. So we're just going to debug it. The first thing that we're going to do is we're going to tokenize, and you can see that the file name is main.noc, so we're looking at this file on the right hand side, and we're going to build up the node for this particular piece of syntax. So first we're going to look at the token stream. We're going to tokenize. The token stream is going to produce this token stream function followed by an identifier followed by open brace, close brace, throws. The print token stream is actually just building from the token type how it would look like. So that's where you see the actual word function, but the actual is this is the stream of tokens. Now once we have the stream of tokens, we're now going to parse the program. Right. So firstly we create a body, and a body again is just a list of statements that we're going to put in, because a file can have many things inside it, many functions, struct definitions, and this is the main loop of the parser. So we're going to read so long as we have tokens. So that's what the token stream allows you to do. Just keeps reading until you hit the end of the stream, and just going to play it. So is the first token a struct? No, it's not a struct. Is it a type def? No. Is it an import? No. Is it a function? Yes. And now we're going to parse the function definition, because that's the grammar of the language. Once you see a function token, we know the rest has to be has to conform with how we expect a function definition to look like. So now we're going to pass the function definition. You can see the pass function returns the AST node for the function definition. So we're going to read out all of this information inside here. And if the grammar is not correct, for example, if a user does that, well, this is not the way you write a function. The syntax is not correct, and the parser would be able to recognize that. So let me just carry on here in that file. Let's just go back. So we're now going to step into the pass function declaration. And you can see we're just going to stream over the tokens. Is this token that we're looking at a function? If it's not, then this is of course an error because we expect a function to be there. Cool, we know it's a function. We're now going to read the token. All read token does is we're just going to increment the index, and then we're now looking at this token. Is it an identifier? And is it an open round bracket? So that's how we know, like a function always has to have an identifier followed by an open round bracket. Otherwise the grammar is incorrect. Yes, it is. If it is, then that means that the user did not put a return type. So we know that the return type is void. And we can also take the function name from the token we were looking at, which is the identifier. We take out the literal from that token. So remember, a token is just a chunk of text which contains the literal, some file information, and the token type. And then that's what we're doing. We're just building out the definition. So we're just reading the next token, and then we go, okay, if there's an open round bracket, yes there is. We're going to read that token. We're going to pass the function parameters. Is the function parameters valid? It is valid. Is there a throws? So we can't see here. Can I move it here? Okay. Is there a throws? If there is, then the function does throw. We're going to read that token. Is it external? The function is not external. And then we're going to pass the function body. So what's inside this body? So now we're going to go in here, inside here. Now in the function body, we realize that the body has to start with an open brace. And you can see we're just streaming the tokens and reading them one by one. And then we pass the statements. So everything inside the body. And pass statements, we're going to now pass every single statement that might be in this particular body. And we're just building out this AST, and we're just adding each statement that we build up, we're going to add it to the body of that function definition. So if you look at the ASTH function definition, we're now just adding every statement that we can find inside this body. And that's so good. That's what parsing is just it. We're just going to read over the token stream that we built up, and we're going to look at it token by token. If it's a reserved word like a function, then we know that the tokens after it have to conform to. We know that the tokens after it have to conform to the grammar that we have. Basically, meaning that the tokens after it have to be a particular sequence of tokens. So for a function, let me get the pen up. For a function, let's see. There you go. Let's just zoom in a bit more. For the function, it has to start with the function token, and then we're going to put throws here just to be consistent with the example we were looking at. To be honest, let me just write it like that. Throws, and then the body. So this is what all the tokenizer, so the parser is doing, looking at token by token, saying, okay, is it a function token? Yes, and then we know we're looking at a function. But what has to happen after the function token? An identifier, then open brace, then close brace, then potentially a throws. And then the body has to be open with an open curly brace and a closed curly brace. And then for the body itself, we just pass the body. So when we pass a function, it has the body. Pass function calls pass body, or pass statements it was, but we're just going to pass body. And the body also can have particular different things as well, depending on what happens with inside it. So if there is a printf inside it, we're going to look at the token. If the token is an identifier followed by if it's an identifier followed by an open brace, then we know that it has to be a function call. So now we build up the function call. And the parsing is recursive because each construct that we might pass might cause us to pass, go back up again to pass the body of the function. For example, a for loop has a body inside it. And then we're going to start the parsing process again to see what's inside this body. So it's recursive. To illustrate the recursion, and this is the final thing that I'll speak about from the AST. To illustrate the recursion, let me just write a function here. Function main, the same thing that we have, throws, just to show. And then we're going to have a for loop. And then inside the for loop, we're just going to have printf. So this is infinite for loop, hello world. And we're just going to look at how it's passed, just to show you how that might be tokenized. Here, see, we can see the first token that we find is a function. So we know we're going to have to pass a function, which means all the tokens after it have to conform to some grammar. When we hit the open brace, that we know we're going to be passing the body of the function, and the body can be anything. So then we're going to recurse back up to the main passing body function and then pass up again tokens that we expect to be inside a body. But the for loop again would have a body, so again we'd recurse back up and then pass the body of that. So that's why it's recursive, and we're just going to step through the code to see how that looks like. How would this look? So now we have this this main file, function main throws, and it's an infinite for loop. We're just going to handwrite the AST nodes that the parser would actually build out for us, and we're going to use the actual the nodes that are in the programming language, so in the implementation of it. So the first thing that we're going to build up is the AST function definition node, function def, and this one would have whether it throws or not, all these fields, the return type that you see the parser building out, and then of course it has its body. Remember, body is just a list of statements inside it, so then we're going to pass the body. So the first thing that we find in the body is the AST. Let me remind myself of what it's actually called, so I'm at least consistent. AST, so AST, is it for loop? Yeah, so AST for loop. For loop. And then the for loop has, if you look at the definition, it has whether it's a conditional, the post conditions. Remember that a for loop typically has three parts to it. The assignment, I equals 0, I is less than 10, I plus plus. But in this for loop, there is none of that, so this doesn't get included. But it does always have a body, because a for loop has a body, and the body itself. So we have another AST node. Let me actually be precise. This is called, I think it's called AST body. So let me just correct it here. AST body, and the same thing here as what we have here. AST body. And inside that body we have a function call. So AST function call, right? And it has the name and it has the arguments for that function call as well. So AST function call. And then this one would have the arguments as well, whichever list of arguments. And the arguments themselves can be anything. They can be expressions. They can be also the function call. They can be null, a literal, anything. And that's why extending everything from AST node makes the parsing simpler, because anything can be stuffed in here. And in type checking, we just check whether the argument, the node, is of a correct type. For example, the node cannot be, it can't be a match inside here. That would not be correct. But it can be an array subscription assignment, it can be an array access, it can be an identifier. So that's why just extending everything from node just makes the parser a bit simpler. And in type checking, you can just make sure that the correct node is passed, or even the parser can do it for you. And that's the actual AST node structure. So let's just draw out that tree here. There you go. So here you go. We just have this tree, and you can imagine how you might just traverse this tree. Is we first look at the function definition, then we iterate over the body, then we find out that the first thing in that body is a for loop, then we iterate over its body, then we find the first thing is a function call, then we iterate over its function parameters, and that's tree walking. We're walking the tree depending on the node. And that's as simple as it is from a parsing perspective. The one thing about parsing or the abstract syntax tree structure, it's very memory dense. For example, like if you see the bytes of this, how many bytes there are of this file. I mean, how many characters are there? And each character is a byte. I'm just going to say there's 100 characters in this file. Probably way less. Let's just say 50. I'm not going to count it, but let's just say it's 50 characters. So that's 50 bytes. Each character is 8 bytes. No, each character is 1 byte. So it's 50 bytes. But however, the AST node is really like it's an AST node. If you look at how big it has to be to capture that information, everything extends on this one. So it has to have all of this information, and then it also has to have the information for its particular node as well. So it's really memory hungry, the abstract syntax tree. But it's the only representation I know of that makes intuitive sense anyway, because you're just building up programmatically what the user has written. But it takes way more memory because all these structs and all these objects that you create consume so much more memory than the actual text representation. I don't know of any other representation that isn't the AST or isn't a graph-like structure. There's potentially different ways of creating a tree-based representation of it that isn't the AST, but it always resolves to some kind of graph structure, and the tree is just one kind of graph structure that we have. That's it for parsing, and you can actually look at the code for the rest of the AST nodes to see how they built up, but they built up in the exact same way, and there isn't anything really complex about them. The parsing code, if you look at parser.cpp, and there will be certainly bugs in here. Like if you give bad input, the parser probably won't handle it well. So there's always going to be bugs. But if you look at the parsing code, it's about 2,600 lines, and it's 2,600 lines of not complicated stuff. Okay, it's just quite literally parsing out each construct, and it's just all you're doing is you're just saying, okay, is a token this? Is a token that? If it is, then it has to be this. If it's not, then we expected it to be this, but we got something else, so it's incorrect, whatever you typed in. Just to show that incorrection, let's just say we have a function main, but we did that, okay? So we see here that it's the same exact thing, but instead of a open round bracket, we get an open curly bracket, and here the parser is actually a bit confused because it expects a named identifier. Now the parser is actually saying a function has to be a name followed by an open brace. So this is incorrect. There's a parsing error. Please fix. And that's all it's doing. So if we actually look at where the error is coming from, we can also debug it. Parse function declaration. Okay, and we're just going to put the debug point here. So we can see we're now parsing the function declaration. Yes, the first token is function. The second token is not an identifier followed by an open round bracket. It's an identifier followed by an open curly bracket. Okay, so probably the return type is void. And then we're going to pass the type declaration from it. But the next thing after that is not an identifier, meaning that this is not the correct thing that we expected. We got something else, and the parser is not being accurate into the error. Actually, that's reported, I realized. But that's essentially it. Like the token stream, or the series of tokens that you iterate against, has to conform to a certain structure. Otherwise, it's a parsing error. The user types something that we grammatically don't recognize. Okay, this is all okay from the edit room, and I realized that I somehow lost the clip when I should have shown you how this is debugged within the parser to actually create this AST tree. Now I've got the same program running in main.noc, and we're going to just debug through the program and see how the AST is built up and what we mean by the parser being recursive. So here I've got the debug point. The debug is already running. Let me just restart it then. And you can see that we've tokenized the entire file. So we've tokenized the main.c file, and now we're going to see how the parser is built out. So I'm going to just close this part. And we're trying to build out the AST representation, which certainly should look like this. AST function definition that has a body. The body has one statement, which is a for loop, which also has a body, and then which has the AST function call. And we're going to see how that's built. So the first thing we do is we pass the program. And let me put that here. There you go. The first thing we do is pass the program. So we create a body because a file can have many statements, and a body is just a list of statements. Ignore this hack for imports. This should not be here. And here we're just looping over the stream. So the token stream is just an index that you keep incrementing until you hit the end of the stream. We pick the token. It's not a struct. It's not type def. It's not an import, but it is a function. So now we pass the function declaration. Right. The first thing we do is check whether that's a function token, and we see that it is a function token. And now we create the AST function definition node. So this just allocates the AST function definition object, right? And now we just do some again, we're just checking that the grammar is correct at the top level declaration of the function, and that's totally fine. We're just going to ignore that. There are no parameters, so there's nothing to do here. The function does throw because we see the throws token. And every time we read a token, we're just moving the index forward. And now we do pass function body. So now we've opened this one up. So here, this pass function body returns us an AST body, which is just a list of nodes. So once we pass a function body, what is the empty body? It's not an empty body, as we can see. So here now we allocate again. Oh, I've just completely screwed that up. Let me just run the debugger again and jump back to where it is. There you are. Now we're in function pass function body, and now we're going to pass the statements. So we're going to figure out all of these things within inside the function body. Pass statements creates a body, so it allocates an AST body. So right now we've allocated the AST function definition. Now we've allocated the AST body, right? And again, we do the same thing. While we can read from this token, we're going to actually read. We're going to figure out the first token. It's not a yield. It's not a defer. It's not a tuple. It's not a throw. It's not a function. It's not a try. It is a for loop. So now we're going to pass the for loop. And you can see that the first token has to be a for. We're going to read that token. We're going to check the grammar of the rest. So here we're saying, oh, if it starts with an immediate brace, then this must be an infinite for loop. And now we're going to pass the statements of the for loop body. So this is now going to return a body. So now we're going to pass those statements. Okay. And again, we create another body. So now we're here. So we've created the function definition, created the body. Now we've created the AST for loop, and now we've created the body for that for loop. And now we're going to pass that body, right? And you can see here that it's actually recursive, because if you look at the call stack, pass statements is called, which then calls pass for loop. So pass function is called, which calls pass statements, which calls pass for loop, which calls pass statements. So it recurses on itself. But we're doing the exact same thing. We're trying to figure out what is inside this function's body. Is the first thing a yield? No. Is it a defer? No. Is it a tuple? No. Is it any of the keywords? Basically, that's what we're saying. But you can see that it's not a keyword for anything. It's just an identifier. So the first thing that we say, okay, we can't find a keyword associated with it. We try passing some stuff that we can figure out. If it's not one of the keywords, it could be one of these things. Is it an assignment? No, it's not an assignment. Is it a function call? Let's see. A function call is an identifier token followed by an open round bracket. So that's what we're saying. Okay, if it's an identifier, is the next token after it an open round bracket? If it is, then it is a function call. That's the grammar of a function call. It's a function call. So now we're going to pass that function call. We're going to allocate, again, we're going to pass over it. It has to start with the identifier. Then we allocate the function call, and then we fill up all the information for that function call. I'm just going to skip over this stuff because now we're just passing over the function arguments. But I'm just going to just jump over that, because again, the parsing code gets really long. And now we're actually finally returning. So we add the statement to the body of the body of the for loop. So here, we're now adding this function call to the body of the for loop. And now we're going to return from that. And now we're totally back up. We're going to now return that body. And you can see now we're in the for loop, and now we can add that body to the for loop by creating the infinite for loop. So the infinite for loop just creates a AST for loop node with the conditional being an infinite conditional. True node, true equals true is basically the conditional. Basically, we're just adding the conditional inside here, inside the AST, like the invisible conditional that you can't see. So now that just allocates the for loop. We're just going to return that for loop. This for loop then gets added to the body of the function definition. And then once we continue from that, we read the next thing, we return that body. And now we're at the function definition. As you can see, we're unwinding the call stack. And now the body is not null, so everything was okay. The rest of the grammar is correct. And now we're just going back up to the top main parsing loop. We've now returned the function definition. And now this function definition, we're going to add it to the main body of statements in the file. And that's how we actually built it up. So now we've actually have an AST body, which is a list of statements. And the first thing is the function declaration. So we have the body, and now we have the function definition. And then with this function definition, we can actually just cast it back when we iterate over the body of the file. Then we can see it's a function definition, and then we can iterate over all its fields. See the first one's a for loop, iterate over all its body, and see the first thing is a function call. We can tree walk that. I hope that made sense. Okay, so that's step 1 done. The motivation for tokenization and parsing. We're going to put a big tick there, and I hope it makes sense. But don't worry, as we go through different stages of compilation, we're going to revisit the AST nodes. But the parsing code, we're not going to look at it again because it's incredibly simple, and we're just building up the AST structure. And what we're now going to actually do is look at code generation. So we're going to actually skip type checking entirely and look at code generation. Because really from the, once we generate the abstract syntax tree, we can actually generate the code. The type checking is just checking whether the actual program makes sense with respect to types. Like I didn't say like a string equals a number or anything like that. Let's assume that type checking is okay. We want to now focus on code generation, and a virtual stack-based instruction set is what we're actually going to look at. Okay, just quickly, we're going to look at chapter 6, which is in the documentation, code generation. So we're just skipping type checking for now, just to explain what the virtual instruction set is, and then we're going to go back to type checking, because we don't need to understand type checking right now or how types are represented in the language. It is actually much more beneficial to understand how we might execute the code directly now that we have the AST structure. How do we generate the code from the AST structure? So NoC is a virtual-based instruction set. Basically compiles down to a virtual instruction set, and from that virtual instruction set you can directly generate assembly code. And if you're familiar with compilers, you might have heard of the well, typically this is how compilers are constructed, where you generate an intermediate representation, and then from that you generate the final assembly output. LLVM is one really famous compiler project created by Chris Lantner. He used to work for Apple. He created the Mojo. Is it called Mojo or Mojo? No, not Mojo. That's a new language now. It's called Swift. Yes, he created the Swift programming language. Then ever since leaving Apple, he's then created his own company, which is called Mojo. I think it's called Mojo, where the language he's managed to create is a language that allows you to directly target the GPU and the CPU with honestly the same programming language. It's really, really fascinating, and I encourage everyone to look at it. Chris Lantner, for his PhD thesis, created LLVM, which is a compiler toolchain that gives you access to libraries, and it's a very modular way of creating compilers. You can use particular things to generate the assembly code. Now, one of the things that Chris Lantner created as part of the LLVM was the LLVM instruction set. Now, you can directly generate code for LLVM intermediate instruction set and let the LLVM generate the final assembly code. So that way you can target once and then have the backend for LLVM target to whether it's Intel or ARM or Nintendo or Motorola's instruction set or PowerPC, or I think PowerPC is Motorola's instruction set, but whichever instruction set that you want. The great thing about the virtual instruction set is you can execute it immediately. And also the really great thing is there's only a handful of instructions. I think there's about 40 instructions for the NoC based instruction set, and it was heavily influenced by the JVM instruction set. Basically, I looked at the JVM instruction set and I went, okay, that looked good. So I'm just going to copy pretty much nearly all instructions from the JVM instruction set. But JVM instruction set has way more instructions because I think those instructions are to do with optimizations around certain things, but the 40 that I just had is good enough. And it's a stack-based instruction set. We're going to go through that. Before that, I'm just going to show you how an instruction actually looks. So here's an instruction. An instruction contains an opcode, and then it contains a symbol and potentially a couple of additional arguments that we might have. So it's a fixed length instruction, but you can imagine that these arguments are actually optional. They're arguments for the instruction itself. So let's see what the instructions are. So we have some operations when we want to load an identifier. When we want to store an identifier, the symbol is going to be the string of what we want to load. When we want to load a constant, load an immediate, when we want to load a null maybe. And then we have some arithmetic operations. We want to add, subtract, multiply, divide, mod. I did not add any shifting operations because I never needed them in the language, so they are missing. But once I do need shifting operations, bitwise shifting, then I'll add them here. And we have some type conversion, so double to integer. Doubles and integers are the primitives that are supported, integer to double. And then, of course, we have the Boolean comparisons, less than or equal to. Some control flow, jump if else, a label, some function call stuff. So these are actually implicit, so these aren't real instructions. And we have call lambda, call with try catch, return from void, object creations. These are sort of the instructions that we have, and some error handling and some concurrency stuff. There's an instruction called fork, which spawns a no routine. No routines are coroutines in the literature. And these are all the instructions. So if you look at CodeGen H, you see that the opcodes are all here. And let's see how many there are. Let's see, there's 9 to 56, so about 40. So 56 minus 9, 45 minus, yeah, about 44 instructions. And some of them actually I don't need. Like here, we can remove this, but it's still here. And those are all the instructions that we have in the language. So from the AST structure, we're going to generate the opcodes that the virtual machine is going to execute. Now, before we go into that, I want to explain what we mean by stack-based instruction set. So now we're going to explain the virtual instruction set. Virtual instruction set, and we're going to explain why it's stack-based. But to explain what it is, we're just going to look at the expression 1 plus 1 and what the AST looks like, because from the AST we can actually generate code directly, and we don't really need to do any type checking. In the NoC compiler, type checking has to happen in order for the code generation to actually work. But you can actually, well, if I designed it differently, you wouldn't need to be done like this. But the code generation needs type checking because depending on a certain field, we need type information to generate the correct machine, well, the correct virtual instruction code. But for this x equals 1 plus 1, the AST structure for this one would look like the following. This will be an AST assignment. The AST assignment node has the AST identifier. The identifier is going to be X, and the assignment has a right side to it. So if you look at the code, the right side, and the right side is going to be an AST arithmetic expression. So like we're handwriting the AST arithmetic expression. I'm not going to write the whole thing out. My pen's also not working properly. Arithmetic expression, and an AST arithmetic expression has the operation, which is plus, and it has a left and right side. So left, right. And the left is going to be a literal, AST literal, and the literal is 1. And also the right is going to be another AST literal, and the literal is going to be 1. Now, here's the abstract syntax tree that represents this piece of code. And how would we actually generate the instructions for this particular node in our program? The way we just do that is we just traverse the tree and we generate the instructions for its children before we do for the parent. So for the AST assignment, we first generate the code for the right side, and for the right side we generate the code for any children that the right side might have. So for the AST arithmetic, we generate code for the left side, the right side, and then we generate code for the parent, and then we keep doing that for that. But how? First, I'm just going to generate the actual code before explaining it, because that might be a bit simpler to do. Now, x equals 1 plus 1. This is the code that's going to be generated for it. Now, why do we call it a stack-based instruction set? Because there is a stack of, well, we're going to call it a stack of operands, but this could be a stack of values. It's called a stack-based instruction set because depending on the it's called a stack-based instruction set because the instructions operate on the stack. We either take values off from the stack or we push values onto the stack. Depending on the instruction, we might push multiple values onto the stack or we might pop off multiple values onto the stack. And the instruction implies how many values we push or pop from the stack. That's why earlier in the documentation, you might see a push arg and a pop arg. These are implicit instructions, meaning that the instruction determines how many values we push and pull. So the first instruction, we're just going to name them like that, 2, 3, 3, 4. So the first instruction is a load. So a load, we're going to load 1, and we're going to push that onto the stack. And then we're going to load another one. We're going to put 1 onto the stack as well. Add is an instruction that implies that we need to pop 2 elements off the stack, and then we need to push the value after adding them. We're going to push that onto the stack. Let me just get the eraser. So add is now going to push, so it's going to pull or pop, that's the actual word. It's going to pop multiple values off from the stack, only 2, because an arithmetic add needs 2 operands, the left side and the right side of the add. And then we're going to push the result back onto the stack. Now 1 + 1 = 2. And then we're going to push that. And then we actually need to store it in X. What store is another instruction. Store again is just going to pop off whatever's on top of the stack. And then we're going to store it in X. And we're going to see how storage is done later. But we're going to store X as a local variable. And we're going to store whatever we have on top of the stack. And we're just going to pop off 2. So we're going to pop off 2 and store X. And then have X equals 2. And this is why we use a stack-based virtual instruction set, because it's incredibly easy to generate code for, and it naturally allows you to resolve expressions. Depending on the node, we either push, so depending on the AST node, we generate particular instructions. Depending on the instruction, we either push or pop from the operand stack. And that's really why we call it a stack-based virtual instruction set, because it's stack-based, meaning that the virtual instruction would make no sense if there was no stack. Now, in a real CPU, real assembly code, and the CPU has a bunch of registers inside it, R1, R2, and depending on the instruction set, there might be a dozen registers that you load values into it, and then you can actually run the correct operation by reading correct values off from the registers. This is how a real instruction set would work. So instead of saying load 1, you might move the number 1 into register R1, move number 2, so move number 1 again into register R2, then add R1 and R2, and then store it in R3. And then you eventually push it out to memory. And that's how it would work in a real assembly instruction set. You can just directly write it to memory, but in doing so, you generate a lot of memory traffic. I mean, it's a lot slower to do that than it is to actually utilize the registers, because that's what they're for, because they're inside the CPU. It's just a small little cache inside the CPU that allows you to do operations really, really quickly, because you load them into these really fast registers, and then you operate on those registers. But if you did not want to use them, you could imagine just this entire thing would just be loading into R1 and then pushing out into memory, then loading into R1 again and then pushing out into memory. Then we read whatever we have by directly reading from memory. I don't see any reason why that can't be supported. It's just going to be incredibly, incredibly slow compared to a register-based instruction set. But this is a stack-based one. And that's what makes it really, really easy to generate code for. Another example of it, because okay, so here's the program, y = 2 + 2, x = 2 + 2, and then t = y + x, and we can see these are the instructions that's generated from it. I've just copied it into a Miro, but Miro thinks for some reason it needs to be an Excel table and not text. I'm not sure why, but regardless, so we're just going to now look at the stack and draw out everything that has to happen from that particular program. So we can see we load the constant 5, which is 2, and load the constant 6, which is 6, and then we add them, and we push that value onto the stack, and then we store it, which is just going to pop the value off from the stack and store it in Y. We're going to look at how storage works later, but just assume somewhere that it's going to be stored. Basically, storage is just a map of the text to the actual to the value. So when we store y, we're just storing it into a map. Again, we do the same thing for this, x equals 2 plus 2. You can see here that we load the constant 7, load the constant 8. The 7 is not the number, it's just the index into the constants array, which is 2 and 2. You can see that, well, shouldn't it be the same index because it's the same number, and there's no optimization for that. Even if it's the same number, there's also going to be a different index into that constants pool or constants array. But we do the same thing here, is we load the constant for 2, load the constant for 2, and push 2 onto the stack, push 2 onto the stack, adds, pops 2 off the stack, and then we store it. And then we now do t. And now for t is x plus y. So what we want to do is we want to load whatever's in y, we load whatever's in x, then we add them, and add just pops off 2 things from the stack. So when we load something, we push it onto the stack, we push that onto the stack, we add them, we pop 2 things off, and then we store it back in t. And this is what a stack-based instruction set allows you to do. Really easily evaluate expressions, and really easily you can generate code for it, but just by traversing the tree. We're going to look at how this piece of code is generated, but before I want to show you how that piece of code is generated, we're just going to step through the virtual machine to see how this code is actually executed. Okay, now we're going to see how the virtual machine actually executes these instructions. It's okay if you don't understand the internals right now. I just want to show you the hot loop that we do to actually execute these instructions. It's very, it's almost similar word for word with what I explained in Maro and in the diagrams. But this 2 plus 2 creates this stack-based instruction stream. And then now we're going to iterate over this instruction stream and execute the code. So initially we have the opcode load const. We're going to load the constant from some constants array. So you can see that arg1, which is an optional argument in an instruction, which is 5. So we're going to load the constant from index 5. And the constant is an integer constant. And we're going to push that onto the stack. So push up around, we're going to push it onto the stack. Then we're going to increment the instruction pointer to point now to the next instruction. Okay. And now we're going to go to the next instruction. So this is the hot loop. It's just while there are more instructions, we want to execute those instructions. And it's a huge case of instructions that we want to have. It's all 46 instructions that are here. And that is basically the virtual machine. We just loop through while the instruction is valid. We get the instruction, so we fetch the instruction. We decode the instruction, and then we execute the instruction. And this is what a virtual machine is why it's called a virtual machine, because it emulates what would happen inside an actual physical CPU with the fetch, decode, execute cycle. You fetch an instruction, you decode, you figure out what that instruction is, and then you execute that instruction, and then you do the fetch whole cycle again. And now we're on to the next instruction. The next instruction is going to be a load const. So we're going to fetch that instruction from the instruction pointer. We're going to decode that instruction. It's a constant, right? And we're going to push that onto the operand. So we're going to push 2 onto the operand. Now we're going to fetch the next instruction, which is add. We're going to decode that instruction, which you see it's any one of these, add, subtract, multiply, divide, all work the same way. So we're going to pop 2 things from the stack, and then we're going to resolve the arithmetic expression. Now, they all work by popping 2 things off the stack. We're going to get the result. Now, if you actually look at result arithmetic, we're going to see what it is. I'm just going to skip over this piece of code. So the result, if it's an add, we're just going to get the second operand and add it to the first operand, and that would be the result. And then we push it, we create the result object for that. So I'm just going to step out of this code. That's the result of that. Then we're going to push that operand, and then we're going to increment the IP. And then we're going to keep doing that until we hit the end. So now we're in the next instruction, which is a store. So for store, we pop the operand, so we popped whatever we evaluated, and then we store it in some storage location. Now, I said it in the explanation, it's just a map, and you can see that the storage is just a map of the identifier also, which is this identifier, to the actual result object. We'll go into what is an OC runtime object container, but it's the object that's going to hold the value of that. So now we store the symbol, we increment the IP, And then we're almost at the end of the instruction stream for main. You can ignore load null, that's something that I need to remove. And then we return from void, because it's a return, there's no other instructions. We return from void, and that's it. Now you can see that we dropped out of the while loop because there's no more instructions left, because there's no more instructions to execute. So we dropped out the while loop, and that's the end. So this is a no CVM, and all it's doing is while. All it's doing is just running it's just looping around the instruction stream and executing that instruction. Okay, so we quickly looked at how the virtual machine, how it iterates across the instruction stream, and then it executes those instructions. It's a fetch, decode, execute cycle of all 45 instructions that are in the instruction stream. What I actually now want to show you quickly before we look at the next thing, which is just tree walking, is the idea of no C threads. So I don't want to do that. Okay, we just seen quickly how the VM executes those instructions. We said that the stack-based virtual machine is really useful because it allows us to really intuitively execute expression statements and pretty much anything. We just load things onto the stack, and then we pop things onto the stack, we evaluate expressions, and we push it back. That's basically what a computer does anyway. At the end of the day, you're either moving things, or you're transforming things, or you're doing a multiply operation. That's basically it. And the stack-based virtual machine lets us do that. And we've seen how the virtual machine just iterates over the instruction stream and decodes each instruction and then executes that. So we've seen that in the code. It was a while loop. While the instruction is valid, IP is valid, fetch, decode, so figure out what instruction it is, and then execute. Execute. This is basically the hot loop for the VM. What I now want to quickly explain to you, and I won't go in too much depth into this, is where are these instructions kept? I mean, what object do they belong to? And this is an introduction to no C threads or virtual threads. Now, no C threads or virtual threads. Virtual threads. Now, a no C thread, right now, I'm just going to say it includes three things. It includes the instruction pointer that we're currently executing. So which instruction are we currently executing? It has the stack of operands that we need. And also it has the instruction stream, like the virtual instruction that we generate. It has a reference to that because it needs to read the instructions from this stream. So we're just going to call them instruction stream. And an OC thread, we're just going to look at the actual code. We're going to ignore that. We can see that it has the instruction pointer, it has the stack of operands, and it has the instruction stream, as well as a bunch of other stuff that we'll get into much later. And also has the thread ID that we can explain quite easily right now. And it has those things. And inside the VM, all we do is when we run a thread or run an OC thread, all we're doing is we're fetching the current instruction pointer from that thread, and then we're getting the instruction that points to from the instruction stream, and then we're decoding it, and then we're iterating it again and again. And we do this fetch, decode, execute cycle for that no-C thread. It is the same thing as what's happening inside a physical CPU. It's just, we're just virtualizing it right now. And the virtualization is quite good because it allows us to have a good representation of what the CPU is actually doing. So when we do generate direct code, we know what the CPU needs to do because it's what the virtual machine will do. And we need to make sure what we're emulating is what we produce, what the final CPU will do. But the emulation or the virtual machine gives us a really good intuition in how to do with them. And there's also great things that you can do with virtual machines that would be much more difficult to do with direct code generation. So one great thing with virtual threading or virtual machines, not virtual threading, virtual machines, is you can imagine that you can just suspend the program really, really easily and then connect it to a debugger. This is something that we get into much, much later, but there are things that are much easier to do with a virtual machine than it is to do with direct code generation. And also it's so much easier to test with the virtual machine instead of actually doing direct code generation, because you can just debug it and step through your code. It's much more difficult to do that if you're actually generating direct code for the CPU. But it gives you a very good intuition in how to think, in how things work inside a CPU by understanding how the virtual machine actually works. And that is one more thing that I would like to show is this, with this x equals 1 plus 1, we're now just going to see how the code generation walks this tree to generate code for this. And this is our introduction into tree walking, which is absolutely nothing complicated. I mean, the tree walking, which is basically given a node, we want to visit its children, and if that node has children, we want to visit its children, and then generate the code for a node that has no children. And that's essentially how we generate code from. I believe it's a pre-order search where we actually visit the children first before we visit the parent, and we generate code for the leaf nodes, the bottom nodes, before we generate code from the parent. So you can see here that the store is the actual first node. It's an AST assignment, but we generate the code last, whereas the literal one is the last node, but we generate the code for that first. So we go deep as we can. We generate the code for the children, then we generate the code for the parent. I'm just going to quickly show how that code is generated. It'll give you a really precise understanding of how tree walking is done, and it also introduces us to how we can manipulate or program against the AST, because the AST is a representation of the text, and now we can generate code for it. Okay, now we're going to explain how the code is generated from an AST assignment. All we have to do with generating code for a particular node in our tree, for example, this is an AST assignment node, is we just walk the tree down and we find the first node in the tree that has no leaves associated with it. I'm going to stick away from comparing it to children where you have a leaf node, because you can end up saying quite ridiculous things. So we keep walking the tree down until we find a leaf node. A leaf node is a node that has no leaves associated with it. So here we have the AST assignment. It has two, the identifier itself and then the right side. And then from the right side has the arithmetic expression, which also has a bunch of leaves associated with it, left and right. And then we keep walking down the tree until we hit a leaf node that has no more other leaves. It's a branch with no more branches, you could say. Again, I'm trying to stick away from the child metaphor, because that sounds so silly when you actually say, oh, this node has this many children, and then the child is terminal or something. It just sounds so inappropriate. And that's how we're going to generate code for. And remember, the code for this x equals +1 or y equals 2 + 2, as we see here, is contained inside an AST function definition. And here I got the debugger loaded up for that particular function definition. So here is the main function, and we're going to generate code for this main function. Now, the main function is we're going to jump all over this stuff. All over this stuff, and we're going to see that the first thing that the function has, remember the AST function. I'm going to open up ASTH. AST function definition has body, and a body is just a list of statements. We're just going to loop over those statements. Again, we're walking the tree. We're going to loop over those statements and then generate code for each statement or each node within the function definition. And we see the first thing that we're going to generate code for is going to be the AST assignment and assignment. We're going to put the debugger here so I don't have to walk through. So now we eventually we've walked down the tree to find this AST assignment node, and now we're going to generate code for that. In order to generate code for it, we're going to first generate code for its right side, for its I'm going to go back to the children metaphor, for its own children, before we can generate code for the parent. And what is the child? So the child, we're just going to figure out what node it is. And these else if statements can be just changed to a switch, but they actually demonstrate the walking of the tree quite nicely with the debugger. We're just trying to figure out what node type is that child. And now from my row, we can see that it is the right side is going to be an arithmetic expression. So we're just trying to figure out where that is within this massive chain. And can you see each node has a particular way we generate code for, but it's really the same kind of structures. We just find the node, then we recurse up its children before generating the code for its parent. And the reason why we generate code for its children is because we're creating a stack-based virtual instruction set. So can you see that the first instruction is load 1, but that's the last node in this tree. And you can see store X is the last instruction, but the assignment is the first node in the tree. And in order to do that, that's why we have to do it in this way, because it's a stack-based instruction set. We're doing that traversal. I believe that traversal is pre-order, where you visit the children before you visit the parent. Yeah, we're just going to find out the arithmetic expression. There's so many different ones that we want to generate code for. And eventually we find the arithmetic expression. Now, all we do here is I'm going to generate, who cares about that, is we generate the code for the AST literal here, and this function is doing that. And then we look at the opcode. If it's an add, we then generate an add. And then we walk back up. So you can see that from the call stack, you can see that we've recursed quite heavily. And now we're on the assignment. And now because we've generated the code for its children, which is this part, we can now actually do the storage. Now, ignore this type order code. It's actually just needed to do type conversion if there is anything that needs, for example, if the right hand side is a double, then this needs to be converted into a double, because implicitly if you don't give a type to something, then implicitly the arithmetic expression is always going to resolve to an integer. But this is saying, oh, if the user put in a type, do we need to convert it? And now we generate the store, and the store is pretty much the same thing. We just emit the store instruction, and we put in the symbol for that. So the symbol is Y, because the main program, main.noc, is Y. And that is, in essence, how we actually walk the tree to generate code for. And that's how it works for the stack-based instruction set. We walk the tree, we generate code for the leaves of that tree, then we walk back up, and then we generate code for the parent. And that's where you see the store X. And we keep doing that until we run out of things we need to iterate on, because a function has many, many statements. For each statement in that function, we generate code for that statement. And that's it. That's how the stack-based virtual instruction set works. There are many instructions that you can look at. So if you look at CodeGen H, so you can see all of these instructions. But one thing I did want to actually demonstrate is tree walking. You have the AST, you walk that tree, and you recurse into itself, and then you keep walking until you find a terminal node that you can generate code for. And then you walk back up the tree, and eventually when you hit the parent, you can generate code for the parent. And you do it like this because you are creating code that is for us, that will work on a stack-based virtual machine or stack-based instruction set, and because the stack operations are implied within the instruction. And that is all there is to it with code generation. Now there are many, many different nodes, and we're going to go back and forth between how that is represented as the AST, then how we generate code for that, and how that's type checked. But I wanted to give you an intuition in how the virtual machine works, because everything else right now is going to be dependent on us understanding tree walking and understanding this AST node structure. It's very, very simple. And depending on the node, the code can be quite complex, or it can be incredibly simple, like storing something into value of X. This is one instruction for it. But something like a lambda function resolution is actually a lot more instructions. But that's okay. For each construct that we introduce from now on, we're going to be looking at how that is represented as the AST, then how that gets type checked, and then how that gets code generated, and then how that gets executed in the VM. Just a quick overview of everything that we've covered so far, because I feel like we covered quite a lot of content as an introduction to the virtual instruction set. So let's just see. We've introduced the virtual stack-based instruction set that has about 40 opcodes. And the virtual stack-based instruction set is easy because it allows us to evaluate expressions by popping values and pushing values onto a stack. We've now seen how the virtual machine then evaluates that code with fetch, decode, execute cycle, just like in a CPU. We've introduced no-C threads, which is the object that's actually going to encapsulate all this information. The no-C threads are the core object that virtual threading is going to be based on. So the no-C thread has itself, just like the real thread that you'll find in a kernel, has the instruction pointer, has the stack, has the instruction stream. And then number 5, we just looked at tree walking to generate code. Given the AST node that we pass out from the text, how do we generate code from that? Really, really simple. We generate code for a leaf, for its leaves, and then we generate code for the parent. Depending on the node, we generate different instructions. And that's tree walking. We walk the AST tree. And then we keep walking down until we hit a terminal node, a node that has no children, and then we generate code for that specific node. Then we walk back up to its parent. By walking back up, we just let the recursion exit out, and then we just walk back up the call stack, and then we eventually hit the parent, and then we generate code for that parent. And we've seen how that works for y equals 2 plus 2. Understanding this is the basis for understanding everything else. And once you understand that, it's just so simple. And you can start to abuse heavily the virtual based instruction set. It's abused quite heavily by me to generate many different things, because there's so many different constructs in the language. Not so many, but there is quite a bit of things that the language does support. And sometimes there's an instruction code that is specifically for that construct. And that's a bit strange, but we'll get to that in a bit. So there is an abuse that happens, and the abuse makes it a bit harder for me to then directly from this virtual instruction set, virtual intermediate representation, which is stack based, to then generate direct code. Because the virtual instruction set is abused quite heavily. Like there's some things that don't even map to an instruction that you might find in a real instruction set. It just doesn't. It's a kind of an abuse of the instruction set. But we're going to go through that much later. What we're now going to look into is type checking. Again, because we now understand tree walking, we're going to see how the type checker works. Okay. Yes. So before we left off, it's dark again. But before we left off, we spoke about tree walking and how essentially we just walk the AST. Given an AST node structure, we cast it to the particular node that it represents, and then we walk its fields. So we just recursively walk downwards to a leaf node. That's essentially tree walking. Type checking, so far we've done step 1. We've explained the motivation behind tokenization and parsing. We created abstract syntax tree. We've jumped straight into code generation because we immediately want to see how code might be executed. We looked at stack-based expressions, introduction to no-C threads, and some simple code execution. Now we're going to go back to type checking. And again, type checking works with tree walking. I mean, it's the same kind of traversal mechanism that we saw in code generation. Now we're just going to do it to type check. Right? So in step 2, we've done code generation yet, so we've done step 2, and now we're going to look at type checking, and we're going to look at some examples on how they're type checked, and we're going to explain how types are represented in the language, how symbol resolution is done, and we're going to be looking at two examples for type checking at this part. Now, in the documentation, there's actually a really good visualization on tree walking for type checking, right? Let me just see if I can find. Type checking is just a tree walk. So here's an AST assignment node, and the left side of assignment is X, and it's declared as an integer, and the right side is an addition. Now, what we have to first do is we infer the type of the right hand side. We know it's a function call, and then we see what the type of the return type of the function call is. Once we get the return type of the function call, we then check if it's the same thing as the left hand side. Because they declared it as an integer, we compare whether the right hand side is equal to the left hand side. And that's essentially how type checking works. It's just a tree walk of a particular node, and then from that we infer the type. Depending on the inference, we might have to determine equality between types as well. So let's look at this example again. We just smack it right here. So here we have, let me just move on to it. So say we have x equals 1 plus 1. And this is going to be an AST. Actually, let's make a much simpler example. Actually, let's just do the same thing here. X equals add 1. We're just going to say it's add. And the function add, we're just going to say function returns an int add. Who cares what the implementation of this? It actually does nothing, takes in nothing, and just returns an integer. Now, how this would be represented as the AST is, this is going to be an AST assignment. The left side is going to be X, and the right side is going to be an AST function call, right? The reason why I'm just writing this is just so you can see the tree, and then we're just going to tree walk it. AST function call, and it has no arguments, and that's how the tree would look. So when we type check this, we first hit the AST assignment node. Okay, first we infer the type of the right hand side, so we then walk the right hand side, that we see that's a function call. We then look up the return type for this function call, and this is what type checking is essentially doing. It's just storing types for function symbols, struct types, symbols that you declare. The type checker is going to store that all in its symbol table, and then when we call certain functions, we're going to resolve it if that resolution exists. Well, we're going to look at how the symbol table works just a bit later, but for now, what I just wanted to explain is once we hit the function call, we then look it up and then we return its type, and then we compare whether the right hand side is equal to the left hand side. Because there's no type declared, NoC doesn't require you to declare a type, just like Go, and in more recent versions of Java you can just write var, but NoC doesn't require you to do that. So x would be inferred to be of type int. Now, if x was not inferred to be of type int, so if x was marked as integer equals add, then we infer the type from the right hand side. We know the type from the left hand side because the user said it's an int, and then we compare whether return types are equal. Are return types equal? That is essentially type checking. Infer one side, compare it with the left. If there's equality, shabang, that works out well. Now we're just going to look at a quick example. Okay, let's look at an example. Here we have x is declared as an integer and it equals to whatever the add function returns, and of course the add function just returns 1 and returns an integer. And the user here has declared the type integer. Of course, in NoC you can just do this, where it's just inferred. X is not inferred to be an int. Here we're saying x is an int, and it should equal to the type that's returned from the function call. We can ignore this. What this does, it just calls a breakpoint within the type checker, and that way we can actually look at the next statement immediately. It's just a really nice utility. This way I can just remove every single breakpoint, and then when this breakpoint hits, I can then attach another breakpoint to the next statement. So let's just run the debugger. And you can see type check breakpoint has been hit, so we've hit this debug break. If you want to know how this works, it just raises this signal, and then that just connects with the debugger. If there's a debugger running, it would halt the entire program. And now we can look at the next statement in this function. So we're just going to step out of this thing, and here here we're just looping, we're type checking the function body. So every single statement inside this function, we're going to be type checking. So this function is not a real function. So now we're going to be actually doing the thing that we want to type check. And that's type checking the assignment statement. So again, we're just walking the tree. Here, we're type checking this statement. It's not a match, it's not a return, it's not a defer, it's not an if statement, it's not an array subscription assignment, but it is this assignment, this AST assignment. And remember how the AST assignment looks? It has an identifier, which is the X. It potentially has a type declaration. This one does have a type declaration, and that's an integer. Then it has the right-hand side, which could be anything. So that's how an AST statement looks like. So how do we look at the type of the assignment? Let's step into that. Okay. What we first do is we infer the type of the right-hand side. If the right-hand side is a function call, it's just going to resolve the return type of that function call. We don't need to know how that works. We're just going to jump over it. And the return type returned is an integer. So int return. Now, because the user has declared it to be an integer, we type check the assignment equality because we actually need to do that. Now, what we do is we run this function if the return types are equal. If the return types are not equal, then we see whether we can do a conversion, and this typically can happen between a character and a byte. But we're not going to expand that because that code is a bit confusing. But the return type equals is the basis of type checking. Given one type and another type, can we determine the equality? So what's the type of the left-hand side? Is int return. What's the type of the right-hand side? Is an int return. And therefore, the return types are equal, and this assignment is totally correct. Let's do one more. Let's say that this is a string. Hello. So add returns a string. Now we'd expect type equality to fail. Again, I'm just going to remove all debug points because this is going to call our debugger. Here's the assignment. I'm just going to be looking for that. Here we go. And here the right side is a function call. The right side is returning a string. So we can see that the return type for this one is, well, we can't actually see, it's not labeled here, but it is a string. And the return type equality would fail because a string is not equal to an integer. I'm just going to let it play because otherwise we're going to step through so many functions. Left-hand side of the assignment is not equal to the right side. Left side is int, right side is a string. And that is type checking in the easiest way that I can explain it. We're looking at an AST node, we just walk the tree, and each node in this function body, we iterate it, we type check it, and we resolve the type. If there's a mismatch, then that would cause the error that you actually see. Left-hand side is not equal to the right-hand side. And that is what type checking is. We just walk the tree and we infer the type. If there's an explicit type declaration that the user made, then it's an error. If there is no explicit typing, for example, let's just say x equals that. Let's just run the compiler without the debugger. Oh, sorry. See, if you run the compiler and you keep this thing attached, because it's going to raise a signal, but there's no debugger attached, so it just crashed the entire program. There you go. So here you just see there's no type error because x has not been declared as anything, so it gets inferred as a string. So that the type inference is there, and that's just really nice. I think Go has this. Java previously you had to actually declare it as a string x equals add, and in more recent versions of Java you can do this. I'm not sure in Java 22 if you can just do that, but I like this syntax a lot, and it's the same as Go. There's no var keyword or anything like that. Just x equals add. If you want to declare the type, let's just declare the type as an integer. And there you go, left-hand side is not equal to the right-hand side. Because the fundamental function that actually does the type checking is are return types equal. Given one return type and another return type, are they the same? And now we're going to actually explain how types are represented in the language. Okay, how are types represented in the language? We know that I've just explained a function which is critical for the type checker. Our return types equal, which compares two types and determines if they're equal. But how are types represented in the language? What are the base types for the language? Like a base type is an integer, a boolean, a double, a character, a byte. The void is a base type, and any user-defined types, like if a user said struct person, these are base types, right? This is types that are foundation, like they can't be broken down into anything else. Like that is of a type person, that is of a type double. These are considered base types, right? And these are actually called base types in the compiler. They are base or basic. They used to be called something else, but I just decided to use the word base type. From this one, we also have many other types that are actually supported. I'm showing you some of the source code from the type checker. Here's all the different types that we have. We're just going to look at base types and array types for now, because they're the easiest to explain, and we'll introduce other types as we introduce other features into the type checker. But there's two types that we have, a base type and an array type. And an array type, of course, is of a type of an array with any number of dimensions. So this is a two-dimensional array. Person, this is a one-dimensional person array. So this is just considered an array type. The way types are represented in the NoC compiler is they have a tree hierarchy. Types as trees. The easiest way that I can actually show it is just by showing you the source code for it. So here's what a base type is. Everything extends from type, and type, just like in the AST structure, has a type of type, which tells you what the type object is. So here we have a base type, an array type. It can only be one of these things. So a base type extends from this type, and it just has the type string, and whether it's a primitive or not. And there are built into the compiler the following base types: void, integer, double, boolean, null, byte, char, and any. And all of them are primitives except any. Now, any is not something that you can use in the compiler. The compiler does not, the language does not support any types. You can't use any. Like in TypeScript, you can just say something is anything. Or in Go, I think before they added generics, you'd have to use any to cast something from one type to another, if you knew what the cast was, if you knew that cast to be safe. But these are the base types, and you can see void is also a base type. This allows us to compare if something is returning, if someone's trying to restore, like here's a void function, and this won't work because add is a void return type, but this one is an int return type. So the type equality still works fine. So there's no special thing that we have to handle void. We just declare it as a type. And these are the base types. And base types are also user-defined types, because it just has the type string. Like a struct person would also be a base type, because it's the base, it's the foundation type. An array type is just a base type followed by the number of dimensions associated with that array. And the dimensions are key, because a one-dimensional array is not the same as a two-dimensional array. Yeah, so you can see the array type has the number of dimensions associated with that, and then the base type associated with it. Now, it's considered a type tree because this type could be anything. But right now, just assume that it's just going to be a base type, just to make the examples clear. But this type actually could be a polymorphic type. It could be a lambda type. So having this hierarchy where everything extends from everything allows us to stuff anything in here into the type tree. It's just like the AST. It's the same kind of thing. So when we build up the type, all we really are doing, once we have one type compared to another type, is we just compare the tree structure that's associated with it. So here's let's just say we have an int, and let's just say we have a int array. So here, this thing would be a base type. Once we make the object, this would be a base type. The type string would be an int. Here, this would be an array type. The base type for this array type would be integer. The number of dimensions is going to be 2, so 2 dimensions. Okay, let's create one-dimensional object. Again, the same thing. It's an array type, but the number of dimensions is 1, and the base type is int. So although the base types are the same, the dimensions are not the same. So it's not considered equal. Now, let's just actually draw it as a graph. So we have an array type. What's the base type? The base type is an int. What's the base type of this one? It's also an int. What's the number of dimensions? 1. What's the number of dimensions here? 2. So when we compare two types, all we're doing is we first compare that the type of type is actually the same. Because if this is an array type and this is a base type, then for sure these things aren't equal. Then we compare the number of dimensions. If the number of dimensions are the same, that's great. And then we check the base type of each. We check the base type of each array, and we keep doing this, and we keep expanding the tree. Okay, let's write an example here where we have, let's just zoom in here. We have x equals new int, and we're just going to have a one-dimensional array. Y equals new int. Y equals new int, and we're going to have a two-dimensional array of length 1. And then we're going to say y equals x. We're just going to reassign y to be x. But this should fail because these two types aren't the same. Although they are of the same array type, the number of dimensions is completely different. So this kind of equality should fail. Now, the way the types would be represented, this would be an array type with 2 dimensions, so dim is 2, and its base type would be integer. The same thing for this one as well. It's also considered an array type. And dimensions are 1, and its base type is also integer. So although the base type is the same for both, the number of dimensions is different. So let's look at how that works within the type checker. Okay, again, we're just gonna call this function. So the breakpoint is going to be here after the type checker does all of this stuff. So let's just run the debugger so we can see that the type checker breakpoint is here. So now I'm going to put a debug on is return types equals, because these two, this assignment would trigger this function to be called, and that's the basis of type equality. This function being called is called everywhere. So first we compare the left-hand side type to the right-hand side. The left-hand side type is an array type, and the right-hand side type is also an array type. So the type of type for both things is the same. So at least we know at this point the two graphs could be the same. Now, let me just go on. Now we do the type comparison for the array type. We cast both types, the left-hand side and the right-hand side, to be array types. Now we compare the number of dimensions. The number of dimensions is 1 here, the number of dimensions is 2 here. So this is false. It just returns the return types are not equal. And that's what we get. The symbol has been redeclared with a different type. X used to be an integer of dimension 1, and now it's been declared to be an integer of dimension 2. And now let's say the dimensions are the same, but let's make a string array and do the same thing here. Okay, so I'm just going to remove all the breakpoints, and again, just run the debugger. The debugger is called. So let me just open up main.noc here. Our return types equals. So let's see what happens here. We can see here that the return type for the left-hand side is an array type, and the return type for the right-hand side is also an array type. So again, this is the same thing, works really well. So we just go into the array type equality check. The dimensions are the same, so that's good. But is the base type the same? Okay, now we're going to recursively call back into itself. Again, because it's a tree, we can recursively do this. But we're going to be looking at the base type. So if you look at the array type comparison, what we pass in for equality checking is this base type. We're now going to check, okay, so the dimensions were correct. Is the base type the same? Now let's look at the base type. They're both of a base type. So string and an integer is, did I put an integer here? They're all considered base types. Now all we do is we just take the type string. Okay, this is a string and this is an integer. Okay, these strings are not equal. So the type is not the same and we get the same error. And that is how type equality is done. The reason why we represent them as trees is so we can get a natural recursion of them, because we can build up more and more complex type trees. We've only looked at two, which is the base type and the array type, but when I showed you in the source code, there was about 6 different types, and these actually nest to create more and more complex types. But that is the basis for type equality. The other complex types just recurse differently, and the type tree just looks different, but the fundamental equality is the same. We are comparing two type graphs that we get. Now, we've seen how types are represented, but how do we go from the AST to then generate a type? It's almost the same thing as we did, is how we went from text to tokens to the AST. Now we're going from the AST definitions that we find to generating types from those AST definitions. And once we have those type definitions, we can actually store them in the type table, which is tracking all the types that the compiler has seen. And this is called the symbol table. The symbol table is a table, it's a map of all user declared symbols that are seen during compilation. So anything that the user defines, anything that the compiler also defines is part of the type table. Like the base types, those are symbols that are part of the type checker, and they're part of the symbol table. And it's not something that the user can define. You can't define what an int is. And the symbol table keeps track of all this information and resolves any discrepancies that might be in the program. One final thing I want to talk about just before I conclude is just introduction to the lambda type. It's just going to consolidate what I mean by type hierarchies and type trees. So here's a test function that takes in a void function. So any function that has this signature is allowed to be put inside here. And so foo has this signature. It takes in nothing and it returns void. So here test, we're passing foo, and you can see that the function will be called here. Again, higher order functions. So when we run the compiler, we see test and foo is being called. So test and then foo is being called. This is the foo function. Now, how is this represented? Each function has its own lambda type. A lambda type is just the function signature, the return type and the arguments. When we compare two different lambda types, we're just doing this equality check. We're checking the return type, and for each argument, we check the types of those arguments. So if you run the debugger, I already have it run on the equality check for lambdas. And I hope this runs quickly. Sometimes the debugger takes a really long time to start. It should start really quickly now. So here you see, when we're doing the lambda type comparison, we check whether the return types are equal. The return types are both void. The foo return type and this type definition return type is both void. Let me see if I can remove that. So those two things match. And the number of arguments are 0. So those both things match. So we are allowed to pass this function. If we changed it into this function returns a string, and then we ran the compiler, types does not match in one of the arguments. So here, foo does not match the type definition that we have here. The lambda types don't match. Each function, we build a lambda type for every function that we have. This just allows us to pass in functions to other functions. And yeah, this what makes type checking higher order functions. This is how we support it. The next thing I want to talk about is a symbol table, and it's a key data structure within inside type checking. A symbol table is just a map, quite literally a map data structure between identifiers to the symbol resolution. So the symbol just refers to some object within inside the type checker that represents that information associated with that symbol. So when we do x equals new person, we look up whether that person exists inside the symbol table, and we get all the fields related to that person, and then we do type checking based off that information. So a symbol table is just that. It's just a map. Where is it? there you go, yeah. A symbol table is just a map between some name and then the representation of that object. And that mapping will contain type information and everything associated with that. So as an example, let's say the user defined a struct person. We're going to iterate over all the struct definitions within this file and then create symbols for these struct definitions. So here we have the debugger broken right here. So we're going to hit the debugger. And remember, we're going from AST nodes, we're traversing across the AST nodes. One of those AST nodes is a struct definition. And we can see this is represented with this AST node. We see a bunch of poly headers. This is for polymorphism or generics, the name of the struct and the members that contains. So you can see that this representation maps to this AST node structure. Now, I'm going to skip over some built-in and here. Now we're going to come to the user-defined one, which is, you can see that this is person. The name of this struct is person. You can see that it just maps to this AST node. From this AST node, we're actually going to generate a type from this. So here, we're going to jump here. We're going to create a type from this. So the type is a base type, and the base type's name is person. So this is how we create a new type. Once you create a new type, we're going to add it to the symbol table. And the symbol table is just names to concrete types, names to concrete symbols. And once someone actually creates an object of this or refers to this, we refer to the symbol table, we refer to the map of all symbols, and then we retrieve that information, and then we type check against it, whether it exists or whether it doesn't. Now, just to give you a good example of this, let's say we have function main. Let's say someone tries to allocate a new person. This will work fine because the person type actually exists, because the struct definition exists. So this is going to be no problem for us. So when we run the compiler, that's totally fine. Let's say we have a new foo. Well, because there's no struct definition for this, there's no base type that we've created. So this is what this is saying, although it's quite a confusing error message. But base type could not be found for non-poly member. This is a horrible error message, but I understand what it means. It just means that when we allocated this object, we could not find the base type associated with it. So initially, of course, a struct needs to be created for that type. And from that struct definition, we then add it to the symbol. And the symbol table, there's many tables that are associated with it. There's a function symbol table, a struct symbol table, enum symbol tables, and a global symbol table. Each symbol has different information associated with it, the name of that symbol, the return type, some scoping info. And this is something that's also used to allow us to be more granular about what context the symbol is being defined in, whether it's a struct, a function definition. But essentially all it is it's just a map. So if you go here, map, sorry, let me just go here, equals new map. Can you see all these maps? When we create the symbol table, we're just creating a bunch of maps that are going to be holding that pieces of information. We take the map from the struct definitions and we create concrete symbols from that. So when we do refer to it, we just look it up, and if it exists, then the type check is fine. If it doesn't exist, then there's an error. Now, if I create it twice, then that also is an error because the same symbol can't exist twice within the symbol table. The struct type is already declared. Now, NoC does not support namespaces, so I wish I kind of added it, because that means I can only have one name type for any object that I want. So it's kind of annoying once your code gets quite big, and you can't define something else called connection or something else called person because it's already been defined in the code base. But it's okay. It doesn't really bother me too much as I was writing out programs. Okay, so in the symbol table, we see a function symbol table, which is a mapping between names and the actual function objects that the type checker represents. And you can just see that this is what a function symbol looks like. It has all of this information about the function. We just take it from the AST. So we get from the AST representation to the representation that's a concrete type checked object that the type checker would use to do type checking whenever that function is referred to. Now, I won't go too deep into the source code because there's not really a point to doing that. So here we can see once we find an AST node that's a function definition, so we find it here. So this is a built-in function called toNativeString. I think this is a bad example. We'll do another one. Length of string. So this is from string.noc, not string.h, string.noc, and length of string, which is this function. As you can see, string is actually written inside its own inside the language itself. So the length of string, which is that, and this is the AST function definition for this is represented here. So this is from this piece of text, we create this AST function definition. From that AST function definition, we then create the function symbol associated with that. And from the function symbol, we just pluck out all the information from the AST and verify that that is correct. So if someone declares a type here, foo, that is also a type check. So the function symbol is a type checked representation of the AST. And that is what's referred to when anyone makes a call to that particular function. If we can resolve it, we find the function symbol associated with it, and then we take all the information out from the function symbol. And depending on the context, we use particular pieces of information to do the type checking. For example, if someone calls a function with the incorrect number of args, we just check whether the args that were passed are the correct size. So this just gets a concrete object from the AST. And that's all function symbol is, and then we just add it to the symbol table at the end. So I hope that sort of symbol table made sense, because there's no point really going deeper into that, because it's just a map, and there's several symbol tables that are there, and you can add as many as you want depending on how granular you want to be, but there's many different tables for many different things. I kind of wish, looking back at the code, that I only had one table for pretty much everything, and that's probably what I should have used. But essentially there's two classes of tables inside the type checker. There's a symbol table for function symbols and enum symbols and struct symbols, and there's another table for global symbols, which the type checker should have unified them and created them all under one single table. But over time, this is the way it kind of evolved. And that's why I don't want to go too deep into it, because the code is quite confusing as we do symbol table resolution. But it should be particularly simple, so because it's just a map and a key lookup for that. The two things that I want to look at right now, two examples, is if statement type checking and function call type checking. This is going to give us, again, we're going to look at how the tree is walked, and also how symbols are resolved from the symbol table to then do more type checking with that. To explain the final thing with symbol tables, we're just going to look at how a function call is type checked. Now, this AST function from we just previously looked at, is made into a function symbol that contains all the information that's type checked about this function. The name, the return types, all of this is type checked and then put into a table that contains all of this information. When we do type checking and a function call is made, as we're doing the tree walk of all of these statements inside, once we see a function call, we actually look up inside the symbol table for this function, and then we type check each argument that's provided. So here you can see that there is an error, because it's expected to be of type int for the second argument, but I'm providing a string. And we're just going to see how that looks right now. So let me just get rid of all this debug points. You can see I've collapsed the function substantially, just because there's so many things that are done when we type check a function call. Depending on the arguments that's passed, there's so many things that you need to consider. So the type checker does become complicated in that sense. The more syntax that you have and the more AST nodes that you have, the more that you actually need to do to make sure type checking is correct. But the core mechanism is we look up the function symbol and we check whether the arguments supplied are correct. If they are, then that's good. So here we're just going to run the debugger. It's going to breakpoint right here, and then we're going to go to the next function. So I'm just going to scroll out of this one, and then we're going to hit now into this AST function body. We're going to go to the next statement, and then we're going to type check this next statement. So again, from the AST, you can see the function definition has a body, and we're just iterating over that body. So you can see the body, the statements, we're just iterating over that. We're tree walking. So here we now land into the function call because that's what the node type is. And we can see that the function call here, the AST node, has foo, has all the arguments that are for the function call. So AST function call. So you can see all the arguments that are here. They could be of any node. So here, let's just go back to main.noc. We're just jumping over it. We're just going to jump over all of this stuff until we get to here. And this is where we look up whether we can actually find a function symbol with this name. We can find a function symbol with this name. And if we can't, then we emit an error. Now, all we have to do now is, given the function call arguments, is it the same as what we expect from the function symbol? If it's not, then the number of args passed is incorrect. If they are the same, then we just loop over what the user has passed and we infer the type of each argument that they supplied, and then we check it with what's expected. So you can see here, for each argument that they provided, we're going to infer the type of each argument and then check it against what we expect from that function symbol. Now again, just to emphasize tree walking again, I'm just going to step into this, and here the node for this is an AST literal node. So again, we're just going to go down again, we're just going to recurse, then we're going to land into an AST literal. It should be an AST literal. So there we can see. What is the literal value for this? It's a number, so we're just going to return an int. And this is what the type checker does. It just recurses down to at least a leaf node that we can infer its type immediately because it's a literal, or it's some identifier that we have to look up in the symbol table to resolve that. But in this particular case, it's just a literal, so we return. We're just going to return all the way back up. And now we're back here into the type checking for the arguments. We ignore all of this stuff, and now we just check whether the expected type is what is passed from the argument. Now, these two match, so this is no problem at all. So we now go to the next argument that's supplied. Again, we do the same thing. We infer the type of that expression. We recurse down again. We just walk that node. We see that that node is indeed a literal. But what kind of literal is it? It's not a number literal. It's a string literal. We ignore all of that stuff. We just get the type of string. And then again, we just walk back up. By walking back up, I mean we're just returning, and now we're back again into the loop of function arguments. So the argument return type is a string type. The argument that we expect, we can see right here, is an int return. So those things don't match. And once we press play, we get main.noc, the arguments don't match. And that hopefully demonstrates a couple things. Tree walking resolution, how we actually just walk the AST nodes, how we use a symbol table from the AST nodes, how we create symbols, and then how we actually resolve the symbols. We just look into a map, and then how we resolve the type checking for a function called. Now, type checking can become quite complicated, not in terms of the algorithmic complexity. It's actually incredibly simple. What becomes complicated is the more AST nodes that you have, the more considerations you have to make when you actually resolve something. So right here, I've actually collapsed a lot of those things because anonymous functions is something that's actually supported within the language. So the argument pass can be an anonymous function. Depending on whether it's an anonymous function, we need to do something else. Now, if the function itself has polymorphic arguments, we need to do something there as well. So depending on the complexity of your language, your type checker will be more and more complex. Something like, what's the language? ML, yes, something like ML, where it has type inference for everything. That type checker, you'd imagine to be incredibly complicated. But we can see here that there's so many different things that can actually be passed to a function. And if I miss a certain case, it could be quite catastrophic in terms of the code generated. It might be entirely incorrect, or something will crash within the type checker. So that's the only difficult thing about type checking. Type checking itself is 3,000 lines, so there's just so many things that you might want to type check. Not because there's algorithmic complexity, it's just there's just so many cases that you want to handle when you actually do it. One final thing I want to talk about in step 3 of the type checker, before we move on to generics and polymorphism, I think that might be the next part, is how structs are represented within the type checker. And this is to do with the layout of the struct. Now, if you're familiar with Java, if you use the reflection APIs, sometimes you see something called like get field of an object. But really, when you create a struct, every member is a field of that struct. So int member in member 2. And what the type checker is going to do is going to create a layout object that represents the layout of this struct. The layout is just all the fields that are contained in there and the order of where the fields are. And if you use the Java reflection API, sometimes you can do like type of person, and then you get given some object back, and then you can iterate over the fields. Really, this is the mechanism behind it. The compiler is going to generate the layout representation of this struct. Now, whereas this is just an AST node, we generate a symbol for this AST node, but we also need to generate other pieces of information. One of those being the layout. What are all the fields inside a struct? Now, to do this, we just take the AST after type checking it. By type checking it, I mean making sure each member is correct and actually resolved to some type. We create a struct layout object for this. And the struct layout just has a list or vector of fields. And a field is just the name. Field is just a name, the name of that field, and then the type of that field. And we're just going to use the type object that we already have. And that is all there is to it. And we're just going to look at the code to see how that actually looks. So if we look at the type checker, and we look at struct layout, when we look at the AST node for a struct, we actually grab all of these pieces of information. So we see we have the vector of fields, and a field is just the name and the return type. The memory offset is something that we need in order to actually resolve this object or create this object at runtime. When we access a certain field, we need to know which memory offset that's in. So if it's the 4th field, then it will be in offset 4, we could say, because it's the 4th field that you want to access of the object. And this is what the struct layout represents. It's just the layout of the struct. Again, this is the typed representation of it. Because the AST node, we can't use the AST node directly. AST node is not type checked. And we don't want to refer to it in our runtime as well, because we actually want to refer to type check pieces of information. The struct layout contains all of that information. Now, in order to do this, again, it's super simple. Once we see a struct node, AST struct node, let's just look at this one. We create, for all the members that we have in the AST node, so here we have the AST struct node, which contains all the members, but again, this is just node information. We then type check it, and then for each member that's in the AST node, we then create the type for that member, and then we create a field for that with the member name and the declaration and the type of that. And then we add this struct field to the struct layout, and then we add that to the symbol table. Now, whenever we want layout information, we just ask the type checker, hey, for this struct, give me the layout information, give me all the fields associated with this struct. This makes it really important. This is a really important thing, because we both need it in the runtime and we both need it in the garbage collector, which we'll look at a lot later. Once we get the struct layout, we just add it to the table. All this code is just doing, it's just making sure that there's not a pre-existing layout already. We're not adding duplicate layouts for no reason. We've now looked at type checking, and we've just completed step 3. We've seen how types of trees are represented, the symbol table, and finally we looked at how struct layouts are represented. The struct layout is really important because we need it in order to generate the object allocation. When we allocate a person object, we need to know how big that object is, and to do that we refer to the struct layout table to get all of that information. And when we want to access a field from that particular object, the struct layout is going to tell us which offset that, which memory offset that exists in. Again, we'll get to that in a second. Right now, we're going to move on to step 4. Now, step 4 is how are objects represented within the language. So we're going to be focusing on that. We're going to be focusing on how objects are represented in the language, how the primitive objects are represented, how user-defined structs are represented, how arrays are represented, and how we access fields from an object, and how we do array access inside the virtual machine as well. We're going to be looking at the code generation that occurs when we allocate an object, and then we're going to look at how we resolve fields. But before that, let's look at the code here on the left hand, on the right hand side. Here we have an int object is 1 plus 1. We have a double object, which is 1 plus 0 plus 1 plus 0. And then we have a char object here. If you increment the character a plus 1, you get the character b. The reason why I've shown that is every object in NoC is actually heap allocated. There's no objects that are allocated on the stack. Everything is heap allocated, even primitives. And this just made it easier for me to actually program against. I didn't have to worry about allocating onto the stack or anything like that. I just allocate from the heap. Essentially, I can do new int and new double. Now, how are these objects represented in the runtime? And in runtime.object.h, you see how all of these objects are actually represented. First, look at the int object right here. So the int runtime object has the int value. It's just represented as a C++ struct, and it's going to contain the int value. The double object is the same thing. It's going to contain the double value. Again, we're just using C++ to emulate that object. The bool object itself has the bool value. The car runtime object has the car value. So each of these objects are going to be allocated by allocating one of these runtime objects. So when we resolve 1 plus 1, we have to actually, we create a new object to store that result in. And we're going to look at the code generation for this, and then we're going to see how the VM allocates that object. And it's going to make it really simple to see, because once we can allocate the primitive objects, we can actually build up user-defined structs. Now, before we do that, we're just going to compile this program and see the code that's generated from this. Right? So so here we have the function main, and remember it's a stack-based instruction set, so we push things onto the stack. So we're pushing one, we're adding them together, and we're storing that object into the int object, the same thing that we're doing for double. See, we're loading 1.0, we're loading 1.0, we're adding them together, and then we're storing them in the int object. Now, we're now going to look at how the VM resolves the arithmetic operations for the integer. Now here, I'm just going to close that. When we resolve an arithmetic operation, we get the first operand and the second operand, we add them together, and we store it in the result object. But we need to allocate the result object first. Everything in NoC is heap allocated. And you can see right here, when we allocate the object, we ask the allocator, in this case is NoC alloc, but this could be just malloc, or your standard allocator that comes with the language. But because we have our own allocator, we just call NoC alloc. You can ignore the pin for now, but NoC alloc. We give a reference to the heap, and we're going to explain later where that reference comes from. And then we ask how many bytes we want the allocator to give us. And we just pass in the size of the runtime object that we're trying to create. So because the result object is going to be an integer, we allocate the size of this integer struct from the allocator. And if it was a double, then we'd allocate a size of double from the allocator. So we're going to debug that program to see how that looks like. Then you see, we ask the allocator, hit allocate for us. We pass in the reference to the heap, and this is how many bytes we want. If it's null, then the allocation has failed. If it's not null, then we know we have the allocation right, and we can just cast the result object to the struct object that we wanted to, because that is how the allocation. That's where you can just cast it back into the object, because the number of bytes that you received is the same thing as the NoC in runtime object, because that is what we asked for. And now from this result object, we can store the value. And with the object just has the value inside it. We can get the value from the first operand and the second operand, which are both of integer. So you can see that they're both integer objects, and we can just store that value. Now, all NoC runtime objects have the container header. Every single runtime object has this. The container header tells us what object type it is. Is it an n-dimension vector? Is it one of the primitive types? Or is it these extra types that we have to support other operations? It also has the type number. So each object has a type number. We need this information for garbage collection because we need to know the layout of that object and what kind of object it is in order to do garbage collection. But we'll come back to that later. But every single object has this header, and it's the first thing associated with that object. Now, once we return the result object, which is an OC runtime object, we can see that we cast it back into this container header. Every object gets casted back into this container header. The reason why we do that is when we need to push the result back onto the stack of operands is of this type, no C runtime object container, because it needs to support any object that we want to push onto the stack. And if you look at runtime objects, there are many different types of objects. Of course, the primitives are there, but you can see that across the primitives, there's all these other objects as well. There's the vector object, a non-native string wrapper, the struct container. We're going to get into them, but it needs to support pushing everything. Now, if they all have this header, then all of them can get pushed. It's not type safe to do this, but I didn't want to use any inheritance hierarchies inside the runtime because it makes the code a bit it makes the code a bit confusing. So I just have this have every single struct have this header, and then you can just cast it, and you can cast every single object to a object container and then push it onto the stack, because the stack needs to support you pushing anything, because this could be an array or it could be a user-defined struct. So the stack needs to support you pushing anything. So that's why everything's casted back to a no-C runtime container. And when we pop it off, depending on the operand, we just cast it back to the correct type. Okay. Now let's look at how a user-defined struct is allocated. Let's look at the opcode that's generated when we actually allocate an object and how we then ask the allocator to allocate that many bytes for the object. In the type checker, we spoke about the struct layout, containing all the information about the fields. The type checker also knows the size of the object because it knows all the fields, and because it knows all the types, each type has a predefined size. When we allocate an object, we generate the opcode for it, which is new. So if you look at the main function, we see that we allocate a new object, and the object that we're allocating is the point object. The identifier index is number 4. So when we search the layout, we just search by this identifier index. So we first find the struct layout, we search for it. Now, this should always be there because the type checker should ensure it. And then we create the struct runtime object. We just get the heap. We create the struct runtime object. How do we know the size of the struct? We ask the layout, hey, give me the size of the struct. So then I can actually ask the allocator, allocate this many bytes for me. And then it's cast into a no-C struct container. And the no-C struct container is the runtime object that is going to represent this struct. And we see here that it has the fields, and here it's actually marked as 0. We'll explain that just right now. Okay, we've looked at parsing and tokenization and type checking. Now we can configure the layout. The type checker creates the struct symbol associated with that. So it creates all the struct layout information associated with a user-defined struct. And now we can actually configure the layout. We can configure the sizing information of that struct. And we can see that we just loop through every single user-defined struct in the symbol table, and then we calculate the total size of the struct. Now the total size of the struct is the size of the container object, which is this header. And the reason why fields is 0 is because we don't want this field to contribute to the size of the object. The size of the struct is the size of this container plus the number of fields that we have. So here you can see the field index is incremented for each field, times the pointer size. Now everything in no-C is a pointer, everything, because everything is heap allocated. So if you look at main.no-C, this is actually, in the runtime, is going to be a pointer to some integer object. And this also is going to be a pointer to some integer object. And that is the total size of the struct object. However many fields there are multiplied by the pointer size. Now the pointer size, depending on the backend, but there's only one backend subway that's no-C virtual, is the size of the no-C field, which is just a character. So it's the size of a pointer. Now, just to bring this point home, we're just going to look at the documentation, as there's a good example here. So here we have a struct person, which has a string name and an integer age. So we can see when we allocate this object, it's always going to be the size of the no-C struct container, which always contains that header information, which is the type of that object. We're looking at struct object type and the type number associated with it. So this is going to be the actual, like the person type. And then the fields associated with it, because remember the struct layout has 2 fields associated with this. So the size is going to be the number of fields times by the pointer size. And that's why we can stuff the fields here, because the object that we're going to allocate is going to be of size no-C struct container header plus however many fields there are, and the pointer size for each field, which is 8 bytes depending on if you're 64-bit. So now we have 2 fields, and then we can just reference and stuff the actual objects inside these fields. And hope that makes sense. Just looking at the runtime object code, when we create a struct runtime object, just once again we allocate from the allocator, and then we can see for each field, so we're looping over the layout of that struct layout. So we can see we have the struct layout right here, and it has all the fields. For each field, we know the index that particular field is going to be. So in our example right here, where we have the point object, we know that this first field is going to be the integer x, and then we can actually just reference, we can actually index straight into that field to then store the pointer value of the object. Now the default object for integers is a 0, so we get that from this function that's going to return the default runtime object. If it's a primitive, we're going to return the default that we expect from a primitive to be, and then we're going to assign it to the index. So that's exactly what we're just doing. We're just looping over all the fields, and then for each field, it has the associated index. It's just in order. We're just going to allocate the default object for that. Now we're going to look at how we load a field from an object. Now looking at the documentation here, say we wanted to load the field name. We know which index that is associated with, whether it's index 0 or index 1. Now it's going to be 0 because it's the first thing that's in this object. And if we wanted to load age, from the person object, we load from index 1. And that is essentially all there is to it. So we're now going to run the compiler to see how we're going to load these fields. So we create a point object, and so we're going to see now how we load from x, y, and z. Now if you look at the main function, we first create a point object. We store that point object into this local variable point. And then when we load a field, initially we have to load where we're loading from. So we load the identifier, and we push that onto the stack. Then when we load the field, we see that the first thing that we pop off from the stack is what we're trying to load from. And it can't be null, otherwise it's a null pointer exception. And this is the way the runtime can just tell you whether you're trying to dereference a null pointer. And that's essentially what this is doing right here. And here is where the first assert comes in, and this is where the runtime object type really helps us, just in case we've made a mistake. As well as with the garbage collection that we need this information, it also makes the VM more robust, because if this is not a struct object type, then whatever we've pushed on, it can't be correct. So the code generation has to be incorrect. So this is how I just make sure everything is working quite well. And the asserts on production mode, if you know, would be turned off. And in the instruction for the load field, you see that the first argument that we have is actually the field index of where that is in the struct layout. And the mem offset for this one is 0. So when we load the object from the offset, all we're actually doing is we're loading from the fields array. And we're loading from field index 0. Just like in the documentation that we had, is for name, it was in field index 0. So this will be field index 0, this will be field index 1, and this will be field index 2. And that's why, because everything's a pointer, we can just actually load the value, and then we can just load it from that particular field offset, and then we can just push it back, and then it's now going to be stored into X. And we do the same thing for everything else. So we can see when we load point.y, the value that we're loading from is the point object. The memory offset is part of the instruction, so you can see here that when we load the field y, we're loading from field index 1. So the memory offset is just an index into that array. So we're now just going to load that in. And remember the field index, it's just an array that is going to hold where that pointer object is. So it's just an array to the pointers that are actually the runtime objects. It's not, in particular, this is not a no-C runtime object pointer or no-C container object pointer. Like, it's not this for one particular reason that we'll come back to later, because I abuse it and I stuff many things inside here to get other things to work. But so long as it's a size of car pointer, then it will always work, and everything is. And we just load the next value, and then now we're going to be looking at point.z. The value that we load from is the point, so that's what's going to be on top of the stack. And the mem offset is going to be 2, so it's the second index in that struct container field. We're going to load from that second index, and we're going to push that value back onto the stack just to complete the instruction. The final instruction is going to be a store. So to store it in Z, we're going to pop that value from the stack and then just store the symbol and increment the IP, and the program is now almost finished. We're just going to return from the void because this is our main function, and now the program is actually finished. There's nothing else to do. That's how struct layouts are supported. Okay, let's see how function call is actually resolved itself. So when we have a program that calls foo, like we see on the right hand side here, how is that foo function going to be resolved? It's the same exact mechanism of a function pointer. We just need to know the address of that function and then call that address, essentially jumping our instruction pointer to where that address resides. And again, when a foo function is called, we generate code for its arguments before we generate code for its parent. And here on the left hand side, we have the debugger running for the code generation that's going to be emitted when we have an AST function call. So I'm now going to debug this just to show. We're going to skip over the first one, and then I'm going to see when we arrive at foo. And here is the AST for function foo. And just to remind you how the AST structure looks like, here's the AST structure for the function call, where we have the name of the function, which we can see right here, and then the arguments that are of the function. Now there's only one argument, and that's the literal 1. And a reminder about how we generate code for a stack-based virtual machine. We generate code for its children before we generate code for its parent. So we can see the first thing that we do is we generate the code for the function arg. Now, because it's a literal value 1, the code that's emitted, I'm just going to show you that instead of actually just explaining it to you. For each argument that's supplied here, we're just going to generate the code for that specific thing. Now, this is just doing a C++ range check. We're just going to generate the code for that internal node, which is the argument of that. And we're going to see that it's going to be a literal. So we're just going to go all the way down. There's so many nodes to generate code for. But we're going to see we're going to arrive at the literal eventually. And here we have a literal. Depending on the literal type that it is, because it's just a number, we're going to load that constant straight onto the stack. And here I'm just going to now unwind the stack. And here now we've generated code for all its children. Now we can actually generate code for the parent, which is the call-up code. Now the call-up code has an argument of where to jump, at what instruction value is this foo function in. So when we see the call instruction, we're going to jump into that. Now I'm going to put the debug point on the VM for the call instruction, opcode call. Here it is. And we're going to start the program again. This time, however, I'm just going to, there you go. Now I'm just going to look at the instruction stream again. Let's look at main right here. We can see main, we load the constant value 5 onto the stack, and then we call the function foo at instruction pointer 60, because that is where the function foo its code is generated at instruction pointer 60. You can see that the label is right here. Now, here we see we're just debugging when we actually hit the opcode call for this foo function. We find out where we need to go from this instruction. We're going to update the instruction pointer to now point at instruction 60. Now it's pointed at instruction 60, so the next instruction that we're going to actually generate, so we're going to actually execute, is the label for this foo function, which contains all the code for the actual foo function itself. Now this is where the function symbol table is going to help us here. Now the function symbol table will let us know how many arguments we need to pop off from the stack. Now remember, when we initially call this foo function, the number 1 was pushed onto the stack. By referring to the symbol table that the type checker generates, we know how many arguments we need to pop off from the stack. Now once we pop off from the stack, we do some initialization that needs to be done for that instruction, for that function call, and then we just execute the following instruction. So we can just ignore all of this stuff. Then we just execute the following instruction after that, which is the load I for x. And that's how a function call is actually resolved. We're going to break it down even further when we look at how to actually set up the function call itself. But I just wanted to again reiterate how the code generation is done for a function call, how we jump in to that instruction pointer, and how the arguments are actually resolved. Here we push one thing onto the stack, and by referring to the symbol table that the type checker generates, we know how many arguments we need to pop off from the stack to actually make the function call resolution work. Once we've done that, we just increment the IP, and then we execute the first instruction in that function call, which you can see is load I of x, because again, the function call for this is a printf. We generate code for its children first, so we load the value of x, we load the non-native string through %d, we turn that non-native string into a native string, and then we load an immediate value of 1, and then we call the printf function. So again, it's the same exact thing. We generate code for its children before we generate the call instruction for its parent. And you can see when that is done, we just return from void, because it's a void function, and that's the entire function call executed. Okay, we've now just done step 4. We've seen how a struct layout and VM objects are represented, how we access fields within a struct layout. We've seen how the function call is actually done, and how the function call is also supported for passing a function pointer. We haven't looked at the full mechanics of how a function call is actually set up. We haven't looked at something called activation frames, but we'll come to that when we actually dive deeper into the runtime. I just wanted to introduce that to you guys so you could see how the code is generated for it and how we access certain fields within the runtime objects. It's not complicated at all. And if there's any confusion with that, you can always complement it with looking at the documentation. The compiler.pdf has this again in more succinct detail than I'm actually explaining it, but it complements what I'm explaining, I think, quite well. We'll look at array access later. When I edit the video, I might just put array access right now, but it's much harder to explain than the other parts of the compiler. The next part, now we're ready to move on to step 5. I want to explain how polymorphism and function polymorphism and struct polymorphism, how it actually works, how are generics supported within the runtime. To support this, we just need to understand how the AST is transformed. And it's actually incredibly simple. I have a new board right here where I'm going to write out a function, a polymorphic function, and and a generic function, or you can call it a polymorphic function or whatever is more comfortable. I'm going to use the word generic and polymorphic interchangeably. So here, let's have a polymorphic identity function. So an identity function is just the function that just returns itself. And it's just going to return t. Now, when the type checker actually sees this, it does generate a function symbol for this, but the function symbol that it generates is a generic function symbol, but the entire mechanism is the same. The mechanism that supports type checking for polymorphic functions is the polytype. It's just a new type that's introduced, just like the array type or the base type or the lambda type, that just represents whether a type is a polymorphic type. Now in NoC, any type that is in between A to Z is considered a polymorphic type. These are reserved by, it's a reserved keyword, you could say. You can't make your own user-defined struct with a type T. Whenever you reference a type T or any type between these alphabetic letters, then it's considered a generic type. Now, type checking is done exactly the same way. The function symbol is generated, the body of the function is type checked, and everything works exactly the same way. The only thing that happens is that this function is actually marked as polymorphic. So when we create the function symbol, and when that function symbol is stored within the symbol table, that function is marked as polymorphic. How does it know it's polymorphic? Because when the type checker goes to look at its types, if any type, whether it's the return type or the arguments, if any of those types are polymorphic, meaning that if any of those types are in between A to Z, then that function is mapped as polymorphic, or that function is mapped as something that needs polybinding. What this means that if the function is called, if this identity function is called with non-generics, meaning that types with an actual concrete type, not a generic type, then we know we need to now expand this function and generate an entirely new clone of it. Now, polymorphism is just cloning the AST when we know what concrete type is. Anything inside the body, we're just going to clone the entire function and replace any t with whatever was resolved at call time. Now, let's say that this particular function, this AST for this particular function, will be an AST function definition, and it's going to have a body, and it's obviously going to have the arguments, and one thing is in that body is the return, AST return, and this is going to be the AST for this exact function. Now, when it's called with an actual type that we can resolve, let's say 42, when it's called with that, what we do is we first look up this identity function. We find the function symbol associated with that. We know that this function symbol now needs polybinding. I mean, we can't actually call this function because it's a polymorphic function. What the polybinding flag tells us, we need to make a clone of this entire function definition, replace out all type t's with what was ever resolved at call time, which is 42. Now, 42 is an integer, so this means that t is an integer. Now, the key data structure that makes this possible for us is the poly environment, and you see it all over the source code. A poly environment is just a map that is of some generic string to whatever was resolved at call time. So here, the polymorphic function has the type t. At call time, we've used 42, so the type inferred is an integer. So the poly environment holds this t and says, oh, this t that is part of this generic function actually now needs to be replaced by an int. So when we call this function, we find the function symbol associated with that, then we clone the entire function definition and the body of that function with this poly environment. Now, the poly environment is really, really important because when we clone this function, anytime we see t, we look up into the poly environment and then we replace whatever the user has supplied, wherever we've inferred. So if you look at the identity function, again, we see, okay, we see a t, we know we need to replace that with whatever we can resolve from the poly environment, the identity, and then again, we find another t, we resolve that, and the entire body is the same. So we clone it for no reason because the body remains the same, but the actual function definition is entirely different. Now, at call time, we cannot call this generic identity function. We have to actually call this expanded function that has the types resolved. Now, when we expand a function, we just don't call it identity, we give it a mangled name. A mangled name. Basically, when we create this identity function, we put in all the types that we resolved. And it will look something like this. This is actually the name of the function. Now, at call time, instead of calling this identity function, this generic function, we actually replace the function call with the mangled name for this function definition. So this one, instead of identity, let me just erase that. When we actually expand the function and we create a new function definition, it looks something like this. Int t. So instead of calling identity, we now call identity int int. And if anyone in the source code calls it with this structure again, we already have the polymorphic expansion of this identity function with an integer as the generic t. This is all that generics is. We clone the entire AST, generics and polymorphism. We clone the entire AST we create a clone of the AST, we create a mangled name for it, and then we substitute this identity function call with what was resolved with the poly environment when the types were substituted, which would be this function call. Now, every AST node has a field called substitution. This allows us to substitute any node with anything else. So here is the AST function call for identity. We're going to substitute this function call with a new function call that now points to this function. And that's how we actually resolve polymorphic functions. We just create a clone. Now a good way to look at this is, let's look at the array list initialization of the array list function. So here I'm going to just write the entire thing, struct. This is a generic array list. It's actually from the source code, array list. And then it has some generic t, which are the elements. Now, there's a function here that initializes the array list. I think it's called initial array list. And given an array list of that generic, okay, let's look at an example. We're going to create a, let me just zoom in. We're going to create a generic function. This function is going to be called generic. It's going to take in an argument of type t. What this function is going to do is going to create a new array. We're just going to say it's 5 elements. That is of that generic type. And then it's just going to allocate the 0th index to whatever the user supplied. And it's not even going to return that. That's just the generic function right there. And this looks like, there you go, generic. Now, when the type checker initially type checks this function, it's just a normal function. It's going to mark this function as something that needs poly binding. How does it know that? Because some of the types are of poly type, they're polymorphic. And remember, a polymorphic type is any type that has the characters A to Z, poly binding equals true. So that means when this function is ever called by anyone, when the function symbol resolves it, when the function symbol table resolves it, it's going to see, oh, it needs poly binding. That means we have to expand this entire function definition and replace any t's, any generic things, with what the user has supplied. So here, okay, we see that it's a generic 42. We initially look at it, oh, we see, oh, it's poly binding true. We now need to expand this entire function, this generic function, and replace that function call with the instantiation of the non-generic function. And initially what happens is we figure out what's inside the poly environment. Poly environment, we can see, oh, t is mapped to now an integer because that is the type inferred. And the first argument is t, so we know we need to map this within the poly environment. Now, when we clone this entire function definition, we use the poly environment. Whenever we see t, we just substitute it with the type that the user has supplied. And in that case, we see that function generic. I'm going to leave some space for a reason we'll get back to. And we see that the first t that we find is this first argument. We replace it with t. And inside of the function, we see if we can see any other t's, r equals new, and it's not going to be t because we know that we found a t. We can look at the poly environment, which is a mapping of the resolved types. We just replace it with an int. Everything else stays the same, 5. And we can see that r0 equals t. And this is now the expanded non-polymorphic function. Now, we can't say that the name is generic. We have to give a mangled name, which is the actual non-generic resolved type. And the way we do that is wherever we've resolved the types to, we just add it to the name. And you can't use the syntax when making a name for a function. This is something that's only available to the type checker, so it creates a mangled name. And the reason why we have to use characters that we can't, that the user can't use, is just so it's impossible for the expanded function definition to be something that the user can potentially type out but by their hand themselves. So we use special characters that can't be used to actually create function definitions. Now, we then substitute this generic function call with this generic int function call. So remember that all ASTs have a node that we can substitute. So this will be an AST function call, but remember everything extends from node. So the first field is a substitution field. Now we just substitute this entire thing with a new function call, AST function call. But what is the name of the function? It's this non-generic int. Now at code generation, this is really important. When we're traversing a tree for code generation, we check if any node that we're trying to generate code for has a non-null substitution. If it does, we generate code for that instead of the actual root node that we found. That way, when we generate code for a function that has its generics resolved, that can be resolved to be a non-generic function, we just walk down the substitution and then we generate function for this. That is all polymorphism is. For the struct definition, it's exactly the same. We just make a clone of the struct definition and we replace all the generic types T's with what the user has supplied within the poly environment. We're now going to debug and look over the source code to see how that is. Then we're going to see the code generation for this. In particular, I'm actually going to use this exact example, and then we're going to see that polymorphic resolution is in the code probably the ugliest part of it, because there's many edge cases for it, but the actual mechanism is really, really simple. The only problem with polymorphic expansion is you create a clone of the entire AST. And if you have many, many polymorphic functions and you have many different resolutions for those, you create separate entire clones for them, because you have to actually generate the clone of this. So if this was called with a string instead, then this will be a new string of an array 5, and there will be an entirely new AST for that. So you actually have code blow up from this. There's other ways to do it, and in the references there is a list of stuff that you can use. And of course, to understand it further, you can always use the AI system, the AI learning tools, and then ask AI how generic functions can be resolved. Well, this is the way I do it, and this is the easiest way that I found to have it done. There is one flaw, and we will look at that after we look at the code examples coming up right now. Okay, let's look at an example, the same exact example that we drew out. Here we have a generic function. It's the same exact example, and the generic is called with an integer. Now, the first thing that happens, and we're going to put the debugger on, is we do the exact same process that we always do, is generic and non-generic functions are still type checked the exact same way. So here we create a function symbol from the function definition AST. So from the AST, we then create a function symbol associated with that. The function symbol just takes in all information from the AST and creates types. One thing that it does do is for each argument, it creates a type for each argument. Now here we can see that the first parameter type is a polytype. And remember, we introduced a new type called a polytype. And a polytype is just any argument that is of type T, or any argument that is between the letters A to Z is considered a polytype. Now here, if we're just saying, is this type a polytype? If it is, then the function symbol needs polybinding, meaning that when this function is called, this flag lets us know that we need to expand the function. Now type checking is done exactly the same way. This function is still treated as a normal function, and the types are still considered types. It's just a polytype. Just like an array type or a base type or a lambda type, these are just types, and the polytype makes no difference. This is array is of type array type, and the base type is a polytype of type T. And that's why we have, if you remember the array type itself, that's why it does not have a base type here. It takes in type because we can now stuff in the polytype for it. That's why it takes in anything. And that's how we create complicated nested hierarchies of types. Now, just to demonstrate that this function still works exactly the same way, it's still type checked exactly the same way, and the function symbol still exists. It just has a flag that lets us know whenever this function is called, we don't call the generic function, we expand it out. Just to show you that, you can see that a symbol has been declared with a different type. Now this is an array of type polytype t, and now we're reassigning it to an integer. The type checker works exactly the same way. Now when we call this generic function, so I'm going to run the debugger again. When we call this generic function, we can see when this generic function is actually called, we arrive here. So you can see that the function call is generic. We skip over all this stuff that I don't really need to explain right now, but we see that the called function symbol requires polybinding. Now when it requires polybinding, we actually don't do the return types equal between what the expected argument is, because we haven't resolved it. We haven't expanded the polymorphic function. Right here is when we expand it. So I'm going to jump to the next part. The called function symbol does need polybinding because the generic is just, it's a generic which takes in a type t, and because of that it needs polybinding. Now we expand the polymorphic function. I'm just going to step into this code now and just skip over all of this pieces of information. But here we actually create the non-poly function symbol associated with that. We're creating a concrete function symbol from the poly function. And you can see right here, as I scroll down a lot of this code, we clone to non-poly. So I'm just going to jump here. Here we then take the entire function AST associated with that. So you can see the poly function symbol, we take its function body, which is right here. We take all of that and we clone that. Anything that we find that has a generic of t, we substitute it with whatever we found in the poly environment. And you can see what's the poly environment. It's just a map from the string for any generic strings to any concrete types. And whenever we see a generic node here, we just substitute it with the type that's resolved from it. We clone out the entire AST, and you can see here, clone to nobody, clone to non-poly, just tree walks the entire AST. Whenever we see a generic, type, we just substitute it out with whatever we can find out in the poly environment. So let's just say when we clone the object creation, we could just ignore a lot of these pieces of code. But when we created the new AST node for this, if I can find out where this function is actually cloned, is clone type declaration. You can see here that right here is, if we see something that's of type t, then we just resolve it from the poly environment. We ask, hey, do you have anything in the poly environment which is of type t? Now, how do we build up the poly environment itself, which is the map? And this is to do with merging and unification. If I jump up right here, is as we create the poly environment, we just figure out what types the user has supplied. And this is here with this merge types and unified types. Now in the documentation it explained what happens here, but essentially we just want to populate what the user has supplied into the poly environment. So if this is an integer, then in the poly environment, t gets mapped to an integer, such that when we clone to the non-poly, we can pluck out and then substitute the entire thing. Now, after cloning the entire body, we create the non-poly function symbol. It doesn't need polybinding because we've actually cloned the entire thing. There are no generic instantiations inside this clone. This non-poly function symbol is then added to the symbol table, just like any regular function. And let me just move right here and call this. Now we create a function call with that polybinded function symbol. You can see the mangled name is generic int void. And instead of calling the generic function, we use the substitution field. And you can see here that every AST node has the substitution field, and we can just substitute any node with pretty much anything. When it has a substitution field, we then create a new AST function call with that non-poly function, which is generic int void. That's the name, that's the mangled name. And then we just substitute that with the function call. And you can see here, right here, we just substitute that with the actual non-polymorphic instantiation of that function, generic int void. The reason why we do this in code generation, if I look up into generate internal right here, if there is a substitution for any node, we generate code for that substitution. We recursively just look at the substitution and then we generate code for that substitution. Now, the substitution for this AST function call is a function call that is generic int void. So when we see the substitution, we then call out into the non-generic function. One thing that I should mention is when we generate code for function calls, if I actually go up here, needs polybinding. When we generate code for function definitions, we just check whether the function needs polybinding. If it does, we do not generate code for it because we don't need that code whatsoever, because at some point someone would have to call it with a known type, and then at that point we expand it to the non-generic function, and then we only generate code for non-generic function definitions. If something is a polymorphic function, we don't generate code for it because we don't need to. At some point the types will be resolved, and that's all there is to it. Now if I let this play, we can see that if you look at generic int void, instead of calling generic right here, we substitute it with generic int void, which is the non-generic function of that. And you can see we generated code for the generic int void. It's exactly the same thing. We load the const 5, we create a new array, and can you see it's int and not t because we substituted that AST, and this is a non-generic substitution. That is all there is to polymorphism and generics. Struct definitions are expanded exactly the same way. If you look at array list, right here, let me just move this right here, you can see that it takes in a type of t. Again, when someone creates an array list with a non-generic argument, we just copy the entire array list and then substitute out any t fields, any generic fields with what the user has supplied. Again, we use the poly environment, which is the mapping of bindings. There's two key functions, merge and unify. This is explained more in the documentation about what they do. And then we build up the poly environment, we substitute it out, and then instead of calling the generic struct, we call the non-generic struct that we resolved with the arguments that the user has supplied. And that's really it, and that's how we actually support generics, and it works out really, really nicely. The only complexity is actually cloning the entire AST. There's many edge cases when cloning the entire AST, and for sure there will be many, many bugs, as if you do stress test the compiler and you give it some weird edge case. I found out to be polymorphism to be the hardest thing to implement, because there were always edge cases associated with bad code generation and cloning the entire AST. It turned out to be quite difficult, because one thing that is supported is local functions and inner functions, and they always created edge cases. So you'll see hacks all around the code base to support polymorphism in the type checker. But that's effectively all that we're doing. And that key thing that really facilitates this is the substitution field in the AST node. If we see a substitution field, we just replace it with something else, and then at code generation we always walk the substitution fields and generate code for that. We've now come to journey's end in the main.cpp file that we initially started with. So let's now come to main.cpp. We can see that hopefully that these parts actually do make sense. Of course, we haven't looked into how every node is code generated, because that would obviously take forever. The documentation should really help to understand that. And of course, the source code, I hope, is written to a good enough standard where you can just read it yourself and find out. It's actually pretty simple how everything works. So we've tokenized and parsed, we've type checked everything. We're going to come into how closures are resolved. We've looked into how layouts are configured and how the runtime represents objects and how we can allocate the objects. We just ask the allocator, hey, give us this many bytes for this object. The allocator gives us this many bytes. When we want to refer to it, we just refer to a single field or an index. If it's a struct, then the field that we want to refer to is an index into an array. And we've also looked into how code is generated. It's just a simple tree walk. We generate the leaves first, and then we generate the code for the pivot. We haven't looked at every node, but I hope we've looked at enough nodes where it gives you a good enough intuition. You can always look at how all the nodes are generated as well. The most important nodes we're only going to look at. And now finally we're here at the runtime, and this is hopefully the final section of this rather long video. I think this video probably will be around 6 hours. The runtime. Let me just zoom in, and let me zoom in more so my handwriting is good. Runtime. This is the final section that we're going to be looking at. So we're going to be looking at, again, no-C threads. We briefly looked at them to see how the VM actually executes code, how it virtualizes the instruction stream. And we're going to look into this in depth. In order to look into this, we're going to understand activation frames. again, we've spoken about how a function call and how function pointers are resolved. We have not looked at how activation frames are set up. Whenever a function call is called, the activation frame needs to be set up, and we're going to look at what that is, what information does that hold, and what does that actually provide us within the runtime. After understanding activation frames, we're in a very good position to understand how we're going to be doing exception handling. Actually, before that, once we understand activation frames, we're going to be a good understanding to understand how defer statements work. Defer statements. Then we're going to be in a very good position to understand exception handling and how we unwind the stack to support exception handling. And even when an exception is thrown, how do we make sure that we run the defer statements that are associated with that? Now that these areas are understood, we're in prime position to understand how local functions work. We're going to be looking at some demos for local functions, how local functions work, and then how we have closure creation. Now, previously, when we looked at how function pointers are passed, we've seen that a closure runtime object is created. The first field is the instruction pointer. The second field is something to do to facilitate closures. We're going to look at how closure creation is used, and in particular, how this allows us to have anonymous functions. Now, understanding closures is the most important anonymous, God, who cares? I don't know how to spell that. Anonymous functions. Understanding closures is required to understand how the runtime is actually going to fork no routines. Once this is finished, we're now going to be looking at how the scheduler works. How the scheduler works. What is the scheduler? What does it do? From that point, we're going to be looking at non-blocking I/O. Actually, we're not going to be looking at non-blocking I/O. From this point, we're actually going to be looking at forking no routines or starting no routines. And then this will allow us to look at non-blocking I/O. What does that mean? And how does virtual threads provide us with a level of concurrency that we cannot get otherwise with non-blocking I/O? And what else are we looking at? And I think that's about it. Okay, after this runtime section is done, then of course we're going to be looking into garbage collection. But garbage collection requires us to understand all of these key parts together. Forking non-routines, non-blocking I/O, is anything else I can think of? No, I do not. Okay, I'm going to explain this again. OBS keeps crashing, I believe because I've been running Docker at the same time. And yeah, the stream always breaks up. Hopefully this works this time around. So I want to explain again no-C threads and introduce the concept of activation frames, which is a key concept we'd need to understand in order for us to understand how function calls are actually resolved. So we have a no-C thread, and we've seen that a no-C thread has the instruction pointer associated with it. We know that the virtual machine just iterates over the instruction stream and fetches, decodes, and executes each instruction, and depending on the instruction, it either increments the pointer or it jumps to another location. And then it keeps doing that until there's no more instructions left to be run. We have a stack of operands that are associated with the thread. So a thread has a stack, just like a real thread that the kernel provides. We have a stack that we want to push values on and pop values off. The stack is really important because we know that our virtual instruction set requires a stack. All instructions implicitly push some values or pop some values off the stack, and the popping and pushing is implied depending on the instruction. The final thing that a no-C thread has, and the structure actually has many things, but one of the most important things is the activation frame. It is the activation frame of the currently running function. Now, if we look at this function that we have, function foo calls bar, bar calls are, the call stack will look like this. Now, depending on if you want to look at it in reverse, you can, but zar, foo calls bar, bar calls zar, and the call stack looks like this. Now, let's enhance the foo function. Let's create another example. Here we have the function foo, and it has three local variables, x equals 1, y equals 2, t equals x plus y. Now, when a function is called, the function needs to be able to store these local variables somewhere. And also the parameters that come in, they're also going to be considered local variables as well. Where are they stored? The function also needs to return somewhere. So when a function exits, that needs to have a return address. these two things are what is kept inside the activation frame. So when a function is called, an activation frame is set up or allocated, and that's going to store these pieces of information. We have the IP, or the return address. Which return address do we need to jump to when we actually return from this function? We also have the storage, and this storage is where the local values are going to be stored and retrieved from when we reference them. So here we store two values, x equals 1, y equals 2, and then when we do the addition, we need to retrieve them from the storage. Two final things are the deferred instruction. Now, no-C supports defer, and when a function exits, a function has an activation frame associated with it. When a function exits or exits improperly, if the user throws an exception, we need to run all the deferred instructions up until that point when the exception was thrown. So the activation frame has a reference to the instructions that it needs to defer when the function exits. And finally, the activation frame always has a reference to the previous activation frame that was set up. It essentially has a reference to the previous call, the previous function call. So za has an activation frame, ba has an activation frame, and foo has an activation frame. But the chain of activation frames goes in reverse. So za has a previous activation frame for ba has a previous activation frame for foo. We need this in order to support stack unwinding. So when an exception is thrown, we need to be able to unwind that stack and find out the first function call or the first activation frame that handles that exception. That's why we have a chain of activation frames. Also, the chain of activation frames allows us to support local functions, and we're going to look at that a bit later. But now we're going to see how a function call is actually done with our understanding of activation frames. We're just going to step over the debugger and understand how this looks. Okay, let's look at how activation frames are created and run in the virtual machine. Here we just have a function that is called foo, and it passes the argument 1. And here we can see that the foo absolutely does nothing but add two values. Before we run the compiler, before we debug the compiler, we're just going to look at the generated code for it. So if you look at the main function, here you can see we're loading the constant for 1. Although it says 6 here, this just means the at index 6. Then we're calling foo, and the instruction of where foo resides, that is instruction 60. So we can see foo, we look for that here. And here foo loads the constant at index 5, which is z equals 3. Then we're storing it in z, and then we're loading an identifier z, we're loading an identifier x, and then we're adding them together and storing that result in location t. And now we're going to debug this entire program just to see how the activation frame is set up, and then how, using the activation frame, we use it for storage, and then finally how we return from a function call by using the information inside the activation frame. So here we're just going to debug this. Hopefully the debugger runs quite quickly. The debugger is stuck, so I have to close this program. We're going to run the debugger again. Should run perfectly fine this time around. So you see we're now calling the foo function. You can see that the return address is 77. So this is just the current instruction pointer we're on, which is the function call, and the return address is the function after it. So that's how we know what the return address is going to be. Then we create the activation frame. Now the activation frame, we just allocate a new activation frame object. We allocate a vector for the deferred instructions. The return address is 77. And we allocate a storage associated with it as well. And then also we allocate, or we link the previous frame that's associated with it. So the current activation frame that we're on, which is main, is linked to the new activation frame for the function called foo. Right? And then we create this new activation frame. And now we jump to instruction pointer 60. And if I just put the debugger point on label, and here we go. Now we're in instruction pointer, we're in instruction 60, which is the actual foo function. Now that the activation frame has been created for this foo function, we can actually use it to store the values for the arguments itself. So we see here that we actually ask the type checker to give us the symbol information for this function. This is going to let us know how many parameters that we have, or how many parameters that were passed. And here, if you go here, we can see that the number of arguments passed is 1. So we can now pop this argument from the stack and then store it within the activation frame storage. And here we store it in activation frame storage, which is just the map. The name is the parameter name, which is x. And then the operand is whatever was pushed onto the stack. And this is how we use the storage to actually store values that we need local storage for. whenever we want to actually load a value, say now we have load z plus x, so we can see we have load, let's just say look at the label for main, so look at the label for foo. We can see here that we want to load z and load x. So I'm going to put the debug pointer here, and when we want to load the identifier here. So the next point is when we want to load z, and you can see here that the symbol that we want to load is z, and we just load it from the activation frame storage. Here we get the activation frame, and we just load it from the map as well. And that's how we actually load values and store values that are local to the function. The map or the storage just lets us store values, and we just load them by the string value. You can change it to not be the string value and just use a number if you would like. The compiler will just have to do some optimization to change the string identifiers into a number. This would make the hashing a lot quicker, because you don't have to hash a string to look into the storage. But that's essentially what happens. We just load the symbol, we get it from the activation frame using this z string, and that's it. We return it back, and then we push it back into the operand, and that's it. The one final thing we're going to do is return from void. When this function actually returns, so it returns at some point here, we're going to see what happens. Let me just remove this breakpoint for the loading identifier. Let me remove that breakpoint as well. And now when we're returning from this foo function, when we're returning from the foo function, we now run all deferred instructions, but there are no deferred instructions, so nothing would run. One thing that we do is we now change the instruction pointer to be the return address of whatever was passed when we created the activation frame, which would be 77, which was right here. And then we update the instruction pointer to point back to the return address associated with the activation frame. Remember, when we created the activation frame, we put in the return address. And now that this updated, the next instruction that we're going to execute is the instruction after this foo function call. And one thing that we do is we restore the current activation frame. When we set up an activation frame, the thread current activation frame is set up with the activation frame of the function call. Once we exit from a function call, we just restore the current activation frame to what was the previous frame, which is going to be main. So the activation frames will be main, calls foo. So here we'd have an activation frame for main, because main is still a function, it just happens to be the main function. And then we create an activation frame for foo. Remember, the return address is whatever is the instruction after this function call. Once and the previous activation frame linked to this is going to be the main's activation frame. And when we exit from this activation frame, we just update the instruction pointer to be the return address, and then we restore the current activation frame of the NoC thread to be the previous one, because we're now popping off, we're just going backwards. And this is the way we can actually chain backwards. And that's what activation frames are. They're just something that is created when we create a function. It's used for local storage and used to hold the return address, and specifically it's also used to hold the deferred instructions. When we return from a function, we just run the deferred instructions, as you can see right here. I hope that explanation of activation frames made sense. An activation frame is just a chain of the call stack. Each function call has its own activation frame. Activation frame allows us to have storage and the return address, as well as some deferred instructions and a link to the previous activation frame. Now, this previous activation frame is really important because it links the chain backwards. So if a foo calls bar, calls zar, calls ma, each function call has an activation frame, but the previous activation frame always points this way, right? It's just the previous activation frame from it. Now, when we throw an error, and in NoC, you just do this to throw an error. When we throw an error, whatever the error message is that we want to throw, say ma throws an error. When we throw an error, because we have this chain of previous activation frames, all we have to do is walk backwards and find the first activation frame that actually has a try-catch handler. If nothing has a try-catch handler, right? If we keep going backwards and backwards and backwards and nothing has a try-catch handler, then we know that nothing can catch this exception, and then we can actually just exit from the entire program. If it's the main thread, then we just exit from the program and we throw an error that nothing can actually handle this exception. let's illustrate how the virtual machine would actually handle this kind of test case. Here we have a main which calls foo, foo which calls bar, bar which calls za, and za actually throws the error. And if you remember from the demo, which was quite a way back, if you're unfamiliar with the syntax, just look at the demo at the beginning of the video when we look at error handling. If none of these functions if none of these functions want to catch the error, then we just try the function call. This effectively says we don't care if an error is thrown, just throw it back up to the call stack, and keep going up and up and up until you find an activation frame that can actually handle this error. Now, I am going to put the debug breakpoint. Let me just get rid of all of these things, and let's just put it opcode throw. And here is the opcode. So when you throw, we generate this opcode throw. Let's debug this entire program. Parsing error is detected. Some semicolon is missing. Cool. Let's run this again. And now we're throwing from here. So at each function call, foo calls, so when foo is called, we create an activation frame for foo. When bar is called, we create an activation frame for bar. When za is called, we create an activation frame for za. And then za throws an error. Now here we call this function throw error internal. Let's just open that up. Now all we do is, looking at the current activation frame, we try to go backwards and find the first activation frame that has a thrown address that does not equal to -1. This just signifies that one of these function calls is actually going to handle this error. So we're looking at the current frame, and because we're throwing an exception, each time we unwind the stack as we're going backwards within the activation frame, because remember, an activation frame has a reference to the previous activation frame. So we're just walking back upwards, or you can say downwards, depending on how you look at the stack. But we're unwinding the stack. And for each frame, we're running the deferred instructions. And this is the way we actually support running deferred instructions even when an error is thrown, because this is how we do it. We just we make sure that when we unwind the stack, we run all deferred functions. Now, we check whether the return address or the thrown return address does not equal to -1. If it does not equal to -1, then we know that we need to restore back to this thrown return address, and then the frame that we restore is the previous frame to that return address. This picture would give you a good visualization of what's happening here. But because nothing here has a catch, absolutely nothing has a catch, we're not going to be able to find a frame that has a thrown return address that does not equal to -1. So we're not going to be, let me just run this one, because we're unwinding the stack. Eventually we're going to be here. There is no frame to restore because nothing is actually handling the error. Now, when this is thrown, we get this error: uncaught no-see error object, terminate call after throwing instance on no-see unhandled error, because there is nothing handling this error. And it goes all the way back up the stack. Nothing handles this error. Now let's just change it such that at least at this point, here is the try catch statement. Now there is no catch keyword in no-see. This is how you just do a try catch. So you can see that the main activation frame, actually the main function call actually handles that. So when we do unwind the stack, we're going to find an activation frame that actually can handle this. And then we're going to restore the pointer to be right here at line number 15, and then restore the activation frame to be the mains activation frame. So we're going to show that again. Here we have it. Debug this entire program again. There is type does not match one of the many arguments, so print error. Here we go, we are throwing an error from the lowest call, which is za. And then once we run the activation frame, eventually we're going to keep going backwards until we find something that actually handles our error. So we keep going backwards. So you can see the current frame equals the previous frame. So we keep doing that. Eventually we're going to find something that, oh, the current frame's thrown return address, which is here, does not equal to -1. So we know we need to restore the instruction pointer to this point, and then we restore the frame. And then we break out. Because there is a frame to restore, we don't throw this error. We update the activation frame to the frame that we need to restore, and then we update the IP. And that is how exception handling is done. As you can see, the program does not crash because this is where the try catch statement is. And that's all there is to it for exception handling in NoC. And that's how it's supported virtually in the runtime. Now, there are some caveats to this, and something like implementation is complete, and a lot of things are incomplete in NoC because, again, I didn't have time to finish off everything, and it was at a stage where I wanted to share it. At least I think it would be beneficial for other people to see. There is one thing that is stopping the complete implementation. The deferred instructions themselves cannot throw an error. If they throw an error, then you kind of end up in this weird loop where your deferred instruction is throwing an error, so you need to unwind that. So I don't support the case where a deferred instruction can throw something. There's also one other thing. If there's an internal error that happens, no deferred instructions actually run. What do I mean by an internal error? What I mean by that is, for example, if there's a null pointer dereference, right now I don't support unwinding the stack for a run pointer error like that, or if there's a array access at an unbound index, I don't support unwinding the stack frame. I just didn't include it, not because it can't be done. It's just I didn't have time to implement that, nor did I care about implementing it. But that's one of those things. But effectively, in any other language, you'd have to support this. Even if you have a runtime error that's thrown, a null pointer exception, you do have to have a mechanism to support running deferred instructions. And those deferred instructions, you have to make sure you protect against the fact that they can also throw and have a runtime exception. You don't want to be in an infinite kind of recursion where your deferred instructions are throwing and those deferred instructions are throwing. So you could end up in this weird loop and certainly come into an inconsistent state. But this is how the mechanism is, and that's what it means by exception handling, to unwind a stack. If you've looked at exception handling, this is my preferred way for errors in a language. I just prefer it like that, and I would always prefer exceptions to explicit error handling unless you're in an embedded system context. I just think this is much cleaner. It looks so much nicer, and there's so much less code to write. The good thing about NoC, just like Zig, is if an error does throw, the try statement at least indicates to the reader of the code that, hey, this function does throw an error, and the caller does not care. At some point, we would handle it, and this is just much nicer to work with. Now that we're on the topic of exceptions, there's one final thing that we want to speak about, and this will be it for exceptions, is if the function is not tried, how does the compiler know that there's not enough statements after it that actually try catches? Because unless you try, you have to catch. This is what the compiler enforces to happen. To do this, we actually need to construct a control flow graph. And a control flow graph is again, another traversal control graph. Again, it's another tree traversal, but it's explicit. Okay, so the control is explicit in the way that the program will be executed by the runtime. For example, if x equals 2, when you make the control flow graph, this will be executed before the if. So when you construct the traversal of this, the conditional would be here before the if statement. We need to do the same thing for the try catch. So if there is a function that throws, so if there's a function that throws and we do not try, we need to look at the statements after it, create the flow graph, and then we check whether that graph equals this statement, if error does not equal null. And if you want to look at the source code to see how that's done, it's called the try handler control flow graph. Really, really small piece of code. And the idea comes from basic blocks. But this is actually not a real implementation of basic blocks. It's a kind of a pseudo call graph. So these names are actually quite inaccurate. And all we do is we just traverse the entire program. And every time we see a function call that throws an error, we record what comes after it. So this is essentially what's happening here. We just append into the control flow graph what comes after a function call that throws. Then we just type check that block. So for all these statements in every single block, we just check whether the next statement after it is of this structure if error does not equal null. So if you look at the source code down here, all we say is expression a catch statement? The expression as catch statement has to look like this. If error, so is the expression after an if statement, does the expression look like this? For example, if I did this is not a try catch. And the compiler complains that it's still not a catch because the operation does not equal. And the right side has to be null. And that's the actual, how the catch statement is enforced. We create a kind of a pseudo control flow graph. And at type checking, if something is not tried, then we make sure that all statements after it match if error does not equal null. And the way we do that is we just create a block. A block is just, in the actual literature, it's supposed to be a code sequence that doesn't have a jump or that doesn't have a change in control flow. The word here is actually not quite accurate, but essentially a block here in this control flow graph is all the statements after a function call that does throw an error. And then you can just check whether that control flow graph is the correct structure for it. The code is really, really simple, and you can look at it in triangular CFG, and that's the way it's enforced. And if you try something, then it doesn't matter. This control flow graph doesn't apply to it because you've tried it, so that is not checked. Okay, another thing, what we've just looked at is, again, a revisit to no-C threads. We've looked at activation frames, how defer statements are handled when the activation frame exits, or when a function exits, the activation frame has a reference to all those defer statements. I have not looked at the code generation for the defer statements, but you can look at it. It's incredibly simple to understand. When we hit a defer keyword, all the instructions after it, which is a function call, are jumped over and then added to the list in the activation frame of instructions that we need to run when we exit from the function. And we've seen exception handling, how we unwind the stack and how we find the first activation frame that can handle the error that we're throwing. The next thing I want to look at is local functions, and it's going to build our understanding and how we actually can implement closures. We've looked at closures and how they're implemented, or how the runtime actually creates the struct runtime object that holds the closure. But now we're going to look at it in depth. We're going to see how the type checker assists us in making the closure, how the code transformation is done. But before that, I want to look at local functions. And it's my favorite thing in programming languages is local functions. So here we have a function foo, and the function foo has x equals 1. We know that when this function is called, we're going to create an activation frame, and the storage for x equals 1 is going to be in the foo's activation frame. It's going to be within the storage of that. So for now, I'm going to add it here, activation frame. And you know we have the storage for that. And then we have a local function that exists inside foo called bar. And when bar is called, as you can see, it prints the value of x. But the value of x is in foo's activation frame storage. So when bar is called, again, a local function is no different than an actual function. It's just syntactically we allow it to nest. But from a type checking perspective and a code generation perspective, it's as though we wrote it outside. Like it exists outside the function. The type checker doesn't make any difference to it whatsoever. It works the exact same way. The type checking works the exact same way. But you can see here that the x that's referenced here does not belong to bar. It belongs to foo. And bar has its own activation frame. So we can see here that the storage for foo would have x equals 1. When bar is called, again, we create another activation frame. But there is nothing in this guy's storage. There's nothing in bar storage. So when it goes to reference x, it can't reference it from its own storage. It has to reference it from foo's storage because that's where it actually is. That's where the variable is declared. Now, it's incredibly, incredibly simple and how we actually resolve this. We know that the stack difference between this symbol and when this function is called is 1. We know at type checking, because we can see it when it nests, that the difference in between the call stack or the difference between the activation frames has to be 1. So when we load the symbol and we find out that the symbol is non-local, meaning that it doesn't exist within inside its own body, we just have to find out the distance between where it's used and where it's declared, the call stack difference. When we load the x, we also take into consideration how many stack frames we need to walk up. Now, because the difference is 1, when we actually load x, we don't load it from its own activation frame. We compile code such that it tells us that we need to go up 1 activation frame and then load it from the previous activation frame. And if it's the further up it is, we just keep recursing backwards. We keep going back activation frame after activation frame and then finding out which activation frame actually holds that piece of code. So the first thing that happens, when the type checker is first going to figure out, oh, there's a non-local identifier, x, inside function bar. The stack difference or the scoping info, well, we can say the stack difference is 1. You're going to have to walk up one activation frame or go to the previous activation frame to find out where that is. With this information, we can actually substitute out the node for x, which is an identifier. And remember, code transformation always works on this substitution field. We can change it to be a scoped identifier. The scoped identifier has an additional field, which is the number of call stacks we need to walk up. And then of course just has the value x. When it comes to generate the code, we substitute out this for this. When it comes to generate the code, when we load an identifier, one of the arguments that we take is how many call stacks we need to walk backwards, how many activation frames we need to walk backwards to find out the storage. Here in this example, it's just 1, because that's the distance between these two things. So we put in 1. And when we actually, in the VM, load this identifier, we just walk up. Just like with exception handling, we just go back one activation frame, because it tells us to go back one activation frame, and reload it from that storage. And it would always be there. That's how non-local identifiers are done. We're going to look at how the code transforms, how the code generates, and then how the VM actually runs this piece of code. Okay, I've just created the same example that we drew out in Miro. Here we have a function foo. It stores a local variable x equals 1, and then bar is a local function inside it, and then bar is called within that local function. Again, local functions are compiled exactly the same as regular functions. The type checker just allows you to just declare it with inside another function, but they're treated exactly the same way. In the main.cpp file, we've visited this quite a bit to see how type checking is done. We've looked at how code is generated, but I've always skipped over this part, resolving closures. Now, one thing that the type checker does do is every time in its symbol table, anytime it finds a identifier that's non-local, meaning that it's part of another function declaration, it stores this information as a non-local identifier. And the final thing that we do for all these non-local identifiers that are part of this function, so here the function bar has a non-local identifier x. When it identifies this non-local identifier, it also records the stack difference between where it's identified and where it's actually declared. This is it's called the call stack difference. But basically it means, and I should have renamed it to be something else, it means how many activation frames you need to walk up before finding where this is actually stored so you can load from it. So you can see right here, when we create the scoped identifiers, we create an AST node called a scoped identifier. And the AST node for a scoped identifier is the same thing as an identifier with one thing. It has the call stack difference, right? I'm going to put a debug point right here to see something. Actually, it makes much more effective. There you go. Okay. So here we go. So when we create these scoped identifiers, for every function that has non-local identifiers, we're going to create a transformation that's a scoped identifier. Essentially a new AST node. The only difference is it's going to tell us what's the distance between this, how many activation frames we have to walk up. So if you look at the function symbol, this is the function symbol for bar. Again, you can see that local functions are exactly represented the same way. There's nothing else. There is only one additional field that says is local, is true, because it's local to some function. And for all these non-local variables, we transform it to a scoped identifier. What's the call stack difference between where this is declared and used and where it's actually been instantiated? The call stack difference is 1, meaning that it's in one activation frame above or below, depending on how you look at the stack. Then we create a scoped identifier AST node, which is just another node, but with this call stack difference. After that, we just substitute out this identifier node, which is right here, with this scoped identifier node. And remember, the way we just do substitutions, every AST node just says substitution, and we just substitute it out. At code generation time, right? Because there's a substitution field, instead of generating the load for the identifier, we generate the load for the scoped identifier. you can see here that there's one additional arg that's provided here. So I'm just going to jump to this point, and you can see the additional arg is 1. So when a load instruction is loaded or executed, we look at the additional arg, and that additional arg tells us how many activation frames we need to walk up to actually get where that is stored. Now here we've got the debugger running, and then we can see how this is executed. So initially foo is called, so we call foo, and we create a new activation frame for foo. And then x is stored as a local variable, and it's going to be stored within the activation frame storage. So we're just going to jump to that. So here's the store. We're going to pop 1 from the stack, and then we're going to store that symbol inside the activation frame for this foo function. That's where it's actually stored. Increment the IP. Then bar is called. Again, bar is called right here. And again, it just works exactly the same way. Local functions are no different than normal functions. We create an activation frame for it. And remember, the activation frame here doesn't store anything whatsoever. So when we actually go to load something, and I'm just going to add a debug point for load I, opcode, load I, here we go, right here. Jump right here, and we're going to be loading x. Here we can see here. When we load the symbol, the first argument is now going to be 1. It's going to tell us, hey, go to the previous activation frame attached with the previous function, and then load it from there, because that's where it actually is. So when we load the symbol, you can see we're getting the activation frame, and we're passing the number of links to walk up. So now we're in bar's activation frame, but we're going to go to the previous activation frame until the number of links to walk up is 0. And the number of links to walk up is 0, and that's the activation frame. If you look at the activation frame that's returned, we're going to see that the function symbol is foo. That's the function activation frame for the function foo. From this, we can just load it directly. So the activation frame that we load from is foo's activation frame. It isn't bar's. And that is the way that local functions also supported, and how they actually allow you to load an identifier that is not scoped to it, that has a different storage location. So we've just seen how non-local identifiers are actually supported, or how local functions are supported, and how they support finding where the non-local identifier is. We just figure out the call stack difference and then just walk up the activation frames. However, how do we use that to also support returning functions? So here we see there's a function foo. It returns a function that's of this signature, so you can see that it takes in nothing and returns void. And we can see function bar prints f. F is in foo's activation frame, and then it returns this bar function. Now we know that in the virtual instruction set that all functions have a label, and it's just a pointer or the number where it is in the instruction stream. So let's just say that bar is at instruction 10. When we return this function, here you can see function main, it calls foo, and foo returns bar, and it stores it in the variable f, and then f is called. So we can actually return where the instruction IP is in the instruction stream when we return an actual function. But let's trace the activation frames, and let's see the problem that we arrive in. So first main is called, so main has its own activation frame. Right, so we're going to write main. And then foo is called, and when a function is always called, we create a new activation frame. Remember, an activation frame is a place that we store things, and we store the return address. So now we've got foo's activation frame. Now, foo returns a bar, and let's say its bar is just going to be returned as an integer, which is where it is in the instruction stream. So when foo returns, this activation frame no longer exists because we now return from it. And now we're back in main. And then main calls f, which calls the bar function because it's stored in the variable f. Now when we call a function, we create a new activation frame. So now we create bar's activation frame. So let's just say bar's activation frame. And then we call the function bar. And then when we print f, we know what the stack difference is supposed to be. We're just supposed to walk up one activation frame to find out where x is. However, look what happens. The code says, hey, load this identifier, but walk up one activation frame. What's the actual activation frame that we walk up? It's actually main's activation frame. It isn't foo's activation frame because we returned from foo. and then we executed bar, creating a new activation frame. So the framing is actually incorrect. We somehow need to preserve, when we return a function, we need to preserve the activation frame or link into the activation frame. So when we call that function, we still link correctly. Now, the word for this is used in the literature is a static link. When we create a closure, when we return a function, we create a closure object. Now the closure object has two things: the instruction, where that function is, and the static link, which just means the activation frame that existed when the function was created. Now let's just see. Let's say when we return a function, that we actually return a closure object. There's two fields in the closure object: the instruction pointer and the activation frame that existed when we returned the function. And we're going to call this the static link. Right? And we return this object when we return a function. Yes, as I was saying, when we return a function, we return a closure object. So we allocate a closure object and we return that closure object. It contains two things: the instruction pointer of where that function is in the instruction stream, and also the activation frame that existed when we returned that function. Now, when we call a function, all we do is we load the instruction IP from the closure object, we create a new activation frame, and we link in the static link with the new activation frame. So let's just see how that would work. So main, in this example, main calls foo, which returns a closure object. Now, once that's returned, this activation frame still has to exist somewhere. We still need it, but we return a closure object. So now when we call f, when we create a new activation frame, we don't link it to main's activation frame. We take the static link from the closure object and link that in. So we create a new activation frame, which is bar's activation frame, because we're calling the bar function, and we link it with the activation frame that is in the closure object, which was created when we allocated the closure object. So now when we load a non-local identifier, we just follow the static link and it goes to the correct place. It goes to foo's activation frame and we can retrieve it from foo storage. So in order to do this, activation frames have to be heap allocated. We can't deallocate them. We can't deallocate them when we return from a function. When we return a function from a function, we cannot deallocate them. They need to exist because we need to always maintain a reference to foo's activation frame. And that is how closures are supported. Okay, you can see on the right hand side it's the same exact program that we drew in Miro. I forgot the application's name that we drew in Miro. You can see exactly the same thing. We just return bar, and then the bar is being called the value of x is x. So it's the same exact example. The first thing that the type checker needs to do, it needs to figure out all functions that escape. You can see here that it's really easy to determine what escapes, because if we see in a return statement, then we know that the function by definition escapes, it's returning. And we store that in, the symbol table stores that in function definitions that escape. We loop all over escaping functions, and then we substitute the identifier with a closure creation AST node. Now the closure creation AST node isn't something that a user can write in code. It's something that we just use to help code generation. So you can see the AST closure node is just like a normal AST node, but it has the escaping function name. And with that, the code generation knows that it needs to create a closure when it returns this. Here it just looks like an identifier. So the code generation might just load the identifier for bar and then just return that. So we need to tell the code generator that it shouldn't do this. It should actually create code required for a closure. Now, we're just gonna debug this. So we can see all the function definitions that escape. You see the escaping function right here. The escaping function symbol is bar because we're returning it right here. And then we just figure out which statement did it escape under. Now there's only two ways you can actually have an escape function, either through an anonymous function or through an identifier. You can see that there's a return here, but there's a certain never reaches. I need to refactor the code. This should no longer work anymore. But here we just see it's an identifier. We're going to replace that node with a closure creation. And you can see the closure creation, that exists. If we come here, the AST closure creation is just a normal node with the escaping function name. So here we get the function symbol and the name is bar. And you can see here that we also create the struct for the closure object. You see he has two fields, the instruction IP, so the instruction function pointer field name, and then the static link, which is type any return. The reason why this is not created in code, like the reason why I don't have something like this already defined, like closure object, because I could easily do this, instruction IP, and then we have any static link. The reason why this doesn't exist is I did not want to expose any as a keyword that could be used in when you actually write code. So that's why it's just written in code itself. And this is something I should also have done for the string object. The struct string actually should not exist as something I should have written by hand because it's a fundamental type within the language. I should have actually just written it as in actual C++ code because I did not want to expose it. I did not want to depend on this existing in some file in order for the thing to work. So here now we substitute it out for a closure creation node. And at code generation time, I'm just going to let it play for code generation. We can see that it's substituted out to be a closure creation. Now in a closure creation, what we do is we first load the immediate address of the escaping function name. And then we ask the runtime, hey, create a closure for us. So we can see here, now we're going to jump into the runtime. When this return function is executed, we're going to see that we've asked the runtime, hey, create a closure for us. Now we're going to search for this struct that we created. And here's just some static asserts that it needs to have two fields. We're going to ask the allocator, create this closure object for us. It's just a regular struct. So just how we create a struct, we just create a closure object. The first field that we store in this closure object, we can see, is we call it the lambda IP, but it's the instruction IP of the bar function. And we pop that off from the stack because in the code generation, remember that, let me just go one more. We load the immediate value, we load the immediate address of the escaping function onto the stack. So when we create the closure, if I go to back to the VM, when we create the closure, we can just pop this off from the stack right here. And then we can just store it as the first field. So now this object that's been allocated, the first field is bar's address. The next thing that we do is we just link the static link in. So what's the current activation frame? We store that in the field as well. And we see in this one, the current activation frame is foo. So we just link foo's activation frame in. Cool, and now we just return this entire object. It's just like returning an object, but essentially what we're actually doing, we've transformed it to look like this. New closure object instead. So this is what we've transformed the bar function to look like. And now that closure object is returned and stored in F, and it's just like a normal object. It's a normal struct that you would have defined yourself. When we go to load F, so we're just going to return that. When we go to load F, there's only one difference that we have. We see that there's two opcodes, one for call lambda and one for call. Now the reason why they exist is to differentiate between something that is a normal function call like foo, where we know the address, and a function call that exists inside a closure object. That's the reason why the two opcodes exist. Because when we call a lambda from a closure, we first pop the closure from the stack, and we can see that the runtime type is of closure. And from the closure itself, let me just get the code back in that I keep deleting. From the closure itself, we can get the instruction pointer or the location of where that function is. And then we can actually jump to this function. So here, you can see right here that we get the function pointer, and that is 48. You can see in the instruction stream that 48, if I just search for it, is the function address for bar. And as you can see, we also get the static link from the closure. So that's in the second field. When we create the activation frame, we link in the static link, and it's right here. So we have the previous frame always, and the previous frame is always the call stack frames. So here it's main, which calls foo, and then foo returns, and then it calls F. So the previous one will be bar's activation frame and then main's activation frame. But we link in the static link. So this now works. Now I'm going to now load in an identifier, and we can see the bar is being called and it's going to load in X. Now, when we load the symbol, you might have noticed that when we get the activation frame, we do not follow the previous frame. We follow up the static link. So we don't, the previous frame to bar is main, because that's the context where it's being called from. But we don't follow that because that will lead us to the wrong storage location. We follow the static link, which is foo static link. Now, if I just walk over that, and we see the static link that we find, if we look at it right here, is foo. And that is how closures are supported within the language. That's how we actually keep a reference to variables that that need to exist when we call a function. Functions are returned, they're transformed into closure objects. From those closure objects, we know to call the lambda opcode, because to call a function inside a closure is different than calling a normal regular function. We need to load the instruction IP from the closure object, and then we need to link in the static link. And that's exactly all there is to closure objects. And this is how we can actually just return functions from other functions. And here we return the bar function, and then we execute it a bit later. Now, the reason why closures are so important, because it allows us to suspend execution until we want to execute it, right? Because we're not executing bar immediately, we're returning it. Many things can happen here, and then we execute it later when we want. And this is how no routines are actually supported. No routines are just closures that we then run when we want to run them. When we want to schedule the async task, we're actually scheduling the closure object, and we're just calling a function. That's essentially all a no routine is, but we'll just go into that. I hope that made sense, and now we're going to go into the next section. One final thing I would like to speak about is how anonymous functions are supported within the language. So here you can see that this function anon demo takes in a function with this signature and then just calls f. And we can see here, instead of giving a named function, we're just passing in an anonymous function. We're just creating the function anonymously. An anonymous function is a function without a name. Now, when we actually go to generate a code for this, you can see that at the top of the instruction stream that we've actually given this anonymous function a name. And the name for this function is just something that we create within the compiler, private function 1 with these diamond brackets. We use diamond brackets to prevent anyone from ever using this name ever. So we can never get a conflict. And for each anonymous function that there is, we just increment the number right here. So here we give it a location in the instruction stream. And the rest of the mechanism works exactly the same way. We allocate a closure object with the instruction pointer being wherever this anonymous function is within the instruction stream, and we link in the static link. So we make sure that the static link is the activation frame that existed when actually creating the anonymous function. And you can see here that the anonymous function says hello from anon, and it prints x. So we know the stack difference is 1. We know we need to walk up one static link and get extra storage. It works exactly the same way. Just to show that it works exactly the same way, I'm just going to debug over the code again, and hopefully the debugger does not take a long time to load. It is taking a long time to load, and it should work right now. We see that the function symbol that is escaping is the anonymous function, private function 1. We've just given it a name. So the type checker, whenever it sees an anonymous function, it's just going to give it a name and just store it in the symbol table. And we're just going to generate code normally. It's as if someone created a function called private function 1, but the compiler, the type checker, is just going to give it a name. And we can see which escaping node it falls under. Because it's anonymous node, anonymous function, we just substitute that again just to be a closure creation. Now the code works exactly the same way. We just create a closure, and the first thing, the instruction IP for this closure is the anonymous function's IP address. It's not the IP address, it's the anonymous function's instruction pointer, wherever it is in the instruction stream, its location, and then we link in the activation, we link in the static link as well. So when this function is actually called, I'm just going to jump over it. So we generate the exact same code, there's no difference whatsoever. We create a static link, again there's no difference whatsoever, and we can see that we do the exact same thing. We pop the IP address, we link in the static link, and then when we call it, I think I did not put it right here. There you go, right here. So when we call it, we pop the closure off from the stack, and we can see we get the instruction pointer that we need to jump to. It's function pointer 0, and function pointer 0 is what? Is the label for the anonymous function. And then obviously we link in the static link, and then we jump to that function, and that's it. And that's how it's supported. It's exactly the same mechanism. We just create a closure, and then we run when we call the function, we just load the instruction pointer from that closure, and then we link in the static link, and everything works exactly the same way. So when this hello is called and we want to actually find out where the storage location is, remember, we just walk up the static links. We know the difference is 1. We just follow it up, and the static link allows us to preserve this link context. And that's all there is to it. Okay, yes, now we're ready to look into schedulers and node routines and how the scheduler works and how these NoC threads are actually scheduled. Just looking up on our track, we're almost at the end of our runtime section. So let me just find it right here. So we've looked at NoC threads, we've looked at activation frames, how defer statements are handled within the activation frame, how exception handling is done, how local functions are supported, and with non-local identifiers, how closure creation mechanisms are supported, and how we can anonymously create a function. The reason why anonymous functions are so important, or why closures are so important, because a closure allows you to then schedule the execution of that function later, whenever you so desire. And with that, we can actually do some pretty sophisticated things. If we support this mechanism, actually running asynchronous tasks is really, really simple. So on my right, we have two things. We have a main function, which is really small, but it's hello world from virtual thread ID, get vthread ID, because the main function is running in some NoC thread. And then here we start an asynchronous no routine, or a coroutine, or a go routine, whatever phrase you like to use. And here it just starts this no routine, which runs this anonymous function. And this is the reason why we wanted closure support, because closures allow you to execute a function later in time. So when we write no, really what we're saying is spin off this task and run this task somehow, however the runtime runs it. It's going to execute at some point. And the thing that's going to be executing is hello world from virtual thread ID, get read, and we're going to ask the runtime, what's the virtual thread ID? What's the NoC thread that this anonymous function is running in? And if you run the program, let me just exit the program right here. If you run the program, we see that the first line is hello world from virtual thread ID, and we see virtual thread ID 1. And then we see the second no routine, or the second asynchronous task, it has a different virtual thread ID. So somehow we've created a new virtual thread object, and then we've scheduled that. But the reason why we wanted anonymous functions or closures is because it allows us to have a mechanism where we can schedule that function call. And the only way to actually use no routines is through anonymous functions. There's no other mechanism. In order to spin off an asynchronous task, you have to be using this syntax. Again, because the mechanism that works is anonymous functions are created as closures. With no routines, all we do actually is at some point we schedule that no routine. What we're really doing is we're executing this anonymous function at some point later in time. And this leaves me up to my discussion on schedulers, NoC threads, and no routines. If I can come here, right here. So here now we're on schedulers and no routines, which is the last part of the runtime. And this is really the journey's end for the runtime. We're going to put it all together to see a good example how everything works. And then we're going to move on to the final stage, garbage collection. Both of these things, the code for this is incredibly simple, but you can always add more sophistication wherever you see fit. So just to remind ourselves what a NoC thread is. A NoC thread, we've seen that from the struct, it has a virtual thread ID. And then we've seen that in the example, we've asked the runtime, give me the virtual thread ID. All the runtime is doing is just reading this value from the struct, from the NoC struct. We've seen that it has an instruction pointer, and it also has access to the instruction stream. Of course, it needs to be able to do this hot loop that the VM is doing while IP is valid, execute the next instruction. And then we know that the NoC thread has the current activation frame that is currently running. So basically, what's the function call that it's actually executing at this point? We're going to look at other fields that are part of the NoC thread. But here we've seen that the virtual machine is running this loop, right? Given a NoC thread, the virtual machine, given a NoC thread, the virtual machine is doing this hot loop. It's fetching the next instruction for that NoC thread, it's decoding that, and then it's executing that stack-based instruction set. What we haven't spoken about is how this initial NoC thread is actually scheduled. Because when we just run the compiler, we just see that it runs. We know that the hot loop is working. But how do we initially execute that NoC thread? Now this brings us to our topic on schedulers. Okay, now we're ready to look into schedulers. And the question we really want is, given all these NoC threads that we have, how do we actually get them to schedule? How do we get them to run? How do we get the VM to start and iterate across the instruction stream for these NoC threads? And the scheduler is probably, both the scheduler and the garbage collector are incredibly simple. The lines of code between them are probably about 1300. The reason being, there's two reasons for it. One, I didn't have time to add sophistication because I couldn't profile the simplest implementation, and I wanted to depend upon the simplest implementation in order for me to actually iterate on it. So I didn't want to have complexity before I profiled, and then I ran out of time to work on this project. So that's why the implementation is really simple. But the great thing about the implementation is the simplicity allows us to easily understand what's going on and then build a strong foundation to create more sophisticated things. It's always having a strong foundation before we can actually build harder and harder things. So a scheduler, the way I'm actually going to do it, imagine we have a bunch of workers, right? Workers running. And each worker has a queue of tasks. A queue of tasks. Right? And some people might be going, oh, okay, this is really simple. I already know where you're going with this. And we have a queue of tasks, right? And each worker, we can actually say that each worker is bound to an OS thread. We actually ask the OS thread, hey, create for us a worker. Create for us a thread where we can run a worker. All the worker is going to be doing is while there are tasks to run, I'm going to pop or deck these in the queue. It's actually deck, but we're just going to take from queue, take from our worker queue, take from worker queue. Each one is actually going to be doing this. Take from worker queue. And then we're going to run this task. That is what a scheduler is. It's so unsophisticated, and that's all it is really. There's so much more sophistication that you can add into your scheduler, but this is the core basic mechanism. Now, what is a task? A task is actually just a no-C thread. There's no difference between them. Equals a no-C thread. So somehow we need to push these no-C threads onto these worker queues, right? These tasks or task queues. And then all that's going to happen is while there are tasks to take, we're just going to run that task. And a task is a no-C thread, right? So right now we're going to actually look at how the virtual machine boot actually works, how we actually start these worker threads, and then how do we get these worker threads to actually run these tasks. And we're actually going to look at how the main function, how the main program is actually booted. Okay, let's look at this really simple program on the right hand side, which is hello world from virtual thread ID, and we're just going to ask the runtime to give me the virtual thread ID for this. Now we've seen that we've type checked, we've generated the code, and now we're ready to actually boot the VM and run the code. What does booting the VM do? The first thing it does is it creates the main thread. So it creates the no-C thread object. It creates a no-C thread object, which creates all of this information. As you can see, it has the virtual thread ID. It creates the stack of operands, and it also has the state of that thread. And this is now we can see why we need a thread state, because the thread can be in many states. It can be created, ready to run, waiting on a lock, whether it's runnable, running, whether it's parked, signaled, or finished. Again, it's a virtual thread, and this will be very similar to what you might find in an actual kernel thread. And we can see we allocate all this information, and we also allocate the start index of where this thread needs to actually execute from, basically the start index of the main function. Right? Once we allocate the main thread, we can then start the actual scheduler. And when we create the scheduler, all a scheduler is a list of workers. That's all it is. It's a list of workers. And a worker has a run queue. It quite literally is a queue of tasks that it needs to run. Right? You can ignore the other information, but that's effectively what a worker is. Now, when we run the scheduler, here you can see we're running it with one actual worker, with one worker running. For each worker that we have, as this is called number of threads, we allocate a new worker, we allocate a kernel thread for it, we allocate a new worker, we create a new worker object, and then we start a thread, we ask the kernel, hey, start a new thread for us, and run for each worker that you have, run this worker loop. All this worker loop does is it gets the task from its task queue, and then it runs the thread, and you can see where the run thread is going to go. It's going to go into the virtual machine. And that is how it's actually supported. There are workers. We ask the OS, hey, run the worker loop in each OS thread. So however many OS threads you want to run, or however many workers you want to run, we can see that if you go to the VM boot, we only want to run it with one worker. This also makes testing really, really simple, because although there's concurrency, if you have one worker thread, there's no parallelism. You can be concurrent even with one thread, and we'll see how you can actually do that. So here we have just the scheduler with one worker running. I guess I should change this to be worker threads instead of calling it number of threads. And then we allocate a kernel thread object, and we ask the kernel, hey, for each worker that we run, just run this worker loop. All the worker loop does is it just gets the task from its own task queue, and all tasks are just no-C threads, and then it runs those threads. Now we're gonna actually debug this and see how this is actually executed. Super, 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 super simple. Right? We're gonna boot it. We're gonna boot into it. As you can see, we're just doing the same thing. We're just initializing some stuff, some constant pools. The constant pool would now make sense as you know, this is this is just an array of constants that are allocated for it. We can see what we create the main C thread, we create the scheduler, and then we can now run the scheduler. Right? When we run the scheduler, we create a kernel object for each worker that we want to run, and then we ask the kernel, hey, run the worker loop in a new thread. You know, because you have to always ask the OS to actually create threads, because the OS is the only thing that can actually run a thread, because it has to schedule it. The OS has to schedule a thread of execution. So the worker here is bound to a kernel thread, but the worker loop itself is its own scheduler. Well, the scheduler is really, really simple. We're just going to pop a task from its task queue and then run it. So we can see right here, that happens is as I create everything, all of this is running. So we create all our kernel thread objects, and then we actually ask the runtime, hey, not the runtime, sorry, the operating system, hey, create threads that are going to run the worker loop for each worker that actually exists in our runtime. And then we can see that we're going to push the first task, which is the main thread, into our worker. Once we push the task into our worker, we see that it gets popped off immediately, and then we can actually begin executing that. And this is exactly what's happening, right? We're just setting up the first activation frame because technically it has to happen because the main function is still a function. And then we're just iterating over this piece of code. And that's exactly what a scheduler is. So if you look right here, a scheduler is just a bunch of workers. Each worker just has a queue of tasks that it needs to run. And we ask the OS, hey, run each worker loop inside its own OS thread. And then that's how we get multi-threading within the language, because each worker is running in its own OS thread. When we actually submit a new no routine, essentially we just create a new no C thread, and then we push that onto one of these queues that we have here. Hey guys, this is OK from the edit room. I just want to quickly clarify that we're not creating any actual kernel objects. Obviously, we're not in the kernel, we're in user space. I just call it kernel thread. So in my explanation, I just kept using the word kernel. We're obviously just creating a pthread object, and we're going to ask the OS to actually create the thread for us. And the OS is going to actually allocate its own objects in its own address space. So I hope that doesn't confuse anyone. We're not creating any kernel objects whatsoever. It's just called kernel thread for whatever reason. I don't know why I named it that. The final thing that I want to explain with workers is the actual design is work stealing. So each worker has its own run queue that has its tasks, and a task gets pushed onto a run queue. So an OC thread is the task of execution, and it gets pushed onto a run queue. And once it gets pushed onto a run queue, if that run queue becomes full, so where's my pen? If it becomes full of tasks, and it becomes overflown, like imagine there's 1,000 no routines waiting to run on this worker, and there's nothing waiting to run on this worker, and there's nothing waiting to run on this worker, we can actually steal tasks from another worker. This reduces the stress that a worker can have, and it actually distributes the load of tasks across it. Now this is in the literature, it's called work stealing. I have not found a lot of publications that actually formally describe this, maybe because it's actually a very simple implementation. But I haven't found many pieces of of literature on it. The mostly about schedulers is just with YouTube videos, but they're linked in the references as well. But this is just called work stealing. If we can't find a task to run on your own private worker queue, we just steal it from someone else. Here's a quick example of how we can start a new no routine. On the bottom, we're actually going to see what the code is actually generated for that. So we can see in the label function, the first thing that's done is we create a closure for this anonymous function. And we can see that we first reload the immediate address of the anonymous function, and this has been given a name, private function 3, and then we create a closure, and this closure is going to have the static link associated with it, and it's also going to have the instruction address for this private function associated with that. We then call the fork operation, and the fork opcode is always created when we create a no routine, we fork it. And within inside it, when we fork a no routine, all we're doing is we're creating a new no-C thread with its own instruction stream, and the instructions that it would actually only execute, the first thing that it would do, it would just load the closure and then call the closure, and then that's it. And this is why we want closures within the language, because it allows us to asynchronously schedule tasks really, really easily by just building on the constructs for the language. So right now I've got the debugger, and we're just going to see how the code is executed for forking a no routine. So here we first see the first instruction is, if we look at main, the first instruction is load the immediate address of private function 3. So we're going to first load the immediate address for that, and we're going to see that the value is 8. So if you look at instruction number 8, hopefully it goes up, we can see that it's private function 3. This is the private function that we're going to load. Now from this private function, we can see that it's address 8, so that's the private function of this anonymous function. And then we're going to push that value onto the stack, and then we're ready to create the closure. So now we create the closure. Again, it's exactly the same thing. We just allocate the closure struct object. The first field is the instruction IP for that, and we push that in, and we also link in the static link associated with that as well. This allows us to still refer to anything from outside the anonymous function. It works exactly the same way, it's just the closure. And then once we do that, we're ready to actually fork the no routine. Now we can ignore what this is. Essentially, we actually can just ignore that. We first need to create a new instruction stream from the offset. The no routine's instruction, or the new no routine, is just actually just running this closure. So after running this closure, it needs to exit. So if you look at the main that we have, so we create the closure and then we fork it. The second argument is the last instruction of that no routine. So we can see here that this is the last instruction, return from void. And that is all that this asynchronous task does. Actually, this is all the asynchronous tasks. All of them have very, very small instruction streams, because all they're doing is they're just running the closure when that no-C thread gets scheduled. So we then create the instruction stream from the offset, and then we create a no-C thread from the parent. So the parent thread is the main thread, and we create that no-C thread from it. So we just create a new no-C thread. We can just ignore all of this stuff. Essentially, we just create a new no-C thread object. All that code is doing is, if there's a cached no-C thread, then we're gonna find that cached thread. If that's the only complexity with inside it. So now we just fork it. We don't fork it, so we create the thread from the parent, and then we're ready to actually schedule that thread. So we're going to just jump here. When we schedule the thread, we just push it into the private queue of that worker. So we just push the task onto the private queue of that worker. So here we have the worker. In our example, we only have one worker running. So here, the main no-C thread is the first thing that's pushed because it's still running. And now the next thing to run is the new no-C thread that we created. So if we look at here, so here we have worker. We have the main no-C thread that's pushed on, and that's currently executing. And then we fork something else, and then we push in something else into the queue. And that is the task for the new forked no routine that we're running. So we're just going to write the no routine. So when main is finished, the next task that's going to be picked off is going to be the no routine. So now that's just scheduled, we're going to push that onto the task. I am going to put a debug point on this point. So once the main function now finishes here, once it actually drops out and returns from void, I'm just going to jump over this this piece of code. Once that all exits and this main thread actually finishes running, we finished running the thread, so we're just going to now loop back, and if the shutdown request has not been requested, then we're ready to get a new task from the run queue, which was just pushed, which was this task right here. And we're going to get a task, and now we're just going to run that task. And all that task is just running that closure. So here we're going to call the lambda, it's exactly the same thing. We're going to call the lambda, we're going to jump to that instruction, and then we're going to do that until we exit out from this. And we can see right here in the output, nothing's actually running yet because we're just about to execute that. And then you can see here that there are no more tasks to run. So there's no more tasks. We're going to try to steal a task. There's nothing to run. And then we're going to keep doing that forever and ever and ever. So that is how no routines actually work. It's incredibly, incredibly simple. The mechanism for no routines is creating closures. When we fork them, all we're doing is we're creating a new no-C thread. We're creating a new instruction stream, which is just this piece of instruction that we need to run. And all that is doing is just going to execute the closure when that no routine gets scheduled, right? So we push it onto the worker queue, and once the worker queue has executed its previous task, it's going to get a new task from its run queue. I'm now going to show you one problem with that, and why you might want multiple worker queues that steal from each other. The following can happen, right? Let me just change some things in the boot. There you go, boot.cpp. Instead of having one worker thread, we're going to start 2 worker threads, right? Actually, no, we're going to keep this at one worker thread. And after doing this, I'm going to create an infinite loop right here. And we're going to see that this infinite loop is just going to run forever and ever and ever. So we're just going to run the compiler. And remember, we're just running one worker thread. And you can see that nothing is getting outputted whatsoever. Like this asynchronous task is not running. Why is that? If we look at the scheduler, we can see that when it's running a thread, all that's going to be happening is it's just going to be iterating over the VM, right? It's just going to be iterating all over these instructions. So even though we fork something, we schedule something, if we look at the run queue and we only have one worker queue, the main thread is currently running. We've pushed in a new task for this no routine, but the main task is just in an infinite loop. So this would never exit. And because it never exits, we never loop back up to get a new task. Now, Go has a scheduler that can detect this. It can detect whether something is running for too long and it can suspend it. But in our example, we actually don't have any of that sophistication. So this thing is just running forever. So when we have one worker, we're actually limited in our throughput, because if someone has a really big for loop that is running infinitely, we never exit out from that function. We never exit out to actually pick up the new task. Now let's see what happens if we have now 2 workers running. If we have 2 workers running, worker 2, this worker has nothing pushed onto it, right? It's just empty. It's going to try to steal, if it has nothing on it, it's going to try to steal something from another worker. And this works out really well. So now what I'm going to actually do is exit this program. Oh, this program can't exit because it's an infinite loop. Let me just kill it. And now in the VM boot, instead of having it with one worker, I'm going to have it with 2 workers. And we're going to see something. We're going to run the, I need to rebuild the program. I wish I just supplied an argument that I could run the compiler with, but I have to compile the entire program again in order to use multiple workers. Now we're going to have 2 workers that are created when the scheduler runs. Now, when we run the compiler, we see that, hey, this actually gets run. Why? Because when we actually schedule it, I'm going to run now, kill this and run it with the debugger. When we actually schedule it, if I go into the VM, and I'm going to put it into the fork, opcode fork, and then I'm going to schedule the new thread. So we're going to just jump for all over these things, and I am going to debug this. We're creating a static link, we're forking it, and now we're going to schedule this new thread. When we schedule this new thread, we're going to push it into its own private worker queue, which is exactly what it does do. And then I'm going to put the debug point, excuse me, I'm going to put the debug point after it steals a task, right here. So we're going to schedule a new thread. Oh, I've missed it. The debugger was too slow. But what happened here was, and if I look at the main program, it's still correct. What happened here was another worker has stolen this task. And that's why you'd want a work stealing kind of design, because it increases the throughput of how many asynchronous tasks that you can run. The more workers that you have, the more parallelism that you might achieve. So if you have 64 cores, or have many cores in the machine, you can have each worker running, and you get the hopefully the throughput that's required. That's going to utilize all those cores. But of course, if each worker queue can actually be, the progress can be halted if the worker queue is just infinitely looping. So there's a task on the worker queue that's just infinitely looping, doing nothing. And so you get this, so you can get a reduction in throughput. Go prevents this from happening by just detecting whether a thread is running for too long, whether its virtual thread is running for too long, and then it suspends it and then allows the worker queue to then schedule something else. And this is how it creates a better fairness and better throughput for the amount of tasks that are asynchronously executed. But in my design, it's incredibly simple. You have multiple workers running and they just steal tasks, and that's how you can get parallelism. Now you can see that the worker queue1 is still going to be halted because it's still running this task. Even though tasks can be stolen, it's still running this main task, which is running forever and ever and ever. But that is the mechanism, and that's the simplest way that you can create a scheduler. And this is just virtual threading support, because you just have a OS kernel that's just running the worker queue in a loop, and then you can have multiple workers running, and that is how you can get virtual threading support. One more thing that we can talk about, actually now we're ready to talk about non-blocking IO, and how virtual threads are actually going to be the mechanism for facilitating non-blocking IO. Okay, let's look at the following example from the right hand side. And in this case, the VM boot that you can see, we're running with one worker. So we only have one worker thread running, and that means that we have one worker queue and only one worker thread that's going to pull off from this queue and then run the next thing. But here you can see that we first asynchronously run a no routine. We start a new task and we push it onto the worker's run queue. And all this thing is going to just say hello world from vthread ID, get virtual thread ID. And then we're going to printf from the main, and then we're going to sleep for 5 seconds. And then after sleeping for 5 seconds, we want to resume, and this print statement is going to be printed out. However, if this were blocking, if this sleep were blocking, then nothing else could run, because we would ask the OS thread, hey, just go to sleep for 5 seconds. And once that is done, then reawaken the OS thread. So the worker would be blocked because nothing else would be running, because remember, the worker is tied with the OS thread. If the OS thread goes to sleep, physically goes to sleep, then nothing else can run. However, we're not going to be doing that. First, I'm going to show you the demo. Remember, there's only one worker running. And even if there's a worker running, we can see that first is hello world from vthread ID. So this is run. Although this is scheduled, the next statement to run is this one. Remember, because no other task can run until a task finishes. If there's only one worker, there's no other worker to steal the task. So this main task has to finish before this can run. But we see that hello world from vthread ID, then we sleep. And then as the moment that we sleep, we see that, somehow this task can now run. And then once the sleep finishes, we get a notification that the sleep is done. And then somehow we're able to resume and then done from vthread 1. So I'm just going to show you that program again. So immediately hello world from vthread 1. So this is the first thing that runs. And then once we sleep, somehow we freed up the worker queue. We've parked, you could say we've parked this main no-c thread. We freed up the worker queue, we freed up the worker thread, and the worker thread is now able to somehow pull a new task from the worker queue and then run that and finish running that. Then we somehow get a notification that the sleep is done, and then we resume the main thread that was running. Virtual threading, right? We virtually are supporting threads within the system. The mechanism for registering events that you want, right, from the OS is you need an interface that the OS supports for non-blocking IO. So you register an IO interest or an IO event that you want notifications on. And this could be a timer event. It could be a socket connection event. It could be a socket connection event. It could be like, are there more bytes on this socket? It could be a socket incoming connection request, right? You can imagine it could be anything. It could be file is ready to read, file is ready to write. Now, in Linux, descriptors are always, files are always ready to read and write. But just imagine for now that you could actually get events when the file is ready to read. The reason why, because the file is on your machine. So, you know, the hardware is on your machine. So it's always ready to read and write. There's nothing that you need to wait on. Whereas a connection or a timer is something that you do wait on. You're waiting to receive a packet, or you're waiting to send a packet. So your incoming connection request, connection send packet, receive packet. So you can receive all these events. And the way that you do that is that the interface has to support a mechanism for registering these I/O events. Now, the standard interface that's supported in Linux is EPO. And you might always recognize this. In Windows, it's called I/O completion ports. In FreeBSD, I think it's called, in FreeBSD and Mac, it's called KQ or something similar. Basically, there's an interface supported in every operating system that allows you to register interest for certain I/O events that you're interested in. And then you can actually poll the OS for the status of these. And using that status, then you can actually run something else. And this is what we're actually going to do. When sleep is called in NoC, when we sleep and we pass in the number of seconds, the first thing that we do is, because we only support ePoll, and NoC only supports ePoll, it doesn't support Windows or KQ, so it can only run on Linux, or the versions of Linux that have this interface associated with it. And I think pretty much every distribution of Linux supports ePoll, or has the implementation for ePoll. But you can imagine that if you wanted a language to run on many runtimes, and you wanted to utilize non-blocking I/O in many different OSs, you'll have to support an abstraction for, you'll have to support Windows, and you'll have to use the I/O completion interface, because that's the only thing that's supported in Windows. And in FreeBSD and Mac, you'd have to use KQ. You wouldn't be able to use ePoll, because unless those interfaces were somehow supported in Windows and Mac, then there's nothing that you can do. You'd have to wrap around I/O completion and KQ if you wanted to use the same ePoll interface. But in NoC only supports Linux, or the distribution that has ePoll. And in the Docker images, it's Debian, and Debian has ePoll, so there's no problem there. So the ePoll interface allows us to register events that we want to receive for a descriptor. And a descriptor can be anything. It can be a timer, it can be a connection, it can be a file, it can be anything. And you can register your interest on ePoll. Now, once you've registered the interest, so let me see, ePoll register, that's not what the function is called, but we register that we want it to receive an event. Then we park our thread, the one that we're running, right? So this will be the main thread, which is what, once it's about to sleep, it gets parked. All park does is just it changes the thread state of the thread to parked, and then it unwinds the stack that allows the worker queue to then pull off the next task from the run queue, right? So we're just going to write long jump. I'll explain what this long jump is. And then we're free to actually run the next task, because we've parked this thread. Now, at some point, we need to poll ePoll, we need to poll the OS again for the status of everything that we registered, and we need to receive those events. So at some point, we're going to poll. And the OS is going to tell us whether a certain descriptor that we registered with, a certain event that we registered, is actually ready, right? It's actually going to return us a set or a list of events. It's going to return us a list of events. And the events is going to contain all the information that we need. That's going to contain whether a certain descriptor is now ready. Because remember, we register an event for a descriptor. When we poll it, we're going to receive that event object back, and it's going to have some information. One of the pieces of information is the thing that we're waiting on. And then we can resume the thread that was waiting on this I/O event, right? And then we resume it. By resuming, all we're doing is we're pushing that thread. We're pushing that thread back to its run queue, right? Because every worker has this run queue, we're just pushing it back. Remember when I spoke about NoC threads? The NoC thread has the instruction pointer, right? It has the stack of operands. It has a stack of operands. It has, of course, the thread state that we're going to change. All of this piece of information we can actually save, but because we're virtualized, we're running in a VM, there's not much we need to save. We just need to save the instruction pointer, and we just need to save the stack of operands, such that when we resume it, we're going to resume it from the next instruction, and we have to make sure that anything that we popped off before parking it, we can actually restore it. So we need to restore the context. It's just like how an OS might restore the thread state after a context switch happens. Right? So we're just going to look at the code. It's incredibly simple. We're just going to look at the code to see how this mechanism works, what happens when we actually call sleep, how do we register that interest with the epo interface, how do we then park the thread, and what is this mysterious long jump that's going to allow us to pull a new task from the worker. And then at some point we need to poll for the event. We need to poll to see if this event is ready. If that event is ready, then we can actually resume the thread. Now, remember that in our example that we have right here, that there was only one worker thread running. And even with one worker thread running, somehow we're able to achieve a level of concurrency within the system because we're non-blocking, right? We don't block on IO calls, like sleep. I'm going to call sleep an IO call, right? But we don't block on any IO calls. We park it and then we resume something else. So even though there's one worker queue running, we can multiplex across this worker queue. And that's what really makes it really nice to actually visualize at least how you can get concurrency. Now, concurrency is not the same thing as parallelism. Parallelism is when you're actually running multiple things in parallel. Concurrency you can achieve by just interleaving the threads. We're interleaving the virtual threads that we're running. It looks like I'm doing 6-7, right? Yeah. I wanted to put that in. so okay, there we go. Just to, again, visualize everything that's running. Initially, the main thread is pushed onto the worker queue's run queue, right? And that has virtual thread ID 1. We're just going to put virtual thread ID 1. Okay, so let me just actually erase that and put in vthread ID 1. So let me just put that here. So main has vthread ID 1, and that's initially what's pushed onto the queue because it's the main task. There's only one worker running, so there's a loop that's just pulling off from the task queue. So we first pull that thing off, and now because it's pulled off or decked off, whichever phase that you want, the worker queue is empty, and then we run it, right? We run the thread. We run the thread. Then we register the no routine, so we fork a no routine, and then we push that onto the worker's run queue. And that's going to have it's going to be a new no-c thread, which means it's going to have a new virtual thread ID, virtual thread ID 2. And this is currently on the worker's run queue. Now, it can't immediately run this because it's actually running its thread, but it is in the worker queue. Now, the next thing that it actually does is sleeping. It sleeps for 10 seconds. At this point, we register an IO event that we're interested in to the epo interface. We ask the OS, hey, the operating system, can you create a timer for us for 10 seconds? When that elapses, can you let us know, right? So we register that interest. Once we register it, we park our current thread. And then we long jump. Now, why do we long jump, right? You can imagine here that if you actually look at the call stack that's happening, is the worker loop is running, right? The worker loop is running, and then the worker loop calls get task, which pops it from the task queue, and then it calls run thread. Now, run thread is actually running this while loop, and then eventually it calls sleep, right? And then we call park the actual thread that we're running, and then we need to resume the next, well, we need to actually pop off the next thing, the virtual thread ID from the queue. Now, say we didn't actually have this magical function called long jump. If we popped off the task right here, can you see the call stack is still this? This is actually the physical call stack. And that's not correct. Like, once this function finishes, we don't want to then unwind the stack and then resume from here, right? This is what long jump allows us to do. We're going to long jump all the way back to the worker loop and resume from there, basically unwinding the entire stack because we don't want to call get task here, because otherwise we're going to keep stacking tasks recursively, and then when we unwind, we're going to be in a really weird state where we've unwound to this park thread point, and then we're going to resume some stuff that's happening here. We don't want that. We want a long jump all the way back up to this point. Now, long jump, the way it works is there's a sister function associated with it called set jump. Now, before we run a task, we set a jump point right here, and then whenever we long jump, it long jumps to the set jump point that we previously set. This allows us to unwind the stack immediately, and then at that point we can just get the task again, run thread, and keep doing that. That way we don't have this weird stack that keeps growing every time we want to run a new task. And that's going to be the incorrect stacking, because we don't want to unwind the stack and then somehow resume from this point. And that's what long jump is going to do. And now we're ready to run a new task. At some point we need to poll the ePoll interface to say, hey, are there any events that are ready? Poll, are there any events that are ready? If the events are ready, then I'm going to figure out whether there is, what thread was associated with that, what parked thread is associated with that event, and then we're going to resume the thread. All that is going to do is push that thread back to the workers run queue. So here we can see virtual thread ID 2 is now running. When that finishes, and we get the eraser, so it gets popped off. When that is finished, because virtual thread ID 2 has been popped off from the queue, or decked from the queue, and when that's finished running, we then poll for the IO event, and then we push virtual thread ID 2 back on, so virtual thread ID 1, which is the main thread, back onto the queue, because nothing else is running, it gets popped off, and we resume from the previous instruction pointer. And that's how we just resume a thread, and that's how we support virtual threading. Now we're going to look at how we're going to debug it, and hopefully we can see how that looks. I'm going to obviously skip across a lot of the pieces of code that support this, but this is essentially it. You need an interface that's supported by the OS that can tell you whether certain events are complete, and then at some point you need to poll it and then resume wherever you want to resume. Let's run a demo just to show that non-blocking non-blocking IO reads are working in practice. So here on the right hand side we have demo.io no-c. Here we create a socket object and we try to connect to some remote server. The remote server is some Python server that's running on the left hand side. All it's doing is accepting a connection, receiving at least 1 KB from the client that's sending it. Basically we're just saying hello server, and then it's going to go to sleep. And then after it sleeps, it's then going to send hello client back. And you can see on the right side that once we send the message, we're going to read from the socket. We're going to read from the connection that we connected to, so from the Python server. But the Python server is sleeping for 10 seconds. Now, if this was blocking IO, the entire worker thread will go to sleep. However, it's not blocking IO because we're going to register this socket with epo, and we're going to register it as non-blocking. So if there's no bytes available, it's going to tell us whether no bytes are available. We can park the thread and then resume something else. And when this becomes available, epo will let us know, and then we resume this thread from this point forth. Now I'm just going to show you the no-c VM code that is the read socket function, which is an external function. As you can see, we're just reading the number of bytes here. But here is where we have IO on socket. And IO on socket just either tells us whether it's failed, in that case there's an error, or it tells us where there's no bytes available. And in this case, we need to park the thread. Exactly the same mechanism. We park the thread, we register interest in some IO event object, and we park the thread. Once we park the thread, again, we long jump and we let something else run. The same exact mechanism, if we look at the scheduler, IO event loop, the same thing exactly is what it is here. We epoll for events relating to this socket descriptor. If it's available, then we resume the thread. And that is exactly how it works. So here I'm just going to open up this main.noc file. Here we can see that there's only one worker thread running. So if you look at VM boot, just to remind you, there's only one worker thread running, so one OS thread. Now we're going to initially fork a new no routine, an asynchronous task. That's going to push it onto its private queue. But because obviously there's no other worker threads running, nothing can steal it. So we're just clogged up behind it. then immediately when we do a socket demo, when you call this function, and again, can you see I'm just trying it because I don't care whether any of this fails. We're going to connect to the remote server and then wait to read the bytes. But because Python server falls asleep, this would actually block. Because it would block, we yield that thread and we let something else run. And it's the exact same mechanism. I'm just going to demo it to you now. The server's already running, so the Python server's already running. You can see immediately it's connected to the server, but it's then tried to read from the socket, no bytes are available, so it parks itself. Then now this can actually run. And once it's now ready, we poll the epoll event loop, and then we resume the thread, and you can see here that the response should be hello client got hello client. The reason why the last two characters are missing is because I'm only reading 10 bytes. And then we're done, as you can see here. This is exactly how non-blocking IO mechanism works in Go, and how it's actually supported. One thing I would like to just quickly mention, just before we wrap up on this, the scheduler code is incredibly small, and most of this is like constructor functions. Like, can you see here, I'm just creating a new worker. The actual implementation is probably like 200 lines. The epoll implementation is incomplete, so there's many bugs there because I don't handle errors properly. Because if a socket closes, epoll will let you know whether that socket is closed, whether the server closes it or the client closes it. You need to be able to handle those events and resume the thread correctly, right? And there's many nuances with epoll that you need to take account for, because the interface has many things that you can use it for. It is not the only interface available in Linux. There's, of course, in 2019, the new interface came out for IO Uring, and instead of you actually making a syscall always to the OS and asking, hey OS, can you tell me the status of these events, instead of you always making a syscall every time in a loop, IO Uring has a shared buffer that is shared between them. It's a memory map buffer that's shared between both the kernel and the user space, so both the kernel and the application. And instead of you making an OS call, you just read from this shared data structure within it. It has an IO submission queue and an IO receive queue, and you're just actually reading off shared memory instead. And it's way faster than you just making syscalls, because you can do that really quickly in a hot loop. Every time in the IO event poller, so poll, if you look at poll, where is this? Where is that code? And where is the code? Okay, there you go, one IO event loop. As you can see here, every time I have to make a call to the kernel, every time I call epoll wait. So this can reduce throughput, and this is where IO Uring should theoretically be a great performance improvement. It is the basis of the Tiger Beetle database that's become quite a sensation if you've been following it. A lot of their throughput is just based on their ability to use IO Uring. Now, just to conclude, I'm just going to conclude with one more thing, and one more project that I just want to show to you. The libuv project is an abstraction, provides this kind of non-blocking IO abstraction, and it implements every single interface for every OS that you can think of. So IO completion ports for Windows, obviously epoll for Linux, and KQ for Mac, and it also supports IO Uring. It also supports all these interfaces, and then depending on your configuration, you can just do that, and then you can just target libuv and then just use their standard interface. And depending on the OS, you don't really care, right? You just you compile and you link to the correct thing depending on the OS. libuv just does this automatically. Like if you're running on Windows, you just set a flag, and then libuv would use IO completion ports. But the interface you program against is the libuv queue structures and the libuv event loop structures. That's the project here, and you can look at that project. I believe the Node.js runtime is based on libuv, and I think also the C# runtime. I'm not sure about it anymore. Like the .NET runtime is also based on libuv. I am not sure if that's true anymore. The last time I checked that was years ago. But that is how you can actually abstract away the complexities of all of these interfaces. You can just take a dependency on libuv. Anything else I actually want to speak about here? Again, the source code is incredibly small here. You can just read that. There is no problem here. Oh yes, one thing I do want to just conclude with. Okay. Right. Okay guys, we're just going to show how this works with the debugger, because I forgot to actually show that when I did the explanation. I'm pretty sure I did it, but I can't find the clip in the edit. And here, this demo, we start a node routine, and then you can see just underneath it, we try to connect to a Python server. The Python server is, if I show it here, simple socket server. It's just this simple Python server running on port 80. It accepts a connection and then it sleeps for 30 seconds. And this is actually going to let us show the mechanism of non-blocking IO. So here we start a node routine, but because we have one worker thread, it can't run. We're going to try to connect to the Python server, and we're going to try to read some 10 bytes from the Python server. Because it's fallen asleep, those bytes aren't going to be ready. So we can at this point park the thread, and we're going to see how that mechanism looks like. The first thing that we want to see is first what happens when we connect a socket. So I'm going to run this program. Now initially when we connect a socket, because you can see no CVM, because it's an external function, we're just going to externally call socket.connect. We're going to create a socket. It is just using the standard C functions that are available. And then we're going to set this socket to non-blocking. And this is just going to set the descriptor to non-blocking. That way we can actually receive events with epo about this socket, right? So we're going to set it to we're going to set this to non-blocking, and now that this socket is non-blocking, right? And then we're going to register an IO event with that that we're interested in. We're going to create an event. It's just going to create an event object for us, and we're going to add the event to this data structure that's tracking all these events, and we're going to register that now we're interested in receiving we're now interested in receiving events for this descriptor. We're going to actually ask epo, hey, we're now interested in these events. These events are going to tell us whether bytes are coming in or whether connections being cancelled. All these different flags have different meanings. But now we're going to register that event with epo. And we're just going to jump over all of these pieces of code. And you can see that we've registered the event with epo, and now that's it. And you can see in the code here that here the next time we're going to read from the socket. So I'm going to have, this is also an external function called. If you see socket.noc, you see that these are external function calls. So here, the next time we see, we're going to read the socket, right? So we're going to play right here. So when we read a socket, again, we use the C functions to actually just read from the socket or write to the socket. Now, if there are no bytes that are ready, right? If there is an error, then we're actually going to figure out whether we need to block or not. Because the error code that's going to come from this read or write is going to tell us whether that call would block or not, because basically no bytes are ready. If no bytes are ready, then we park ourselves, right? So we save the operands that we want to restore when we're woken up, because here we've just popped up a bunch of operands. So here when we park the thread, we just pass in the operands that we want to restore when we're resumed, right? And here we just register the fact that we're blocked on this descriptor, and then we're going to park ourselves. Now all parking does is, again, it's just going to long jump to reset the entire stack back to the top of the worker queue. So if you look at this get task here, right here, initially before starting the loop, we set the jump point that we want to jump to. And this is a standard function that you get from C. And what this actually does, it just restores the instruction pointer and some registers for that CPU. And it should work for every single architecture that you want, because it's a standard C function. So here when we do the long jump, we're going to come back here. And now that we do the long jump, we're going to pop this node routine off from the wait queue. And then we're going to actually run that. Right, and you can see that something is happening, right? The next thing that we're going to do is we've got no other node routines to run because there's nothing in the queue anymore. We're now going to poll for IO events, right? We're going to poll epoll for IO events. So now epoll is going to tell us, oh, these are all the events that are ready, and these are all the new events that have come in since your last poll. Now we're going to figure out the IO event that's associated with that, because we keep a track of that. For some reason that the IO event status has failed. I'm not sure why. And then we're actually going to resume that thread, right? Even though the IO status has failed, we still want to resume it. So now once we resume it, we're going to resume that execution from this point right here. So again, we're going to restore the operands and have it run this function. So once we resume it, we just push it back onto the run queue. We're going to again read the socket, because we've restored the entire state of the program. We're just now reading and resuming from this point on. This no routine is now finished, so you can see that something's happening. It's on the screen. We're now going to ask again from the IO on socket to read. This one is actually going to, for whatever reason, we've transferred bytes, but we have an error. So the implementation is incorrect in this case. But regardless, it wouldn't block. There are bytes to read, and we just read out the bytes, and that's the entire program. That's basically how the mechanism works. You can see that there is a bug here for whatever reason, that the epo status, the event said it failed, but we actually read bytes from it. So that's probably a mistake I made in the implementation. So the implementation is not complete. You can see that hello client is coming back. So the implementation is not complete, but this is the mechanism that it works with. And that's how you actually have virtual threading support with non-blocking IO, and how you can just suspend a thread, you can park it, and you can wait on it for a descriptor, you can schedule something else, and then poll the epoll instance, or whichever interface you're using for IO. That's it. I hope that made sense. One final thing I want to talk about is the epoll instance itself. Now, we're using epoll as the interface to register events with the kernel. When initially we set up epoll, we have to ask the kernel to create this data structure for us in its own kernel memory. And it's going to allocate this structure for us, and it's going to use that to handle all these events. This is actually, you just create an instance, so you just call create epoll instance. Now this instance is shared between every single worker thread. Right, every single worker thread has this global epoll instance, and every single worker thread is going to poll this. Now this might cause a huge amount of contention now, because we have one epoll instance and many workers that are constantly polling to figure out if the event's resumed or not. There are bugs definitely in the implementation, because I don't think I even handle this case well. But the problem about having a private instance for each worker, let's say each worker had its own private instance, right? So we give each worker its own epoll instance, and that way it can just look at its own private epoll to figure out the readiness of events. The problem comes with stealing work, right? Because each worker steals a task, right? Each worker steals a task, so they can all steal a task from all other workers. Now, if we create a socket and that is happening on worker 1, we register that descriptor with this epoll instance. This epoll instance is the only instance that knows about these events for the socket descriptor. And each worker is just polling on its own individual epoll instance. So if this task is now stolen, say it gets parked and it gets stolen to worker number 2, worker number 2 now no longer has the information about the readiness of this socket descriptor, because it's in the instance for the first worker. So if you have private epoll instance, you can't increase the throughput, but it creates another problem, because the descriptors now need to be migrated away from this worker to this worker, such that when each worker polls the event loop, it actually gets the events for the task that is stolen, right? Poll event, and obviously this one's poll event. And this is the reason why we have a global epoll instance. That way you can never have this issue, because all workers, have the same instance, and all workers can receive events for all descriptors, because it's all the same instance. You can try to see if this architecture works. I haven't implemented it, but it seems quite interesting to do. The Go architecture for it as well apparently is a global epoll instance as well, so they don't do this. So they have a global epoll instance, and they have optimizations around to make sure that implementation has the best throughput. Again, if epoll was a bottleneck because you're making so many syscalls, IOU ring is going to be a really interesting thing to explore, because there are no syscalls. It's just the shared memory mapping between the kernel and your application, and you have these queues that you can actually poll from instead, so there is no context switching required. So that's really interesting. I'm not sure again if IOU ring is used in production. I mean, even where I work, I've never seen anyone actually use the IOU ring. Maybe internally, but externally for applications I've never seen it, or don't know if they actually are using it. And I'm not sure even if the engineers themselves know they're actually using it, honestly. But it's very interesting to use. Apparently there's so many security issues associated with IOU ring, so I'm not too sure about that. But that is something that you can look at for this. But that concludes our discussion on non-blocking IO. I really hope that made sense, because now we're going to move on to features.
to conclude the section on the runtime, I believe this is the final thing that I'll be speaking about within the runtime, is how do we implement locks and use the locks to have mutually exclusive sections, and how do we also use futures. And what I mean by a future is when we create a null routine, right, it actually returns a future, and then we can await on this future. If the future is not ready, then we park the thread and let something else run. When this async task finishes, it somehow wakes us up, right? And we're going to see how that mechanism works. So this is what I mean by a future. In every single language, there's always a concept of a future, because that's what you need, some data structure to represent the status of an asynchronous running task. JavaScript has promises. C#, I'm not entirely sure what C# has. Oh, it has task. That's the object that it exposes, and Java has the actual future. I'm not sure if they've changed it since last time I looked at Java was in Java 8. We're now in Java 22, and I have not used Java since Java 8. But in Java 8, they had this object that represents the status of an asynchronous running task. And it is the same in NoC. We need to know the status of an asynchronous running task in the background. However, when we await on it, we do not want to block the OS thread. If it's not ready, then we yield and let something else run. When it is ready, we want to be woken up, and then we want to resume, because that is the job done for this asynchronous function, and we can move on. Locks, on the other hand, or to understand how this is actually implemented, I just want to give a very brief introduction to how locks can be implemented using the atomic instructions. There's only one instruction that we'll speak about, which is the cas instruction. Compare and swap. This is an atomic instruction that compares a value here. I'm just going to say this is R1. Compares the value, what it expects, and swaps it with the value in R2. If it is this value, then it swaps it with R2. If it's not the value, then the compare and swap fails. And we can actually use this atomic instruction to implement a lock. So let's just say we have this lock object. And this lock object has an integer that says it's locked, right? A lock can be unlocked. So let's just say it's free if the value is 0, and it's locked if the value is 1. Now let's just say we have thread 1, thread 2, thread 2. And both of these, what these try to do is they try to take the lock, and they have a cas instruction that they're going to do. They expect the lock to be free. If the value is free, then swap it with mutex lock, which is 1, right? And both of them are going to try to do the same thing. Mutex free, and swap it with mutex lock. And then I'm going to write lock.cas. Right? The cas instruction is happening on this, atomically is happening on this variable. Right? Now, because it's atomic, the cas instruction is a hardware instruction. Exposed by, it's in every instruction set that there will be some mechanism to have this atomic swap. Because it's atomic, no two threads can both see it free at the same time, because one of them is going to see it as free, and it's going to swap it with this lock. And the next person that looks at it sees that it's locked, and the cas will fail. So this way we can only have one thread actually acquiring the lock, and then when it's actually done with it, it can just put the value free back, such that the next person that calls the cas sees that it's free and then can take it. Only one lock here can, so one thread of execution can acquire the lock. Now, depending on how many threads that you have and how many cores that you have, this might create a huge amount of traffic within the bus to actually acquire this lock, because the atomic instruction is expensive for that reason. And there's plenty of literature to optimize out how you might deal with this kind of contention. I'm not going to speak about it in this one. You can read about it more in the references section. There's amazing publications about concurrency with respect to these kind of atomic instructions. And there's so many algorithms in the literature that allow us to leverage hardware in a better way with respect to these cas instructions. But this is the way we can actually create a lock. Now, one thing I want to speak about is spin locking. Spin lock. A spin lock is while the lock.cas is failing, keep trying to acquire the lock. And that is all a spin lock is, right? Lock.cas is failing, keep spinning, keep spinning, keep spinning, keep spinning, right? Keep doing it until one thread sets it to free, and then someone else can acquire it, right? There's optimizations to make this while loop much faster, but that's the eternal mechanism of a spin lock. You're just spinning on a lock. Now this is very different than a sleep lock. A sleep lock is almost the same. It does the lock.cas. Both of these things do the lock.cas. If it finds that someone else has acquired the lock, then we're going to put ourselves to sleep in some queue that's part of the lock's data structure, right? When a thread actually releases the lock, we loop over the queue of waiting threads, and then we wake them back up, and then we allow them again to acquire the sleep lock. Now, the reason why you might have a different granulation of lock, if that's so much a word that I can use, why you might want to have a spin lock associated with a sleep lock, is there are times that you can't go to sleep, right? There are times you just cannot go to sleep, otherwise the algorithm won't function. And there are times where you only hold the lock for a very brief period of time. You don't want to actually go to sleep because the lock is going to become free very soon. But there are times where you hold the lock for a huge amount of time. Right? You're doing a lot of work with this lock. I don't imagine why you would do a lot of work with the lock, but there could be a time where you hold the lock for a pretty long time. And you don't want everyone else just trying to cause traffic on the bus by just trying to acquire it in a hot loop, doing nothing, right? Because this is still bound to some OS thread. So you're basically wasting resources trying to acquire a lock that won't be released anytime soon. So in this case, the optimization is you sleep, right? You just put yourself in a queue of waiting threads, and when the lock is released, all waiting threads are looped on and then woken up. This kind of mechanism of a queue of waiting threads is the thing that we want to actually look at today. It's going to be the mechanism of how we implement locks, but it's also going to be the mechanism of how we implement futures, how we can await on futures. It's pretty much the same thing. If we have a sleep lock, then we sleep until we're woken up by whoever releases it. And this is the same thing as a future, because in the future, you try to acquire, it's almost the same thing, you try to acquire the state of the future. If it's not done, then you actually want to put yourself to sleep, yield yourself, but add yourself to some queue, such that when the future is done, you loop over the queue and you wake up all those threads and they'll resume on from it. Again, non-blocking, in the sense that you do not block up the worker thread for any of this stuff. The OS thread is free because it yields itself, it puts the virtual thread to sleep, and then anything else can actually run. When it's woken up, all we do is we put it back to the run queue. That is the mechanism of how locks are implemented, and that kind of sleep mechanism or sleep locking is how we're going to implement futures. But I just want to show how locks are done within the language itself. Okay, apologies for the noise in the background. It's just someone's having a party downstairs. But here is the data structure that represents the sleep lock within the C++ source code, because creating a mutex, if you look at threading, it's an external. If you look at threading, create mutex, can you see it's an external, and it has this mutex object that's associated with it. It's just a placeholder because this object actually refers to this structure. And the way the placeholders work in NoC is we need this to compile, but the object actually can reference something else. And we can cast it back to this data structure whenever we need to actually reference the sleep lock. The sleep lock has two things associated with it, or three things. The mutex, right? That is the thing that actually implements the lock, right? It's either free or not free. We see that there's a wait queue associated with it. Now, if we cannot acquire the lock, then we want to be put on a wait queue, right? And then there's a spin lock associated with that as well, to atomically protect the wait queue. And remember what I spoke about spin locks? Spin locks, you might want them only for a period of time. And there are situations where you need the spin lock because you can't go to sleep. Now, we're going to explain just that in a way. Now, let's look at how the lock function is actually implemented within the runtime. Sleeplock.cpp has this. First, we create the sleep lock. That's what happens when we create a mutex. We just get this data structure back. Now, Sleeplock.lock is the implementation for the external function lock, right? First thing that we do is we see whether we can do a cas, and we see whether the mutex is free, and then we compare it with we see whether the mutex is free, and we try to swap it with our mutex locked value. And if it succeeds, then no one else has the lock. In that case, we can just return. In the case where it fails, and that means someone else has the lock, right? In that case, we want to acquire this spin lock, which is this lock that protects something. What does it protect? It protects the wait queue that you can see right here associated with it. The reason why we need a spin lock is because we actually can't go to sleep, because we need to be able to push atomically into this wait queue. The reason why we acquire a lock is we don't want to be in a situation where something unlocks and then sees nothing in this queue because it doesn't acquire the spin lock. So the spin lock protects us from parking. The spin lock protects us from the race condition where something's unlocked by some other thread and it finds nothing in the wait queue. So if you want to unlock, you always look at the wait queue by acquiring the spin lock first. But in this case, we could not acquire it, so we push ourselves onto the wait queue. Now let's see how unlock works. Right? Can you see, one thing that I forgot to mention is we push ourselves onto the wait queue and then we release the spin lock and we park ourselves, letting something else run, right? Let's look at sleeplock unlock. Sleeplock unlock first just has a sanity test to see whether we actually do have the lock. You can't unlock something that you don't own, although maybe it does need to be an error. In this case, I actually found one-time error. First thing that we do is we just store the mutex as free within this lock. Then we acquire the spin lock associated with it. The reason why we have to acquire the spin lock is because we don't want to be in a position where we've stored free and the other thread is pushing itself to the wait queue. So by acquiring the spin lock, we wait for this entire thing to finish before we can then look at the wait queue. So again, we look at the wait queue, and if it's empty, we release the spin lock, we're done. If it's not empty, then we look at the first thread that's waiting on the wait queue, and then we pop it off, and then we resume that thread, and we release the spin lock. And that's how the mechanism actually works, is exactly the same way. Now, I've written here, is there a need to wake up all the threads? I mean, maybe there is, I'm not sure. But I only wake up the first thread that's waiting, or the thread that's waiting the longest. And that is how sleep locking is implemented. There is a problem here, right? There is a problem where, and Go handles this with inside its own source code. There's a starvation problem, means that arriving threads that come in, if there's many threads that come in and they see that the lock is free, they will acquire it quicker than you can actually get it from these wait queues starting up. Because we wake up these wait queues and then we have to resume the thread. By the time that they're resumed, threads that are coming in that should have lower priority because they've not been waiting as long actually have a chance to acquire the thread. You can look at the Go source code that has this, and the Go source code has optimizations around it. It's quite confusing to actually understand, but I believe it's trying to solve this problem, this fundamental problem of starvation, of newly arriving threads that have not been waiting as long somehow manage to get the mutex as free. And that is how sleep locks are implemented within that one. One thing I finally want to talk about, well, there might be other things I want to talk about with locking, is the idea of re-entrant locks or recursive locks. So re-entrant locks or recursive locks. Recursive locks, depending on some literature you might read, it might use either name. Say we have a thread that takes a lock mutex here, and then it does some stuff, maybe it does an if statement or some other pieces of code here, then it acquires the lock again, and then it unlocks. It does some more work and then it unlocks the mutex. In our standard way that we acquire the lock, if you look at it here, I've drawn the same example here. In the standard way we acquire the lock, we first do the cas on the value, and if it's free, then we just take the lock and we put in the mutex lock value. So here we actually have acquired the lock, it's totally fine. Here we do some more work and then we acquire the lock again. In this case, we see that the cas fails because the value is not free, it's 1. And in that case, we spin lock and then we put ourselves to sleep. In this situation, we're going to deadlock because nothing else can wake us up because we are the ones holding the lock. The thing that's actually stopping us from this is actually the value for mutex 3 and mutex lock is 0 or 1. There is no discrepancy between if we're the ones holding the lock. We can't actually check that. And reentrant locks is a way that we support that. So in the NoC thread, we have the virtual thread ID, which is just a number. And then we can actually do the compare and swap on this ID. Now, if we see that the mutex is free, then we swap our virtual thread ID. And then when we lock again, all we do is we just check whether our thread ID is equal to the value of the lock. If it is, then that means we hold the lock and we don't deadlock. We just allow this. And I prefer this. Go does not have this mechanism because I'm not entirely sure why they didn't add this. It's not something like it's difficult to add or anything, but they didn't decide to have this kind of reentrant locks. I guess because in the code it's more explicit. You know, there's no side effect of acquiring a lock twice. It works exactly the same way in Go's model, but with recursive locking there is the side effect that when you lock twice, you don't do anything. I guess there's no side effect really in this situation, but I'm not sure why they didn't add it. But I prefer threading models or locking models that support this kind of reentrant lock mechanism. And Java has support for this with a synchronized keyword. Like you can have a function that's synchronized and then call another function that's also synchronized, and it's absolutely no problem. Okay, just to see reentrant locks at work, I've just have this example where we create the mutex, we lock the mutex, and we lock the mutex again, and then we unlock the mutex. And this is also going to let us be able to see what happens when we unlock the mutex as well, because I don't think I've given you a demo of this actually working. So initially we see whether we can lock the mutex. This is line number 7 right here. We see whether the mutex is actually free. If is the mutex value our virtual thread? This is how we're supporting reentrant locks. We see it's not, so we're going to do a cast to see if we can actually atomically modify it. Is the lock currently free? And if it is, then swap it with the mutex lock value, which is our virtual thread ID. And our cast succeeds, so we don't actually acquire the spin lock and we don't put ourselves onto the wait queue. Now, we're going to jump again because now we're on line number 8 and we're going to acquire the lock again. And we see right here that the lock, we're going to see if it's the value of our virtual thread ID. If it is, then we're actually going to return. We don't need to do the cast. And then that's it. And now I'm just going to put the sleep lock unlock right here. And there you go. So here we have the sleep lock unlock code. Here there's just a test just to see whether we actually own the lock. I mean, I might actually remove this. I don't think, maybe should not throw an error. But here I say you can't unlock something that you don't actually have the lock for. And maybe this is the correct thing to do. Here then we now put the lock mutex.store free. So we're just putting 0 in the value of the mutex. We acquire the spin lock and we check whether anything is in the wait queue. Again, we acquire the spin lock because we don't want to be in a situation where someone puts something onto the wait queue and while we're trying to pop something off, while the unlock is trying to pop something off. And we see that the wait queue is empty, so there's nothing for us to do. And if there was something inside it, we will take it off, resume that thread. By resuming the thread, it just pushes it onto a worker queue, and that's it. We release the spin lock and we're good to go. There are probably, certainly, maybe some really fine-grained concurrency bugs in here. I haven't particularly stress tested this, but this is the mechanism that supports lock-in and making sure that we can sleep lock as well. By sleep lock, we just mean that if we cannot acquire the lock, we just put it on the wait queue structure and just put ourselves to sleep, park ourselves. When something's unlocked, then it would wake us up. The one thing I do want to just talk about, I keep saying like there's one more thing that I want to talk about, is of course starvation. We've spoken about it just briefly with new arriving threads, but you can have a problem because there's no sophistication in the run queues themselves. So you can be in a situation where the thread that holds the lock never gets to run again to then release the lock. So everything else is waiting behind it. Now, in other schedulers, there is priority boosting for things that are holding locks, or if the scheduler can figure out that something is waiting on a lock, so for example, if another thread tries to acquire the lock and sees that it's being held by a thread that is not running, then it can boost its priority and get it to actually run. This is something that that is described well in the FreeBSD kernel, and it's in the references section as well. You can actually look at the references to see the video that's associated with that, and it's also in the FreeBSD internal book, the mechanisms that actually tries to solve this starvation problem of threads not being able to run. There's always going to be a starvation problem in the way the scheduler runs, because the queues, there are no priority in the queues, and this is actually a poor implementation of the scheduler. But you'd imagine in a real scheduler, you want different levels of queues with each having different priority, and then you either boost them or unboost them, basically meaning you either move it to one priority queue to another priority queue, depending on the context. And this is one way that you can actually have a priority boost for something that's waiting on a lock. You can actually get it to run, so you can actually quickly release its lock. And yeah, and that's one thing that you might want to consider. It's a really nice thing. It's a really nice problem to try and solve. Obviously, there's also the inversion priority problem. Is when you do have priorities, the thread that holds the lock might have a lower priority than anything else, and in that case it would never be able to run, because there's so many more high priority threads that are just running and hogging up the system. In that case, you need to boost the priority such that the thing that's holding the lock gets a higher priority, and that's where you kind of stop this starvation issue, where you're just waiting on something to unlock, which is never going to be able to run. But those situations come up as you're trying to stress test the scheduler, and again, the scheduler is incredibly simple, partly because for this really reason is you don't want to be adding the complexity until you profile a base level, and this is a standard thing that you do in an actual job, right? You don't have the time to implement the most complex solution, so you implement the simplest thing that you can implement, and then you iterate from there. One thing I forgot to mention is how the actual atomic is being used. I've just shown you that the compare instructions are done, but the actual atomic is implemented by the standard C++ library. Now you could implement the atomics yourselves by using the actual hardware instructions available to you. The actual lock instruction itself, you could actually do it yourself. You could write the assembly, but then it would be much more difficult to actually run this on a different architecture. Like if you're running this Docker image on a different architecture, then and you wrote the assembly yourself, then it probably wouldn't work, because you'd have to support every single architecture. At least using the standard atomic library does provide that. One thing that it also does provide, it provides a consistent memory ordering right here. And memory ordering or memory reordering is something that, depending on the architecture, whether it's Intel x86 or whether it's ARM, the memory ordering guarantees that the CPU provides will be different, and they could have really, really different consequences of you being able to implement a mutually exclusive area of code, because operations can actually be reordered. The CPU can reorder those operations, can reorder them, and two threads can actually see the incorrect ordering of operations that they might expect. Now, I'm not going to go into memory ordering at all, actually. But it is incredibly, incredibly fascinating. You can look at more into memory ordering and cache consistency. But just using the standard atomic C++ library, we can actually just use the standard functions, and it would always give us, at the very least, it would actually always give us the appearance that things are sequentially consistent. We would use the maximum ordering guarantees that can be available to us from the actual hardware. Now, the way it works is there's certain memory barriers and fences that are emitted as part of those instructions. Again, you can look at the literature that I have in the references for more. But this is the reason why. You can just make them yourselves, but if you do make them yourselves, you have to attack this problem of memory ordering. And again, I didn't have time to do that. And I actually might implement my own locks myself at some point. In the references, in the book, there's a whole section on concurrency unlocking, and I will put those references that you can look into it in detail, because they are fascinating to actually read. Now let's move our discussion to futures and how futures are supported. Let's remind ourselves what is in the noC_thread object. The noC_thread object has the instruction IP, but we're just going to ignore those fields. The two things that we actually want to look at is the thread state of it. We've seen that it has parked as a state when we park a thread. We know that the thread can actually finish, or it can be in some terminal error state, like if an unhandled exception was thrown. Along with the no-C thread, we see another data structure called the await handle. Now the await handle, all it has inside it is a queue is a queue of threads waiting for this thread to actually finish. When we create a no routine, future equals no function. When we create a no routine, we actually get returned back a future object. The future is actually just a wrapper over the forked no-C thread that we just created. Remember, when we do a no routine, we actually execute the fork instruction of code. That creates a new no-C thread. The future is actually this object that we have. Now, when we await on a future, when a thread awaits on a future, which is this new forked no-C thread that holds this closure, we first check whether this thread has been signaled or if it's finished. If it's finished, then we just get the return result from that thread. Excuse me. My apologies. We get the return result from that no-C thread, and that's it. However, if it's running or hasn't been scheduled or is not in one of these terminal states, then we actually put ourselves onto the await handle queue. And then we park ourselves. When this thread actually finishes, it just decks over everything in its queue, and then it resumes it. And that is just how futures actually work. We're going to now look at the source code to see how that works. Here we see that the no-C thread has this structure associated with it. We're familiar with the virtual thread ID, with the stack of operands, the thread state, which is atomic because it can be modified by different workers. So it has to be atomic. So we can see that it's created, ready, waiting, done, finished, or is in some error state. I can see here that there is no error state for this. I guess the signal state is going to indicate whether it's an error. Oh, I just missed a state. Along with this, we see that it has an await handle. This await handle has a spin lock associated with it, and it has a queue of threads waiting for this thread to finish. So on the right hand side, we see the following. We see that we start this no routine, and remember, for this example, we only have one worker thread running. So the main thread is running on this same worker thread. So now we fork a new no routine, we schedule that in, which just pushes it to the run queue. It returns a future object. Now, in our explanations, the future is actually just a reference to the no-C thread. When we await on this future, we just add ourselves to the await handle queue, and then we just park ourselves. We're just going to see how that mechanism works right now. So I'm just going to run the debugger. The first thing that we see is the fork instruction, because we're forking a new no routine. When we're forking a new routine, we create a thread, a brand new no-C thread. This, we're going to call it the forked thread. And we can see when we return it, what we push onto the stack is the actual forked thread object. It's just wrapped in this future. So if we look at threading.noc, we can see that here, right here, it's just a placeholder for this object, right? And now we're going to push this onto the stack. And if you go back to main.noc, we're going to push it onto the stack, and then it's going to be assigned to the storage value for future. When we await on this future, we're going to see what happens. Here we have if we look at threading.noc, we can see that await is an external function call. So here we're just looking at the external function call. The first argument on this await is going to be the actual future. And here, right here, we actually await. We call await on this future. So we can see, we're going to jump into how that looks like. We first do a little sanity check. We're not awaiting on ourselves. Basically, that's what we're saying. The first thing that we check is, has this thread, is the thread state at least signaled? Which means, is it error or has it finished? If it has, then that means there has to be a result associated with that await handle. We see that the await handle has the queue, but it also has a result, the result from this function, or it has an error, and the error from this function as well. And this is protected by the spin locks. Now, if it is the case, then that means that there has to be a result. But as you can see that because there's one worker running, this no routine cannot run until this is actually parked. The main thread is actually parked. We can see that we acquire the spin lock, and between acquiring the spin lock, we just check again, was this signaled? If it wasn't, then we just push ourselves to the wait queue. We push ourselves to this forked no-C thread's wait queue. And then can you see that we just put ourselves to sleep, we park ourselves, and that frees up the worker, and the worker is now going to execute this function. Now we're going to go back into the VM, and I am going to go to this function, signal waiters, right here. I'm just going to figure out where that big while loop is, because I want to close it. Okay. Now, after the VM has executed every instruction it can, the final thing that we do is we signal any awaiters. So this no routine is actually going to run, and it's going to signal awaiters. So let's just run that. And we can see we're running on thread v2. So now this thread is actually running. I put in a sleep just to show. I didn't actually need to put in a sleep. But here, now that this thread is actually finished, we're now outside the hot loop of the VM. There's no more instructions left to execute. Now we're going to signal the awaiters. There is no result because this is a void function, so we're just going to return null as the result object. Here now we signal the awaiters. We look at the await handle for this no-C thread, and we see whether there are any awaiters. If there are, we're going to update our thread state to signaled, and then we're just going to wake up every single thread and resume the thread. Resuming the thread just puts it back onto the run queue. And the next time it can run, it will run. And here we see that now that they've been woken up, so now this thread, this main thread, has been resumed and put back into the run queue. We now just carry on from that instruction pointer. We see we're back here. We check the await again. We see that it is signaled, so there is a result. So we don't park ourselves. And then we just get that result from the await handle and then resume as is. And that's just how we do non-blocking await on a future. That's how it works. The one thing I want to explain just before closing this debugger is that the await handle, if I look into here, we're going to get the await handle. The await handle has the result as well as some error object that might be associated with it, like if the user's thrown some internal error. The reason why we have this is to support this. Done waiting with result D, result. By having a reference to the result on the await handle, when the awaiting thread gets woken up, it can just get this result directly from here. And we can just run the compiler, and we can see that we're running on the thread, we're sleeping, 1, 2, 3, 4, 5. I should remove that sleep. Let me just actually remove that sleep entirely. Let me just here implement that, and then just run this guy. And then you can see we're running on vthread 2 because once we await, we park ourselves, we let this no thread run, and then once this finishes, it signals the awaiters. So the no-cvm signal waiters. In this case, when we signal it, we just store the result object, which was the final thing on the stack. Because this function returns 1, that is what's going to be on top of the stack. And that way, when we signal awaiters with that result, we can just add it to the await handle and then wake up every single thread that is waiting on this. When it waits on this, it just gets the result from the await handle and everything works exactly the same. So that's why you see done with awaiting result with result 1, because we return 1, just to show that we can return 10. We run the compiler, done with awaiting result 10. And of course, an await can fail because the actual no routine itself can go into a terminal state. Either someone throws an exception or a null pointer. In this case, we signal with an error. We signal the awaiter with an error, and then when we wake up, we just see that there's an error, and then we carry on as is. And that's all how the mechanism works for a future. It's just basically just a state of a running thread that you have a reference to, and that's exactly how it works. A future is just a reference to the no-C thread object, and we just use the await handle to wake up awaiting threads or put threads to the await queue. That's it. This is the final section on garbage collection, and this will be the final section of this huge long ass video, and I hope it has been useful or has introduced you to some of these concepts. At least you've been able to see how they might work with inside a compiler and how it might interface and create some executable code that you can actually run. But the final thing that we want to talk about, and the final thing I actually worked on the language, is introduction to garbage collection. Now, the garbage collection code is actually incredibly simple within the runtime. It's about 1,000 lines, and probably 700 of those lines are actually useful. and most of the lines are just asserts that the garbage collector is running correctly and hasn't corrupted itself somehow. Now there's two things that we're going to look at, and the main thing that garbage collection tries to solve is we don't want to free our own memory. We just want to allocate memory and let the runtime actually determine whether that memory is still being referenced or not. Is that object that we've allocated still alive? And the way we do that, the mechanism we do that, is by using a garbage collection algorithm called mark sweep. There's many algorithms to determine whether objects are alive, but the one that's easiest to implement and the one that's most intuitive to understand is mark sweep. You can layer a lot of complexity inside garbage collection, but we're just going to stick with the basics, and then we're going to build up our intuition from that. After this, we're going to look at how we can actually allocate memory. Now, allocating memory, getting bytes from somewhere, is very different to determining whether those bytes are still alive, whether a reference still exists. So mark sweep is the algorithm that we use to determine whether an object is still alive, and allocation algorithms are used to create actual objects from the heap, right? Okay. Now, what does it mean for an object to be alive? It just means that there is a reference to that object in the object graph of the program. Now, an object graph can become really big. So here we have x equals new person. Let's imagine that, actually, I am going to rename this to be not x, just to give it a variable name person. All right? Here we have person. Right, and then we're going to have person dot name equals new string. And then we're just going to give it a name, hello. You can see each time we're allocating some object, and then, person dot last name equals new string, and then we're building up the object graph of the program. Now I'm actually going to draw the graph just so we can actually see how the object graph might look. So here we have the person object P. P has two fields associated with it, name and last name. And those two things have a string associated with it. And remember, a string is just an array, if you want to look at the implementation. And the string is an array. And those arrays are just characters, so there's nothing that it points to. Hello just points to the array of characters. So the string just points to the array of characters. So here we can see that the object graph looks like this. So all of these objects are still alive because we can actually trace it from some known root. Now the root in this object is person, because that is actually the root of the graph. And we can just traverse the root to figure out other children that are still alive. And from those roots, we then traverse its own children, and we keep doing that until we traverse everything that we possibly can. So that is what mark sweep is attempting to do. It's attempting to find out from a known root whether we can actually find references to known children. So given a root, or given the roots of the program, we're going to trace, given the roots of the program, we're going to trace the object graph. We are going to trace the object graph, and anything that we find is considered alive, and we can't deallocate it. Okay, so we can see here that nothing here we can actually deallocate, because at this point, let's say at this point we do garbage collection, we start at the known root, which is person, and we traverse its left child, we traverse its right child, and then we see that both of these things, so we can reach them, and then we keep doing them until we hit some terminal child that has no children. So you can see that the graph structure, both in the AST, both in the type checker, always seems to creep up, and it's just a fundamental data structure that's so useful in so many different applications. And this is what it means to actually traverse the object graph, to find from a known root, trace the object graph, and everything that you find is considered alive. Everything that you can't find is considered dead. Now let's do the same object graph again. Here in this example, we're going to copy this. I'm going to copy this, I'm going to put it here, just slightly above here. Slightly above here, just zoom in right here. Let's say that person has also an age, and for all of these things, we're just going to heap allocate even integers, because NoC actually has no, everything is heap allocated from in NoC, all objects, whether it's integer or not. Again, obviously that's not something that you want, because it's useless to allocate an integer object, but everything just works like that, just to keep the simplicity of the garbage collector quite simple, because everything is heap allocated. I don't have to worry about a stack. So here again, we see that there's a root object called person. It has three fields, name, last, and age. Okay. let's say with the root node is P, and then we have name, last name, age. Right? And here, once, if garbage collection were to happen, we trace from a known root and we trace down all its children. Here, everything is still alive because there is a reference. There is a known reference to all these allocated objects that we allocated. Here, here, here. If we trace the object graph, we can actually find a live reference to it. Now let's say, after this point, person.lastName, we switched it to be equal null. How does the object graph actually look in this case, if we started from P? So P, well, assuming that we've just set it to null, P now has 3 fields. The name, which still points to the string that we've allocated, so it still points to hello. The last name here points now to null. And here we have age, it still points to the integer 1. Now if you were to trace this object graph, we trace it here, hello is still here. We found last name, but last name doesn't go anywhere because it's null, so there's nothing to trace from this point. And then age is still the same. We've seen that the last name object that we allocated here has no live reference associated with it. Given the root of an object graph, given a known root of an object graph, which is person, we cannot find a reference that points to this string. So this is now considered garbage. Garbage. We don't care about this object anymore, and this object can be actually reclaimed. Now the algorithm to do this is called mark sweep. So it's actually really, really simple. It's probably, if you want the simplest version of it, it's probably like 10 lines. And even in the GC collection, it's actually 10 lines. So mark is the first stage, and then the sweep is the second stage. So mark, what mark does is given for all, I'll just write it in actually I won't write it in mathematical symbols, for all known roots in the program, and we'll explain where a root comes from. For all known roots in the program, mark it, and for each child in that node, we're going to also mark it. By marking, we mean we just set some flag that says, hey, this object is now marked. And that's all mark sweep is, exactly what we're doing here. For each known root, we visit its children. And we mark it. We mark a node that we visited. And then for each of those children, we mark it again until there are no children left. So here we see P. P is now marked. This object that P allocates, actually I'll put it here, is marked. Name is marked. Last name is not marked because there's nothing that points to it. This child right here has no children. It's null. So this one does not get marked. This last name is garbage. And you can see integer does get marked. This is the first stage of mark sweep. For all known roots in the program, we mark it, and then for each child in that node, we mark it. And it's a recursive algorithm. So we keep recursing backwards until we end up in a child that either has no children, in that case, we just recurse back up. And that's it. That's the first stage of marking. Sweeping is the other stage. Sweeping goes over the heap, and if it sees an object that has not been marked, we can deallocate it. So mark is the first stage, sweep is the second stage. So for all known roots in the program, we mark them, and sweep just goes over the entire heap. And if it sees that there isn't a mark flag associated with that object, then it knows that object is garbage, right? And that is essentially all mark sweep is. The most difficult thing to understand about a garbage collection, even the simplest one, is how do we know what the known roots are of a program? How do we find out where the initial roots are so that we can traverse? Okay, let's actually solve that problem. So the first thing that we're trying to solve, because the algorithm is really, 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 really simple. The first thing that we're trying to solve is, given a program, how do we initially find the root? Initially find the roots of the program, right? How do we know to start tracing from person P, right? As in from this person object. How do we know that? Because that's a root in this example, but how do we know? How do we find this initial root? Okay, after finding a node or a root or any object, how do we then know what children that object has? How do we know what children that object has? children that object has. And this is really simple because if you know from the type checker, we have all of this type information. And in our objects themselves, we actually have some type information fields. What's the type of this object? Well, we can actually just refer to the layout and then figure out its children. So this point is actually really, really simple to do, right? Because we just ask the type checker, hey, give me the type information for this object. And then we can actually know its fields and then traverse over its fields. Really, really easy, really simple. And we're going to see how we can do that. That's probably the easiest part to understand. But how do we find the initial roots? Okay, let's just write a no-C program, okay? First of all, let's give every no-C thread its own heap. Just a place in memory, a huge block of memory. Let's say it just says 8 megabytes, because actually that's the actual number that I use. And from this 8 megabyte area, we can just allocate objects, but that's where the heap is, okay? But how do we first figure out where the roots are of this thread, right? Because we have the main thread running, function main. How do we figure out, initially when we do garbage collection, how do we find out the roots? How do we find out the objects that we can start tracing from? If you remember activation frames, then you know that the call stack of the program is created by stacking activation frames. And what does the activation frame has? It has the storage. And what is the storage? It's just the map. So to find the known roots, we look at the thread for each thread that's running in our program, and we say, hey, what's the current activation frame that you're running? Because remember, a thread has the reference to the current activation frame, which is the current function it's running. For each activation frame that's running, we look at the storage, and that is our first way that we can find the roots. Okay, let's just say this main here, x equals new person, y equals new person, and let's say garbage collection happens here. I mean, these objects are still referenced by these two variables, but what's going to be in our local storage for main's activation frame? Well, x is going to point to something, x is going to point to something, which is this person object, and y is going to point to something, which is this person object. And that's how we actually find the roots to begin with. We look at the activation frames for it. Now, why is it that the no-C thread has a reference to the current running activation frame? Let's examine this, okay? So let's say we have function main, and I'm going to draw the activation frames out on the side, okay? Let's say it calls foo, right? And then function foo is called here, and then foo calls bar, but then it returns from bar, and then at this point a GC collection happens. We're low on memory, we need to collect something, and the GC collection is triggered at this point, and we have to trace the object graph and figure out everything that's happening. So first let's actually draw out the activation frames. So in this case, main, I'm going to actually draw it like here, main called foo called bar, but then bar returned, and now we're in foo's activation frame, right? And at this point, after it returned, a GC collection was triggered. So when we look at the no-C thread, what is the current running activation frame for that thread? And what is the activation frame that's immediately fallen out of scope? Is actually bar. So because the no-C thread has the current activation frame that it's running, basically the current function call is actually executing. That is the first place that we use to look at the known roots, because there's no point starting at bar, because all the storage for anything that was stored inside the bar's activation frame is already by definition out of scope since we returned from it. And the no-C thread has the current activation frame associated with it. So main has an activation frame and it has storage. Foo has an activation frame, it has storage. A bar has an activation frame, it has a storage. But bar has been returned. And then GC collection happened after bar was returned. So this activation frame is no longer linked to anything. It's still referenced in the heap. All activation frames are allocated from the heap, but there's nothing that actually references it. Right. So what's the current activation frame for the no-see thread. It's foo. And remember, each activation frame has a reference to the previous activation frame, which is main. And this is how we start marking. We look at the no-see thread. We ask it, what's your current activation frame? From that activation frame, we then trace its storage. Right? We just loop over all storage locations within this map. Quite literally, we iterate over the map. Once we've done that, and for each location, we might need to recurse further, because this object might have more children, and we keep doing that until there's nothing to be done. And for each object that we find in this storage, we just mark it. And then once we've done that, we just go to the previous activation frame. And then we do the same thing here. And then we do that until there's no more activation frames left. And that is how we first answer the question of how we find known roots. How do we find the initial marking? How do we find roots that we can mark from? Okay. The second thing that we have, actually for now, I'm going to show you the source code associated with this part, because once you see it, it's just like, it's quite simple. Then we can actually start to determine how we figure out what children are associated with an object. In gc.cpp, you'll find all the garbage collection code and the allocation code. Incredibly simple code that's here. Nothing sophisticated about the implementation. Again, an objective of this language is to have actually a playground or a sandbox where I can actually iterate and add more complexity. But it's super, super simple. The first thing that we do is we find out all threads that are actually running within the program. Now remember, we have workers, and those workers run threads. Well, the worker also has a list of threads that he runs. We expose this just so we can actually iterate over all running threads. Now for each thread that we run, we actually mark its stack. It's exactly what we do. We first figure out the current activation frame that's running for this particular thread. Right? While the frame is not null, for each variable within that local storage, we're going to mark it. And then we're going to go up to the previous frame and then set that. And then for each local variable in that frame, we're also going to mark it. And this is how we maintain the object graph. So right here, right now, I am going to create something. Okay, in this example, you can see right here, we have the function main, which is allocating two strings, x equals something and y equals wicked. And it calls the function foo. And foo allocates two objects as well, x equals something, y equals wicked. And then we actually call the gc collection function. Now GC is going to happen when we're low on memory, but we can actually force it to happen. And it's just going to call the garbage collector directly. But normally garbage collection happens when we actually cannot allocate anything, or we've hit a certain threshold in memory utilization, and then we need to actually make sure that we clean up or reclaim the heap by figuring out which objects are still referenced and which objects are not. In this case, there is nothing that is garbage, because all the objects that we've allocated are still in reference. I mean, foo's activation frame is here, but it has not returned from here at this point. And these variables are still referenced because we haven't returned on the function. And these variables are, of course, still referenced because we haven't returned from foo. So nothing actually should be allocated. All objects should be marked. Now in this one, we're actually going to hit the debugger. We are going to run right here. Put the debugger right here. And remember, we are in main.noc. You see, when foo is called, we're actually going to call the gc collect function directly. I believe gc utils requires me to tell a gc log level. We're going to put gc.log level verbose, just so we can get all that information required. I've got the debug point on now in the gc cpp file when we garbage collect. So we've just called garbage collection right here at this point, and now we're going to loop over all the threads that are existing in the program, and we're going to mark the thread stack, and we're going to figure out objects are allocated. And this is how we figure out the roots. The first thing that we do is, given a thread, we find out its first activation frame that's running. Now, for this specific one, an external function still has an activation frame associated with it. This is so we're consistent with everything, and external functions can also allocate objects as well. We haven't looked deep into the implementation of some of the external functions, but this works exactly the same way. GC collect is being called. Obviously, the implementation is not here. We're just going to loop over the object itself, and for each local variable, we're just going to mark it. So inside the GC collect, there's a log level associated with it, which is verbose, and we're going to mark that. And there's no more other local variables associated with it. We're going to go to the previous frame, which is foo. Excuse me. And we see that the previous frame foo, it's foo. And we're going to mark that. And then for all local variables here, we're just going to mark it as well. So we see x is 1, and we see y is another 1. So we're just marking it. And then we're going to go to the final activation frame, which is main. And then we're going to mark all those objects as well. And this is essentially how so you can see here that it was just main. So we're just going up the call stack and then marking every single object associated with it. And then when we have no more call stacks to go up to, the marking stage is over for that thread. And then we go to the next thread. And because there's multiple workers, we go to the next worker, but that's it. There's nothing else to do. And at this point, we've now marked. Everything is now marked in the program, and now we can actually do a sweep. I have realized that we've only answered our first question. So before we can actually look into allocation, we've only answered our first question. How do we initially find the roots of the object raft? We have not actually answered the second question, is given an object, how do we then know what children is within that object to then traverse it even more? Remember, the mark sweep algorithm is just a recursive one. For each known root in the program, we mark it. For each child node, we also mark that. And we keep doing it until we hit a terminal node, a node that has no children. Now, how are objects represented in no C? Remember, there are these following objects inside no C. The no C int runtime object, the no C double object, the car object, all the primitives are of these objects. And of course, we've looked at the no C struct container object and the no C vector runtime object, which is just an array runtime object. Right? Every single one of these objects has in it this runtime object container header, which is spelled incredibly weirdly right here, but it's just the header for it. Now, if you look into the runtime object right here that we have, every single object has this header, the runtime object container header. It has two fields, the type number associated with it, and also the runtime object type. I guess I could just have one field that gives me everything that I need, but I've just have two fields, which makes the object allocation quite expensive because I have extra fields for no reason. But here the runtime object type tells me, hey, is it an n dimension vector? Is it an int bool double car? Is it some other object? Is it a struct object? Given the fact that it's a struct object, what we can do next, if it's a struct object, then we can actually look at its type number and then determine from the type checker the fields that are associated with that object. And then we can actually traverse it, right? So this is where type checking and garbage collection have to work together. We need type information to be able to determine the fields of an object. And we see that the no-C struct container has these fields associated with it. Using the type checker, we can actually iterate over all these fields and then recursively mark them. The no-C int runtime and the double runtime and all these primitive objects are actually terminal objects because they have no children. They just have the value associated with it. But the vector object, which is just an array, we're just going to loop over the entire array. And the no-C field, so the no-C struct container has these fields. And we're going to use the type checker to determine that. And then we're going to recursively keep doing that because the mark sweep algorithm is recursive. If I can find it here. The mark sweep algorithm is recursive. So for all known roots in the program, we know how to find the roots. We're going to mark that object, but for each child node within that object, we're also going to mark it. And it just recurses back up onto itself. Where are we? There you go. So the no-C container objects. We're now going to see, let's look at one final example just to bring home the marking part of the algorithm and how the type checker gives us type information. Here we have a struct person, and remember the type checker is going to make a type layout for this, a struct layout to be particular, and then it's going to have all the fields and all the memory offsets that's within that field. So this will be memory offset 0. Let's make another one actually. Let's put height and this will be memory offset 1. So the type checker would know where this information is. Now, this object will be represented as a no-C struct container object. So if you look at the runtime object for this, when this object is allocated, we're going to allocate this object, and each field is going to be this offset, referring to the age and the height, which is also going to be heap allocated. So here we're allocating a person, and then we're going to garbage collect. Okay, let's just run the debugger, see what happens. There is a function called get cannot be resolved. Why is that? GC utils. Oh, sorry, garbage collect, there you go. Okay, let's just run the debugger again. Enum value does not exist. Why? What is the value called then? GC utils, verbo. Let's put. There you go. I spelled it wrong. Okay, now let's run the debugger again. Okay, now here we have we're going to actually mark that thread stack. We can see that the first activation frame we're just going to jump over because it's the activation frame for the GC collection function call. We're just going to jump over that. We don't really care about that. But the next frame we actually do care about, which is the mains function call. So you can see here the frame associated with that is the main. And we're going to loop over all the variables. So the first variable that we see is x, which is this person. And now we're going to mark this object. Okay, it's not null. The object has not been marked. We're going to mark it. And now we're going to switch on its type. We know that this is a struct object type. We're going to ask the type checker, give me the struct layout for this. The type checker is going to return the struct layout. And we're going to iterate over the fields from the struct layout information. We see that there's two fields in this. The first field, if this would move, the first field is the age, and the field offset is 0. So now we're going to mark that object, and that is an int runtime object, so we're just going to jump over that. And you can see there's nothing to do, there's no children for the primitives. So we're going to jump over that. Then we're going to go over the next field, now we're in here, and also that is the field for height. And this memory offset is the memory offset you can see is 1. So again, the type checker has the struct layout information, and we're just going to use it to mark. The same thing happens, it's a primitive type. So again, there's no leaves associated with the primitives. And now we're back up, and now we're finished traversing this object graph. And now that's entirely done, that's marking done. I hope that's brought the idea of marking and how we found those routes. And from those routes, how then we traverse the complicated object graphs. The one thing that maybe didn't make sense is how we traverse the array. I do not think, at the point of recording this right now, I have not explained how arrays are represented within the language, and I might skip it. So I would, if I have not explained it earlier, please look at the source code. It's just a fat array, basically, and we're just going to iterate over them, and the array has a length associated with it. But this is the first mechanism of mark. The second thing that we're going to now do is, now that we've marked the object, how do we determine what objects we can actually sweep? Sweeping is the second half of marking. Basically, if an object in the heap has not been marked, then we can actually reclaim it. At this point now, we can introduce allocation, right? Because in order to return memory that hasn't been marked, we need to understand how to allocate it to begin with. And then we're going to bring it all together in the end. We've now understood the first part of the mark sweep algorithm. We figured out how we can actually trace routes of the program. The one thing that we could not go into right now is how we actually sweep such that we can reclaim the memory that was not marked. Now, how do we first allocate memory? In order to allocate memory, let's imagine we have a really big block of memory that we get given somehow. Okay, we'll come into how it's given, how we get this initial block of memory first. But we have this block of memory. From this block of memory, we can actually allocate objects, right? So let's say the user wants an integer. Now we're going to actually be very specific to no-C. Let's just say the user wants an integer. And remember, integers are actually allocated from the heap. This will be a no-C int runtime object. It would have the header associated with this information. And then obviously we have the int value. When we want to allocate this object, we ask the no-C alloc, which has the same interface as malloc. We pass in the heap, and we pass in the number of bytes. We pass in the size of this runtime object. This is how many bytes we need from the block, how much bytes we need from the heap, right? So the size is no-C int runtime object. And this will be, let's just assume that, I don't know, this is 10 bytes or whatever. I mean, it's not 10 bytes, but let's just assume that it's 10 bytes. Now, from this big block of memory that we have, that we don't know where we get from right now, we're going to give out 10 bytes from this big block of memory, right? When we get this, when we get it. And now this memory is in use, right? When we allocate another integer, we also give another 10 bytes from this block of memory. Let's assume the integers are just 10 bytes. When we allocate something else, we also just take chunks of this piece of memory and we just give it back to the program. And the program then just uses the chunk that we gave and everything works as normal. We allocate a piece of memory and everything else works as is. We just give the bytes back and then just cast it into the correct object and everything works the same. Now when we give, and this is actually now what we can call, this big block of memory that we actually take bytes from, this is the heap. We haven't looked at how we initially get the heap of memory, but assuming that it's just a big block that we're taking out chunks, that's what we actually do. Now, from the heap, when we actually give a chunk of 10 bytes, what do we need to record with that when we actually give it? There's a piece of header information that we also use. So we do give 10 bytes back, but we also take just a bit more for some bookkeeping that we need to do, right? And this is a header. It's part of the block that we get given back. Although the user requests 10 bytes, we actually have to take in more to fit in this header information. Now, what is inside this header of the block that we're going to give back? There's a magic that's in here. There's a size. How big is the block that we've allocated? It's 10 bytes, so this would be 10 bytes. We'll come back into the magic just in a bit. And then there's also the bit flag. Is this marked or not? Marked or not marked, right? Why do we need this magic header? Now this magic header is just some value that we have, dead beef, just some bytes that we put in to it. So we also allocate this many bytes as well as the 10 bytes, we have to allocate this header as well. And that header is going to contain a magic number, which is in hex, I've written it, but we could say it's dead beef, the size, which is 10, and the bit flag, which is marked or not marked. So the actual header that we have is way more than the number of bytes we allocate. So in this picture, it actually will look probably like this in terms of ratio. So much information is taken by the header. But when we return the object to the person that's allocating this, so we can see that this person wants a int runtime object, we actually don't return the address of the header, we return the address right here, because this is at the point of the address that they care about. Why do we need this header, right? And how does this refer to sweeping? Here we have, I'm just going to copy that entire heap right here. We're going to put it right here. Here we've allocated 4 chunks, so 4 integers from it. So each block has, let's just zoom out. Each block has a header, right? And the actual bytes that the user is going to use, but we have a header here, right? And remember, in the header, we have the size, we have some magic, and we have whether it's marked or not marked. And we always allocate from this big heap chunk. The reason why we need to know and have this header information is to support sweeping, right? Because sweeping, the first thing that we do is we mark an object. Okay, given an object that we have here, as we loop over all these objects that are in referenced, right, we can just set the bit flag in the header because of all the objects start from here, right? Just before that there is the header, and then we can actually set the bit flag on the header. When it comes to sweeping, we can actually iterate over the entire heap, right? We can iterate over the entire heap, and anything that does not have the bit flag as set to marked, right, and it's in use, it's been allocated, is actually free, and we can actually give that back, right? So as we're iterating over this heap, we see that there's a block here, a block here, a block here, and another block here. As we're iterating over this heap, we notice that if an object has not been marked, inside its header, the mark bit will not be set. So that means that we can actually reclaim it back, right? So that means that this, let's assume that the chunk 2 has not been marked. That means that we can reclaim it. So during the sweep phase, we can do this. Now, why do we need this magic header? Why do we need this value, dead beef? It's actually, as we iterate over the heap, because it's one massive block, we actually are gonna iterate it by starting at the heap. Each header has the size associated with it, right? And we're gonna add, from this point, the size of the header plus the number of bytes allocated to get to the next chunk. Now, when we arrive at the next chunk, we just check whether the magic is the number that we expect. If it isn't, then that means that we've gone off the heap, right? This is known as heap parsability, the ability to parse a heap. The magic allows us to do that because we can check the next piece of chunk just by getting the header, the size of the block that's been allocated, and then just incrementing it to get to the next block. And then we just check whether the headers are correct. If it is, then we keep doing that. If the bit is not set, then we know that this piece of chunk is free and it's not in use. And that's, let's imagine the following way where we can allocate from a large heap. Right? Initially, let's assume that we have a massive heap, well, not massive heap, but let's just say it's 1,000 bytes, and that's how much memory that we have. Right? This is all fixed and contiguous, like it's all one chunk. Right? It's all addressed from 0 to 1,000. Right? The key data structure that we use to actually take out memory from this heap and chunk it out is something called a free list. A free list is a linked list of free nodes. The free here implies that every node here refers to some chunk in the heap that is free. Right? Initially, we have one node that's free in this free list, and that is the entire heap because it's not being used. When the application starts up, the heap is not being used by anything until the first allocation is made. When the first allocation is made, we look into the free list to find a node that is big enough to actually meet our allocation request. So say we wanted 10 bytes. There's only one node here, but we look at the size and we see, oh, it's big enough to actually allocate. We're going to actually allocate from this 1,000 byte chunk, right? And then we take this chunk off from the free list. We take it off from the free list. Right? We take it off from the free list. And then we allocate this 10 bytes right here at this point, right? This is added here with the header information. The header information contains the magic number as well as the size, right? Header, and it contains the header information and the object that we're wanting to allocate. So both things are allocated here, right? And the remainder, we put it back on the free list, right? So we've taken that node off. What's the remainder? Let's assume that the header plus the bytes we allocate is altogether 20 bytes because we've requested to allocate 10 bytes, but let's just say the header also takes 10 bytes. So the remainder is 9,000, I wish I'd choose a better number, 9,980, right? And let's say we keep doing that. We keep allocating these small chunks. So every time we look and we allocate, we find out the first node in the free list, and then we take it from the free list, and then we chunk it out, and the remainder, we put it back on the free list. Let's just say we do that for a couple of allocations, right? So our heap, remember, our heap is contiguous, but our free list is referencing nodes, referencing addresses within that heap. Eventually, let's just say that the free list has one node. Let's just say it's 500, right? 500. And the 500 it refers to is this block right here, which is still free. Garbage collection has not happened. So there's only one node that's free, and that's the remainder that's right here. Let's say garbage collection happens, right? We do our first mark stage. For all objects, we mark them, right? We loop over all objects in our object graph, and then we mark the bit flag that we have in the header, right? Header, bit flag. Right? Let's say that the only thing that isn't marked right here is this object, right? This object is not marked right here, this third object that was allocated. I'm just going to erase it out. This was not marked, right? Now, when it comes to sweep, we start at the heap starting address, which is address 0. We look at the header information, and remember the header has a magic number, which is called dead beef, that we know that we need it in order to jump over chunks, right? So we start at the header, we see that the size is 20, We see that it's marked, so we don't do anything. We then jump over to the next piece of memory that was allocated. We also see that it has a header and it has a size, and we see it's marked. Cool. We look at the next object that we allocated. We see that it has a header, it has a size, but it's not marked. So this piece of chunk is free, right? And we add this piece of chunk to the free list. So how big was this? Let's just say it's 20, because the header and the object size is 20. We'll just say it's just 20. So now we have two nodes in our free list, right? It's a linked list of 3 nodes. This object and now this object, right? And then we jump to the next part. Again, we see that it has a header and it has an object size 20, and it's in use, as in it's been marked. So that means that a reference still exists to this chunk, so we cannot put it back on the free list. And of course, the final thing is already in the free list, right? So there's nothing to do there. And this is the mechanism of how we allocate from a contiguous area of memory. We use a free list data structure to hold chunks of memory that are free. Now the word free is implied that every single chunk here is free. Now let's say another allocation request comes in, right? Allocation request comes in, which is 50, so let's just say which is 10 bytes, right? We have 2 nodes here that refer to, we have 2 nodes here that refer to 3 things inside this free list. The 500 chunk, which is right here, and the 20 chunk, which is right here. Now, depending on your allocation scheme, you either have best fit, first fit, or worst fit. Basically, of these 3 chunks, which is the best fit, which fits the best, that uses the most amount, that utilizes the most amount of memory. We can see that the best fit right here is chunk number 20, because it leaves 10 bytes unallocated. Whereas here, this will be the worst fit. Or you can do first fit. It's just you find out the first chunk that you can allocate from, which would be 500. You take it out. So let's just do first fit, because we just iterate over the list such that we find the first node that matches our size requirements. Here we see it's 500, right? We take it, we see that it points here. We take a little chunk out from here, right? And then the rest is actually put back onto the free list. So initially we take it off from the free list. So now the free list only has one thing inside, which is 20. We allocate however many bytes we need to. In this case, it's 10 bytes plus the header. And then the remainder, we put it on the free list. And we put it at the end of the free list. We always put it at the tail, because it's a linked list that we add, and we add it at the tail. And I believe it was 500 bytes. So this will be now 490. And this would still be referring to this section. And this is how we can actually get allocation done from the heap using another data structure called the free list. When we sweep, we just sweep over the heap. Anything that's not marked, that we couldn't mark during our mark phase, we just put it back to the free list. And I hope that makes sense. We're going to look at the, we're going to debug the code to see how that works.
So now let's look at the key data structures that make this possible. The free list data structure and how we actually, what's the data structure that's going to contain information about the header for a block. We can see in allocator.h, we see that the first header field. And remember, when we allocate a block has the bytes that we've allocated with it, as well as the header. And we can see that the header has all these fields associated with it. We have the magic number. Again, the magic number is just going to let us know whether we are on a correct block. But if we are on a correct block, as we're iterating, we just check the header and we just check if it's correct. If for some reason the header is not correct, either it means that the heap's been corrupted, right? Some part of the heap has been overwritten because we expected to see the magic number there, or we're just off the heap. And depending on the context, this could be totally fine. Then we have the size of the heap. The size of the block. So here we have the object that's allocated as 20 bytes, so the available size would be 20. We have the size of the previous block associated with it, so each one has the size of the previous one associated with it. This allows us to merge 2 free blocks together to create one larger block. Just knowing the size of the previous one lets us do that. And then we have the actual bit flags. And we just store these bit flags in a 32-bit value. This could actually be 16 bits or even 8 bits actually. It doesn't need to be 32. It can just be that, because we don't need the additional space, because we're only using 4-bit flags, so 4 bits. You can see that each bit here, the 0th bit, the 1th bit, the 2nd bit, and the 3rd bit and the 4th bit, all refer to different things. There's 1 bit for if it's in use or not, and 1 bit for the mark, and that's what we actually use to switch on, to flip whether it's marked or not. And when we scan, the heap. When we sweep the heap, we're just checking whether each block has this marked field or not. If it's not marked, then we know that it hasn't been traced. It hasn't been marked by the marking phase of the algorithm. So then we can actually put it back to the free list. And we have these other bits that are just to do with fixing bugs within the GC. The GC has a limitation where if I don't have these bit flags, the heap ends up becoming corrupted, and there's a reason for that, and I'll explain why. And we can see that the header is actually incredibly large. I've just decided to use size T, which is going to give me 64 bits, or 8 bytes. So I don't know why I decided to use such large numbers for these things, but because of this, and I maybe it's totally fine to change them to a 32-bit value. So just unsigned int 32, and this can be an unsigned int 8. The reason for that, I'm not entirely sure why I use such big ass numbers, but using really large numbers for the header creates a really large struct compared to how many bytes you might want to allocate. Now, when I did some really standard profiling, I found out that the ratio of header to the blocks I typically allocate in my tests is 80% is taken on the header, and only 20% is actually the data that I need. Now, because the tests I did were just allocating really small objects that really didn't do anything, like integers or a really small struct, this just skews the ratio quite heavily. But if you allocate larger and larger objects, obviously the ratio is going to get better. But regardless, there's a huge amount of space taken in the header, and that's why you actually want to use smaller fields that don't actually take that much space, and you want to reduce it. And using bit flags is just a way of actually reducing the amount of bits that you need, because you can just use that number and just take out bits from it, and each bit can represent something. But regardless, the struct header is very big. Now I'm going to look at the free list data structure, which again we said is a linked list. And remember, the free list is just a linked list of free nodes. Each node is a heap node. In the garbage collector, it's called a heap node. And each node has a header, and as well as the data that's after it. And you can see here that the free list is a linked list of heap nodes. It's actually a doubly linked list, meaning that each node knows its next pointer, and it knows the person, the reverse, the guy going backwards. Again, this means that the node that we allocate from has to contain this information. So it has to contain the header, and it has to contain the next pointer and the previous pointer, because we also need from this block, this block represents this piece of memory. But it also needs to be able to be put in a free list, because the free list itself, you can't create a free list without allocating memory. So the memory itself has to come from the block that you're allocating from, which is a bit weird, but we'll just see how that is. And that's a heap node, right? So after the header, anything after the header and after this, the address after this heap node, here you can see here, right here, is where we're actually going to return the data of the object. So when someone allocates something from the allocator, we actually allocate the size of the heap node plus the amounts of bytes that someone's requested, and then we take that and then we give that back. But the object that we give back is actually the address at this point. And the free list, again, it's implied free because all the nodes that are on the free list are free. That's why it's not called, I don't know, a block list or anything like that. It's called a free list because all the nodes in the list are free. So those are the key data structures behind it. Firstly, we're going to look at is how we initially get memory from the operating system, and how we initialize these data structures that are for it. So first we have the initialize heap function, and it's going to actually initialize the first bytes for the heap. It's going to allocate an 8 megabyte block. How do we initially get the 8 megabytes that we want, or however much we actually want? The initial heap size is 8 megabytes. So first we allocate from the OS. By allocating from the OS, we just ask the OS using the system call mmap to give us this many bytes, to give us 8 megabytes. Now these are just flags that you can use because the underlying memory that you get back is virtual memory. It's not actually physical memory, and the OS actually would give it in 4K chunks. But as far as we're concerned, it looks like a contiguous 0 to 8 megabytes memory address. We don't really care, but behind the scenes actually, the OS is going to split up this. It might split up this 8 megabyte chunk that we've requested into 4KB pages, all spliced across the user address space. So they actually, physically, they might not be contiguous, but virtually they are contiguous. And this is the power of virtual memory. But as far as we're concerned, it looks like a block from 0 to 8 megabytes. How the OS then allocates it behind the scenes is entirely up to the OS. But virtual memory is incredibly powerful. And it's also, I think, the coolest thing about operating systems is just the power of virtual memory. We don't really care much about whether we don't really care much whether the operating system is going to really actually give us a whole 8 megabyte chunk contiguously. As far as we're concerned, we're just going to assume it is, because as far as we're concerned, it is, because the memory that we get back, its virtual address space is it's going to look from 0 to 8 megabytes. Physically, it might look entirely different, but we don't care about that. So we call the mmap system call to get this, and there's some flags that we have to make sure that the block that we get back from the operating system is readable and writable, and it's just contained in our user space. It's not shared between any other applications. If you wanted to share memory between two applications, you can, and you can just call the mmap system call and actually make it public, and you can actually share a piece of block between two processes that are running on a system. And this is how I'd imagine IOU ring to work. It's how you share a buffer between the kernel and the user space. But regardless, we don't need that because it's going to be our own memory for our own application. And protection read, protection write. There's also another flag that allows you to execute stuff that you might want to put in there. So you can actually just write code into this block and then execute code from there. And this is how jitters would work. All right, you just write you compile directly to assembly code, and then you stuff the assembly code into this block of memory. And because it's marked as executable, you can just jump into it directly, and there you go. You have a jitter. We're going to come back into guard pages a bit later, just to talk about something called heap corruption. But that is how we get the initial page block from the operating system. Now, from this page block, remember, we don't have any other memory in the system. This is the only memory that we get back. From this, we initially allocate. We carve out the free list from this. We just take a part of this block and we allocate the free list from it. Before we then initialize the rest of the heap and initialize the free list, we need to actually take some bytes from this block of memory, and that's going to be the free list. And that's exactly what we do here, right? We initialize the free list by just taking, by just actually physically marshalling those bytes and storing them in the free list. And the first head, so the first node of that free list is going to be the first node in this heap, which is going to be the rest of everything here after the free list allocation. That's going to be the first node in the heap. So initially we get this block. So from this first block that we get from the operating system, we take out some bytes to actually embed the free list in it. And that's why we just, you might see in some publications called embedding the memory, because we actually just take it from the block that we allocate. The rest is actually the first node in that heap. So just like this picture, it's actually 8 megabytes minus the stuff that we've allocated. And the first node in that heap, the first heap node that we allocate from it and we put to the free list, starts here. That's the address of the first heap node. And the header is the same, right? The available space is this entire 8 megabyte chunk. So I'm just going to say 8 megabyte minus whatever the free list was. But for now, we're just going to assume, I'm just going to say, you know what? I'm just going to say 7 megabytes just to get the maths easy. We're just going to say the free list takes 1 megabyte, but of course it takes only a few bytes. And the magic is added to this particular block, and that's it. And that's the first in the free list. That's the first node. That is the first node in the free list. We have this 7 megabyte thing. This points to this piece of memory, right? You can see that the heap is not moving. Like it's just the contiguous address space that we're allocating from, but the free list is referencing nodes or referencing addresses in the heap, and those things are just represented as heap nodes. So this entire piece of memory is the first node in the free list, and by definition it's free because nothing's been the heap just been initialized, so there can only be one block, and because nothing's been allocated yet. Now from the first allocation, all we do is, instead of looking at the heap, we look at the free list. We ask the free list, hey, is there a node big enough for my allocation request? If it is, take it, use it, and any space left over, add it back to the free list. And it's exactly like what we drew here. Right? So this is how we initialize the free list data structure and how we initialize the heap. We get memory from the OS. We then use that memory from the OS to carve out the free list. And it's a bit weird because the free list is embedded inside the memory we've allocated. But if you're familiar with Siege, you're just basically casting the piece of memory and just taking the free list out and then doing some arithmetic operations just to find out where the first node's going to start, because it has to start after the free list. And then there you go. You just add that node to the free list and you're good to go. The free list is allocated from the memory you've just got from the OS. Again, just a quick note on virtual memory. If you're not familiar with it, you can actually make an allocator that makes no consideration to virtual memory, because as far as you're concerned, or as far as I'm concerned, the memory that we get back is just physical memory. But actually it's virtual memory. But we can just treat it like it's physical memory. There are implications for that, and we won't go into those implications right now. But the way we do that is we call the mmap system function call. We just ask it to create we ask it to allocate however bytes it can allocate. If there's no memory available, and always there's memory available in virtual memory, there's always memory. It almost seems infinite. That's why there's a consideration that you have to make, because you can always grow your heap by just asking the OS for more and more bytes, because it would actually just keep giving you more and more bytes. Those bytes that it allocates might not be resident in memory. It actually might be on disk, and it might have to be paged in. And in that case, you're gonna have a performance struggle. You can grow your heap infinitely, as much as the paging mechanism allows. I don't know how much is configured, how much disk space it can actually use, but theoretically, from what I know anyway, you can always just ask for more and more virtual memory. But that can cause performance degradation, because the extra memory might not physically reside where it's supposed to be. It might just be paged in from disk. But that is really, really powerful. Now that we've initialized the initial size of the heap, and we've actually allocated the free list from it, which now has just one node inside it, which is this, it actually would be the 8 megabyte chunk for the mathematics here. We're just going to say it's 7, but it has one node inside it. How then do we allocate the first object that we want from this free list? Remember, we use the free list to actually allocate. We don't allocate directly from the heap, because the free list again is embedded inside the memory, but it contains references to chunks in the actual heap. So let's see how the first object can be allocated. Here we just have a struct which contains x and y, and we allocate a new person object. Remember, the code generation that's for this is just going to be new followed by the identifier for this person, so the type identifier for this person. We search the struct layout, we find the size, and then we're going to ask the allocator. Okay, so I'm going to put in a debug point. Let me actually remove all the debug points here, and you can see I've got the debug point on the VM pointed to new. So let's just run that. You can see that now we're going to be allocating this person object. We're going to search the struct layout for this person object. We found this struct layout information, and now we're going to create this object. So now we're going to create a runtime object. We first get a reference to the heap, and now we're going to create the struct runtime object. I'm going to put this code actually here. Okay, so we can see the code on the right hand side. First we get the size of the struct. So how big is this struct? Now the size of the struct is going to be 24, because there's actually 2 pointers as well as some header information. So it's going to be the size of this plus how many pointer fields that there are, how many no-C fields there are. And each no-C field is a car, but because it's a car pointer, it's going to be the size of the pointer. So the size of the header plus 2 pointers, because even integers are just heap allocated. So these are just going to be pointers to actual integers. So we're first going to allocate that, and then we're going to call the allocator, and we're going to request this many bytes from the heap. So we're going to go into the allocation function. We're going to ignore this pin thing for now. We are not going to talk about guard pages just yet. So we're just going to now allocate from the standard way that we allocate. We first get a reference to the free list, which is right here. Right? It has one node inside it. And then we're going to find the first node. And here's just an assert to make sure the free list doesn't become corrupted. We're going to find the first node that's free. So we're just iterating over the free list's nodes, and we're going to find the first node that's available. There's only one node inside the free list. Or in this case, there actually should be only one node. And you can see here that there is no next and there is no previous. It's just the one node, and it has a massive size available. I don't know why the size of the previous data is 24. That's a bit strange. So I might have allocated something already from this heap. But regardless, there's only one node inside this free list. So we find this node, first available. So it's a first fit algorithm. You just find the first node that can actually fit the request that you wanted. And from this node, let's expand this. From this node, if you could not find any node, then we actually garbage collect. Regardless of garbage collection, I grow the heap. And this is because I had this really weird performance issue, but regardless of garbage collection, I would frequently always garbage collect. So there was the thing I was playing about with. If you garbage collect, and even if you collect some memory, I still grow the heap. So the frequency of garbage collections is less frequent, because you can imagine that you have an allocation pattern that just allocates and then you free, and so you just found out that half the memory is utilized,
half the memory is only utilized, so you free half of it, but then the allocation pattern just keeps coming up. So you keep doing this with your heap, and growing the heap, in theory, should stop you from actually doing repeated garbage collections for the same allocation style. So regardless, I just tried to grow the heap because I wanted to test whether anything happens with it. There was no performance improvement, but again, the playground is there. The playground is there for me to do some performance measurements. That's what's going to make this project really, really fun. We returned that selected node because we found a node. We don't need to do garbage collection. If we did not find a node, again, it just assumes that, you know, there's no data available, so we should start garbage collection. We should start the mark sweep algorithm. And now we just get the selected node and we figure out if there's any space left over, right? So after allocating however many bytes we want to allocate, we figure out the space left over in this block. If there's space left over, we then just add that after splitting it. We add that to the free list. We just make a new node from this, from the space after what we're going to allocate, and that just gets added to the free list. So you can see the free list is now going to have one node still because this node's just been taken off, and this node is now going to point to this chunk. And so the free list always contains references to free nodes. And then the object that we return back, right? I'm just going to ignore all this other nonsense. Ignore that. So we're just adding the new block to the free list. And the object that we return is not the object that's starting at the heap nodes at the header address. We actually want to jump over it and then return the point of where the actual data is going to start. If you remember that the heap node has to be embedded within the memory that we allocate, because it has to contain the header information as well as the next and previous pointers, because that's also going to reference from the free list. So that's also going to be used to actually create the free list. So we can't actually return data at this address because that's not where the data starts. If we did, then if someone were to write, they would write all these fields and then corrupt the heap. And so we return it after this point because that's actually where the data starts from. That's why you see the return object position that we have right here is whatever the node is that we get from the free list plus the size of the heap node. So we just jump over the first bytes for the header, the first bytes for the heap node, and we return this object position. And then now that we return this object position, we're now returning from the allocation, and we can see that the struct object is allocated. It's not null, so that means the allocation has not failed. Now, if it were null, then that means the allocator failed to allocate an object, and after garbage collection, it still failed to allocate an object. And even after garbage collection fails, we grow the heap, and even then, it still failed. And this means that, you know, there's no memory actually available in the system. Although growing the heap just actually asks for more virtual memory, so in this situation, it would never ever run out, or it should never run out. But regardless, we're always gonna, if allocations fail, then certainly there's nothing that garbage collection can do to reclaim memory. And this is, there you go, you get that address back, and then you can just cast that to the struct container that you wanted. Before this is the actual heap node header, right? Because remember, the return object address is after the heap node, which is this struct. And then we just cast it to that struct. Right? For each field, we then allocate the object. Now, the default runtime object is if it's an integer that you see right here, if the cast is an integer. If it's an integer, we just create an int runtime object, which does another allocation to create the size of the int runtime object. That creates another heap allocated object on the heap, and it returns a pointer, and then from that pointer, we just store it in the field. So all of these are actually, again, we get the bytes from the allocator, and then we just point to these objects. We just update the fields of the struct layout to point now to these default objects. And this just allows us to support objects that have integers that have a default value, because we don't want integers to be null because that doesn't make sense. But because everything is heap allocated, technically you can write something is null. Although the type checker should prevent that. I'm sure there's a situation where you can actually say an integer is null because everything actually is allocated from the heap, regardless whether integer or a boolean. One thing that I like to mention, if it's not one of the primitives, we just return null. Like there's an object that we allocate that is just for the null object, and these are just default values. So if there was like a person field here, then this would be null. There's no default object that we allocate for this, it's just null, because that suits the programming model that I want to have anyway. And then that's it, there you go. We're gonna come into what unpinned is later, so we can see we've allocated another object. I've just jumped into it. Let me just get back out here. Because for each default object that we're creating,
we're allocating that integer runtime object. You can see that we've allocated each field. I'm just going to jump onto it, jump out of it. And then there you go. Now we return the struct object and everything's allocated, and that struct object is now allocated, and we push it onto the struct. That's how allocation works. And remember, each header has the bit mask, whether it's free or not free. We're going to do mark sweep again. And this time I'm just going to call GC collect. And we're going to see how the mark phase now uses the bit mask associated with that header to then track if it's been marked. And now we can look at the sweep phase to actually look at all these chunks of, to see how we can reclaim chunks of memory. We are now ready to understand how the sweep phase is going to work. We've looked at how blocks are allocated, and now let's see how the sweep phase is going to work such that we can return unused blocks back to the free list. The free list is a linked list of unused nodes or free nodes, nodes that are free within the heap. So references to areas of the heap or chunks of the heap that are free. Here we've allocated a person object. We've seen how that's allocated using the allocator, and now we can actually run a GC collection. Now we know what's going to happen in this case is just when we're going to walk for every thread in the system running, we're going to loop through its activation frames, and for each activation frame we're going to mark its storage. We're going to jump over the first activation frame because that's the one for GC collect. We're going to see the next one right here. So for each local variable we can see that this is person. You can see that this is person, and we're going to mark person. Now we can see what happens in the mark one. And now we can actually set the marked bit flag on this runtime object. And remember that every object has this container associated with it. So a person object will be a no-c struct container. I wish I called it no-c struct runtime object, but it's called no-c struct container. So every object can be casted to this header. But remember the bytes that we always return is the position is just after the actual information that contains the heap node. So the heap node is just above it, which contains the header information, the size, everything like that. So all we have to do is when we set the mark bit flag is we just have to do just an arithmetic operation to get the address of the runtime object, subtract it. You can see what happens here. We just subtract it by the size of the heap node, and then we get the node address. And you can see I'm just doing casts everywhere. So this code is really ugly, and I don't use any of the C++ features to to do reinterpret cast or anything like that. I just cast it like C style way, and then we get the heap node back. And then from the heap node we have the header which contains the bit mask, and then the mark bit flag is on bit number 2. So we just set that to marked, and it's now going to be the value of that is going to be 1. So this is just the bitwise operation to set it to 1. And then we keep doing that for the rest of for every field in that person object. And I'm just going to now unwind the stack. So you see we've now done that for every single activation frame in the thread. And now we're going to do it for every thread in the system running, but there's only one thread running. There's only one worker running. And now we're ready to actually do the sweep phase. Again, because each thread has its own heap, and we're going to go into that slightly while we don't have a global heap. Each thread has its own heap. What we're just going to do is we're going to iterate over every single node in the heap, every single node in the heap. And we're going to actually minimize a lot of the code here. And I'm just going to say, if it's not marked right here. You see, if the node is not marked, then we actually free it. Freeing just puts it back to the free list. If it is marked, then we can't free it. We can't put it back to the free list. All we're going to do is we're going to reset the bit mask for it, the bit flag for the marked bit. We're just going to reset it back to 0. So when the next mark phase starts, we just start the marking phase again. If we did not reset it, then it will be reset to 1, and it will just never be deallocated because it's always going to be there. So we have to reset the bit mask. Now and that's it. And then we just iterate to the next node. And when we iterate to the next node, it's just the macro, but we're just going to get the next node address from the current node. So we get the current node that we're looking at, which is the start of the heap. And all we're going to do, if I just go to this one, is to get the next node of it. It's just the current node plus the size of the node, and then we're going to jump to the next block that we've allocated. And that's how we iterate from it. And that's it. The bit mask allows us to, so the header value allows us to just check whether what we've jumped to is actually correct, because we should always be able to jump to another part of the heap. If we've done some addition and we've landed somewhere that doesn't have the magic value for the heap node, then we know that we've either corrupted the heap, in that case the magic should always be there, or we're off the heap. Now, in the implementation that I have, I never use the header to figure out if I'm off the heap. If I cannot find a header, then that means that the heap has been corrupted. Some node, for some reason, has had the header
rewritten by something else. Either there's some problem inside the way we've allocated, or the way I've returned the object address, or there's something else that's happening which is hostile to the heap. And that is the mark phase. So that is the sweep phase done. That is the essence of the mark sweep algorithm. Again, for every thread running in the system, we have multiple workers. Each worker has its own thread list of threads that it's created. Because remember, you can fork no routines, and then that creates a new thread. We mark the thread stack, and then once that is happening, again we do the same exact sweep phase. For each thread, we now sweep. We go over the entire heap. And then for each object that we have that's allocated from this heap, there could be many small objects. We iterate all of them. We iterate over them, and if the mark bit has not been set, then we add it back to the free list. And the next time that an object allocation happens, the free list should be bigger, because all these nodes, there may be many objects that are fallen out of scope, and in that case, that the free list should have all these nodes attached to it. Now, if garbage collection happens and it turns out everything is still in scope, everything still has a live reference to it, then there's nothing that we can do. In this case, we just grow the heap. We just, again, allocate more memory from the OS, and we just grow the heap. And then we just link in that new block that's allocated. And that is essentially it. What I'm now going to talk about is detecting heap corruption and why NoC threads have their own private heap. What does that give us? And yeah, there's many things that I haven't explained within this, not line by line, but again, I recommend you to read the source code. It's really simple to read. One thing I want to talk about is detecting heap corruption, which is really important as we actually write out an allocator anyway, because you can have a bug that somehow you've given a return address back to the application that is not the correct return address that it's supposed to be. Let me just zoom in here, right? The way we do that, there's two ways that I attempted to do that with guard pages, and then asserts all over the heap, asserting heap integrity. I'm going to talk about guard pages right now because they're actually really cool and they use the power of virtual memory. Whenever we allocate a block from the operating system, what we can actually do is we can set that piece of memory to actually be readable or writable, or we can actually just have it not to be writable or readable, meaning that if any application touches this address, then it causes an interrupt and then the application crashes. And so we get that segmentation fault that we're reading somewhere off from an address that we're not supposed to be reading. Guard pages is a way that we can actually do that, because what we can do is when we allocate some block from the OS, we can allocate another page next to it that we can call a guard page. This page is not readable or writable. We just ask the OS, do not allow anyone to read from it or write from it. In the specific guard page that we use, we actually allow people to read from it. We actually don't allow anyone to write from it. What this allows us to do, in some case where the application is running and we've allocated some memory, if the application somehow tries to write off the block that we've allocated, this will now be writing into the guard page. The guard page is exactly next to the operating system. What this allows us to do, if someone's written over it, the application now no longer becomes in a corrupted state. Because if you write over it and you don't have a guard page, the application now continues, but the entire heap has been corrupted potentially, but the application now just becomes buggy. What you want to do that is immediately when you do that, you want to be able to have the operating system let you know that, hey, something has written into some memory address it should not have written into. This could cause the entire application to become buggy, crash the entire program. And at least when you do stress testing, you can actually figure out that there's something that hits the guard page. Okay, now how does this look like? Use guard pages. Let me just see that. There you go. When we get a page block from the operating system, right? And initially it used to work better when I used to have really small pages, when I used to just have request 4 kilobytes on the OS, because each page is always going to be 4 kilobytes. That's the default size for anything that you allocate from the OS, regardless whether it's 10 bytes or not, or 20 bytes or not. It's always going to return the page size, and the page size is normally 4 kilobytes. And you can read more about virtual memory as to why that is. But regardless, if we are using guard pages, which is a flag that we have to set, if we are using guard pages, the first block that we allocate from the OS is here. Then we allocate another piece of memory right next to it called the guard page. And for this guard page, we ask the operating system, protect it and only allow the application to read from this area. Do not allow it to write from this area. So we allocate this much memory, but right in the middle is the guard page. And then we ask the operating system, hey, put this protection on it such that if someone writes into it, then we're going to cause a page fault. And this is going to send it to us, and then it's going to be a segmentation fault because we should not be writing into this memory region. This allows us to detect whether some part of the heap has been corrupted. The only problem with that is that because the operating system creates, you can only get the minimum size that you can get from the OS, regardless of the request size that you ask for, is 4 kilobytes. So even if you ask for 10 bytes, you get 4 kilobytes. So that means that the guard page has to start after the first page that the operating system gives you. So the operating system always gives you, regardless. If you ask 10 bytes, it will give you 4 kilobytes. So if you wanted guard pages, you have to allocate 8 kilobytes because regardless, the next page is always going to be 4 kilobytes. And then you set it to, you set the guard page for that. So it doesn't really work that well because that means that a block that you have, that you get, if you want to use guard pages to detect heap corruption for every single block in your node, it has to be 8 kilobytes because it has to have the guard page right next to it. And it doesn't scale as well. So guard pages is a really nice mechanism for detecting heap corruption, but realistically, it doesn't scale. It's only something that you can use in debugging. You can't obviously use in this production because you have to allocate a huge amount of memory from the, your allocation has to use the entire page along with the guard page in order for that to work. So this one, I didn't implement it fully, but it's something that's really, really interesting. And as the garbage collector gets more and more sophisticated, I might add more mechanisms for that. The second thing is asserting heap integrity, which is a cheaper check, but it's actually quite a nice check. Within each node, of course, we have the heap node. We have the header. And then we have some data, which is the no-C object that we have. However, once this data is put back into the free list, we are going to put data in ourselves, which is just some value. It doesn't matter what this number is, but the number that we use is phi. And this is going to let us know whether this heap node is free. So when we get this heap node from the free list, it should have this value inside it. If it does not have this value inside it, then that means that somehow we've got a reference to a block that's being used by someone else. And that should never ever happen. So let's just look at what this is. Assert selected node. Right? We get the node, right? And we first check whether the header is the magic, and that's all correct. And we check that the node is not marked because how can we get a free node that's marked? And then we check whether the data inside it is of this free constant, which is OX phi, which is a 32 byte value, 65,262. We check whether it's that value. If it's not that value, right, then that means that somehow the free list contains a reference to a node that has data after it that is probably a no-C object. Right? How did this come up into the free list? It is so useful to have this because you can detect heap corruption every time you get something from a free list. Again, on production mode, it's going to be expensive for you to do these asserts every single time. Allocation might be really hot, really frequent, so you don't want these asserts. But for debugging, it's really, really good to detect heap corruption as you're writing out some of the algorithms. This one is my favorite one, and I actually read this from Windows internals. They do the same thing. You can read the Windows internals book. It's in the references section as well. And this is how they also detect heap corruption. Guard pages don't work quite well because you have to allocate a huge amount of memory for each block. You have to always allocate the size of the page plus the guard page, and that has to be the size of your block. So if you can see, if we use a guard page, right, you can see that when we allocate, if we're using guard pages, the node that we actually have, the available size, let me see if I can figure out the return address for this node. If you use guard pages, can I figure out what this is going to be? End address of selected node. Okay, yes, there you go. The only thing that we have to do is the data has to be aligned at the end of the page plus the guard page. So the guard page, let's assume it's, because I don't use this part because it doesn't work that well. But so here's some block that we allocate, which is a 4 KB of writable, and it has the 4 KB of guard page. So this is something that you can't write into, and this is the block that you have to use to read from. Even if you allocate 10 bytes, right, you have to use the whole 4 KB. But the block, in order for you to detect that some write is going to happen into this guard page, the return object address that you have to give has to be aligned at the end of the 4 KB page, just before the guard page starts. And at least this is how you detect it. Guard pages honestly never worked. Although it was a really nice way to do it, I never could get the implementation to work. And I decided that I'm just going to leave it here because I might expand upon it and use it later. The thing that worked the best out is the assert free list assert selected node, where we check the value of the free list node is of value ox phi phi, ox phi, ox phi. There you go, the free constant, right? When we free something, we're just going to write into this, and we're going to write the value into that block. And when we get it from it, we're just going to assert that that value is correct. And that's how, for now, I'm detecting heap corruption. And it works out, this particular thing works out really, really well. And yeah, it was always detecting bugs. Let's now think about heap allocation in the context of no-C threads, in the context of a multi-threaded environment. Obviously, no-C supports forking virtual threads. And how do we increase the throughput of allocation? By actually using private heaps. If each no-C thread has its own heap, right, that we have has its own heap, then we can actually increase the throughput of our memory allocation. Why does that increase the throughput? Let's see. So we have multiple threads running, and each one has its own heap. Initially, the heap is 8 megabytes before it starts to grow, right? So we get 8 megabytes. When a program actually allocates, it's always running in the context of a no-C thread. So when it actually has an allocation request, instead of coming from a global place that we allocate from, we can just allocate it from its private heap. The reason why we do this is so we don't need to have any locking whatsoever. Imagine that we had a global heap, right? So we had one global heap. If that were the case, and multiple threads wanted to allocate from this global heap, we'd have to take a lock, because we needed to protect the data structures that actually are used to track allocation, which is the actual free list, right? We need to actually protect the integrity of the free list. And if you have a global heap and all these threads come in, they will take a lock on the global heap, allocate from the global heap, and then allocate this free list. Append whatever they need to from this free list, or take whatever they need to from the free list, and then they return back. So you get less throughput because you're going to be spending a lot of time actually locking and releasing locks. So no-C threads have their own private heaps. And normally how it's done is, in an actual allocator, you have layers associated with it. But there are no layers in no-C, but initially you might have something like this. Each no-C thread has its own private heap. Private heap. There is still a shared heap that anyone can access from. Right? If you fail to allocate from your private heap, and there's no locking required because it's your private heap, no other thread can actually reference this heap. If you fail to allocate from your private heap, you get it from the shared heap. You take a lock on some shared heap, and then you take the allocation request from there. I am not sure why it's done like this. I can only imagine that doing it this way allows you to actually reduce the amount of memory that you use in the private heap. Because you can imagine if you have no private heap, and this is the way no-C does it, we just allocate more memory into the private heap. But you might be in a situation where you cause fragmentation. Basically, each no-C thread has allocated more memory than it's actually using. And you want to actually have this memory that it's using, and you want to share it with some shared heap, give it back to some shared heap. And this way we can actually reduce the amount of fragmentation. We can improve the utilization of the memory that we allocate. Otherwise, if we let each private heap grow and grow and grow, at some point, it's going to have so much memory. If a garbage collection happens, just imagine that this becomes 800 megabytes, right, of private heap space. And this also is like 800 megabytes of private space. A GC collection happens, and we found out that after the GC collection, we only use 100 megabytes. That means 700 megabytes is left unused, but it's private to this heap and it's not being shared, right? Then that means that this guy, to get another, let's just say this one actually needs 700 megabytes, it's either going to allocate, let's say we don't have a shared heap, it's going to allocate another 700 megabytes. So although there is space in the system, it's actually inside a private heap. So having a shared heap allows you to actually give back memory to some shared data structure. And then when someone wants to allocate something, instead of allocating it from the OS, it might look at the shared heap for it. This allows you to improve the utilization of memory. Otherwise you don't have memory, otherwise you will have memory blow up. And no-C suffers from memory blow up because there is no idea of a shared heap between them. But the reason why I have it is because I wanted to see how much throughput that you can get just by private memory allocation compared to one global allocator that you have to take a lock on. Now, what's the problem with having private heaps? There is one problem that we have. All no-C threads that are running in the program are running concurrently. because there are several workers. Each worker is running some NoC thread, right? Because each worker runs a NoC thread, there could be a garbage collection that happens inside it. When this garbage collection happens, we could just garbage collect privately and then try to free up the private heap. But because we have this shared memory model where threads can actually just reference data from other threads, we have to make sure that we garbage collect all threads at the same time. Otherwise, we might assume that some shared data no longer has a reference, and then we might deallocate it. So let's just say we have, I don't know, X is being used here. X is 2, okay? For some reason that we fall out of scope, but we've shared this value 2 with this NoC thread, right? This 2 was allocated from its private heap. But for some reason, we've lost a reference to this because there's no reference within inside this thread that holds this reference, but it's been shared. In that case, if we just garbage collect without stopping the entire program, then we will see that no one contains a reference to this part of the heap, right? And then we would actually deallocate this, but this, another thread holds a reference to this. This is the idea of like the shared memory model, or you can say the, I don't know, the concurrency model for it. I'm going to show you a quick example of what I mean by it by just looking at the threading demo. Right? You can see here that this is the lock with demo with no routine. It's still running inside a NoC thread. It has the mutex and the box integer. It starts these 2 asynchronous tasks, and you can see that the mutex is still referenced from these asynchronous tasks. Remember that all objects are allocated from its own private heap. So this one has a private heap, this one has a private heap, and this one has a private heap. Initially, we allocate from virtual thread. We would just say that this is virtual thread 1. Virtual thread 1's private heap, right? Virtual threads 1's private heap. So we have 3 virtual threads running, 3 NoC threads running, right? vthread and vthread. Vthread 2. Initially, this allocates the mutex, and remember allocation is just done on its private heap, and it creates this boxed integer. You can see in the code that this is being shared with this no routine, right? And the way it's being shared is how closures mechanisms work. Remember, no routines are just closures. So this one is just actually just linking to the activation frame from another NoC thread. So that's the way that it's really easy to share data once you have closures, because you can just reference an activation frame from an entirely different virtual thread. So here we have shared data. Like we have a reference to that mutex. And also the same thing is happening in this virtual thread right here. We have a reference to that mutex. Now let's say, for whatever reason, that we did not await for this. We just did this, right? We did not await. In this case, we return from the function, and let's say that once we return from a function, our garbage collection is triggered. We no longer have a reference to this activation frame because the activation frame is the previous. We've returned from that function, right? We just say we have main, and then we did lock with demo, lock demo, we call this function, and then we return from this function, and then GC happened on main. If GC happened, then that means because we no longer have this in our activation frame, it's no longer the current activation frame, mutex and boxed int mutex would actually not be marked if we only marked our own private heap, because no reference in this thread actually has a reference to mutex and boxed int, but it still contains a reference from the other virtual threads. We don't want to accidentally mark this as free because it will corrupt everything else. In order to stop that happening, when garbage collection is triggered, we have to stop all threads running, right? Concurrent garbage collection. And the idea is, how do you improve garbage collection by having some parts run, having other no routines run while something is halted? Now in NoC, we don't support concurrent garbage collection, right? When garbage collection starts, every single thread has to stop, because we need to now be in a known state where no one is changing the object graph. Like you don't want to be doing garbage collection and someone is allocating a new object, because you're going to miss it as you're iterating across the thread stack. You need to be in a known position where it's considered safe, like the object graph can no longer change. And the way that's done is by waiting for all threads to stop. For all threads to stop. And then we do marking and sweeping for every single thread in the entire program. let's look at what GC does. When garbage collection is called, garbage collect. When garbage collection is called, right, we're just going to ignore guard pages. We set a flag saying this thread is now garbage collecting, because each thread can start the garbage collection if it's low on memory. We then wait, we then send a request flag for each worker to say, hey, I'm going to request for you to pause. Like, you can no longer execute instructions. And we're going to wait for every worker to actually be paused. Now, if you look at the no CVM, right, check GC signal. Right? Every time we iterate over the instruction, at some point we always check if this flag has been set to true. Like, is there a GC request that's happening, right? If it is, then we actually pause the worker for the GC. What we do is we just take this conditional lock and we put ourselves to sleep. We let another thread actually start the garbage collection. And this thread is just waiting, it's just spinning until all workers are actually stopped. You can see that here, when we stop, if I look back here, we stop at a known safe point. Why do we have to stop at a known safe point? Imagine that a thread is doing this. New person, right? This is going to be broken down into two opcodes, new and then the store. So we're going to first allocate it and then we're going to store it, right? If we did not stop at a safe GC point, let's just say we stopped after allocation, there is now no longer any root that is holding this allocation that we have, right? The person object's been allocated, but it's not referenced anywhere in the local storage because this store function, this store opcode has not happened. This is a problem because when we actually go to mark the entire heap and mark the entire thread, we're not going to see X because X hasn't been created. The store function hasn't happened. But we are going to see there's some object allocated in the heap that has no marked bit associated with it. At this point, we're actually going to deallocate this. So we can only stop at a known safe point. And you can see the safe points that are here. And there should be more safe points. But these are the points where we know that we can't be in this position where we've allocated something, but we haven't given a root reference to it. So we have to start at a known safe point. Once all threads are stopped at a known safe point, we can then just do garbage collection, as we've done. For every worker, we're going to look at every thread, and then we're going to mark every thread. And then again, we're going to sweep for every worker, for every thread, we're going to sweep it. And that's how it's done within that. For that. The reason why we need it is because, again, we have a shared memory model, right? Each thread cannot safely just garbage collect the objects it allocates because it can have a reference by another thread. So we have to stop all threads, stop everything from running, and then do mark sweep for every single thread. Because this object, and we can see here, right here, actually threading demo, because you can see that this mutex is still, this thread is still referencing the mutex. When we actually trace it, we're going to mark this object. We're going to set the mark bit flag, but the actual object is actually referenced in virtual thread one's heap. So when we sweep it, it's going to be marked. So we're not going to deallocate it. This is the way we actually have shared memory between them. Shared memory becomes quite expensive because the mechanism that it works is with closures. So really what we actually have a reference to is when this is locked mutex, we actually have a reference to the static links activation frame. And it can become quite expensive to trace up all the references. But regardless, it actually creates at least a garbage collector that works in consideration with multiple virtual threads happening. And that's everything really that there's many other things maybe in the garbage collector that I can explain, but that's everything that there is in garbage collection that's been implemented in that one.
Zoom in here. I just quickly spoke about shared memory models. Right? And OC is a shared memory model. Everything can actually reference the same memory that other threads are utilizing. This affects us slightly because that means we can't really utilize private heaps properly, which means we also have to stop garbage collection for all threads. But this is not the only memory model that exists in languages. I mean, if you look at Erlang or Go, you notice that they always share. You can share data, even though Go actually does support shared memory model. I think in Erlang is way more strict. You have to share data between threads with a message box. Basically, it's a queue or an array that's actually is part of the array where you copy data into. So you can actually not reference data from another thread. You have to pass it through like a message box, which copies the entire data. And that way you have a memory model that is thread safe. Why is it thread safe? Because literally you do not share the memory, you copy the memory. So the concurrency model here in Erlang is based off message boxes, and you actually copy data into it. But because you can't copy, it's incredibly expensive to copy things, depending on the object, it does support actually sharing data. So Erlang still has private heaps, and they work really, really well. And because it's shared memory, I mean, it's private memory, purely private, meaning that you can't actually reference any memory from another thread without copying it. You can do independent garbage collection without halting the entire program, because by definition, you're not sharing memory, right? And Go has the same thing as well, that the Erlang supports with channels. Its preferred way of actually sharing data is through channels. And the channels is basically the same mechanism that Erlang has. It's just a message box, and then you just you communicate by sharing messages. And depending on whether those messages are copied or not, I don't know if the message is actually copied or not, but it uses this way to communicate between threads rather than the way I showed you in the demo, where you just take a reference to some shared data. This kind of memory model should improve the concurrency bugs that you see in Erlang. You're never going to have any concurrency bugs, right? The fundamental reason why is you can't share data, because when you do share data, it's copied. So you actually don't have, no two threads have the same reference, it just has a copied reference. There are mechanisms to allow you to actually share data in the normal way, because it's going to be incredibly expensive for you to copy things. But that's depending on your memory model, you can actually change your entire concurrency model. But obviously NoC has a shared memory model, just like Go has. But if you want to change your memory model or be in a more thread safe kind of environment, you can use these mechanisms of channels and actor models. They're basically the same things, actors, channels, Erlang message boxes, they're basically the same thing. Instead of actually directly referencing shared memory, you actually just copy data into some data structure that the language provides, and then you're copying into some message box, and then you're reading from this message box. And your application should be thread safe, theoretically, because you're not sharing memory, quite literally. Obviously, you can't be, you can only be, if you're not sharing any memory, you're thread safe by definition. So that's the thing that I wanted to conclude. And now I'm just going to talk about improving the garbage collectors implementation. One thing that you can improve, the one thing that I might improve at some point, there is only one thread marking and there is only one thread sweeping. However, you can just concurrently do this. There's no reason why this can't actually be concurrently done. You know, you can just concurrently mark every thread in the thread list. You know, you can just do that you can just start a worker pool and then just start a thread pool and then have each thread actually run and mark a thread stack itself to improve the speed of marking. And then you can do the same thing for sweeping. There is no reason why you have to hold. There is no reason why one thread has to do this entire thing for every single thread in the entire application. But I haven't implemented that, and you can do that. But the one thing that is obviously, there's so many areas that you can go into in garbage collection. You can then now start to look at concurrent garbage collection. There's many ways that you can do concurrent garbage collection. I just explained one of those ways, but the other way is, how do you allow the application to continue running? How do you have some threads continue running while collecting data? Right? And how do you have other threads continue running while running data? And of course, it's the other thing that I spoke about is using thread pools to actually concurrently mark and sweep. And then even in the allocation themselves, there's so much literature on different ways that we can improve the throughput of our allocation. We've just looked at the free list, but there's so many ways. There is where there's a tree structure that we can use. Instead of a free list, we use a tree. There's segregated lists of different sizes, right? And even to reduce the amount of heap data that we traverse, there is something called generational garbage collection. Each one is designed to actually improve the speed of garbage collection or improve the speed of allocation. There's so much that you can do and study in garbage collection. Let me see if there's one thing I forgot to do. And the reason why garbage collection is expensive, as I hope you can see right now, is we have to wait for everything to stop running. So at some point, in order for us to be safe in our garbage collection, we have to stop every virtual thread running. We have to halt the entire program. When we halt the entire program, we have to scan over all the routes of every single thread. This can be really, really expensive. And this is why you see when there's a lot of GC pressure in an application, the latency spikes. Because again, you have to stop everything from running, and the garbage collection, depending on how big the object graph is, it could be gigabytes big in a real application, you can see actually latency spikes because the entire program
halts until garbage collection finishes. You can read some articles from Discord where they had this problem, where there was a huge object graph, gigabytes and gigabytes allocated, and it would cause GC pressure a lot, and the threads would have to all suspend, and then the user would get really high latency, because whilst the thread is suspended, obviously nothing can run. So their screen was just frozen, and they would just receive nothing. I think it's either in Roblox or it was in Discord. And you can look at that. But that's the mechanism why garbage collection is so expensive with the standard algorithms. Everything with concurrent garbage collection on private heaps, they're just designed to improve the throughput. Of course, if you wanted very fast latency, then you can just get rid of the garbage collector entirely and then just allocate memory and free memory yourselves. And in constrained environments, like for games example, where they need to hit a certain refresh rate, then they might not be able to have the penalty of a language that has garbage collection, because if you're trying to render something and garbage collection is happening, you're probably going to halt your entire rendering pipeline, because that's running in a thread, and you're going to get, the screen's not going to refresh while you're garbage collecting. So it might be really expensive. In the references, I put a really cool talk in GDC by Naughty Dog, the creators of Last of Us and those amazing games, and they have a great presentation on how they've actually managed to make their engine concurrent. And in that concurrency model, they have something that they basically presents private heaps. It's really simple the way they describe it, and the simplicity is something that I'm fascinated in. In server stations, it's a bit different because you have so many cores, right? In a PlayStation, they had 6 cores when they did it, so they get away with a lot of things because of the environment that they're on. But in actual server grade hardware, you have so many cores, so the actual problem space is different because the hardware that you're utilizing is different. But they've done a system that maximizes the amount of hardware that they can utilize. It's super interesting. I'll also link another talk in the references by Bungie, which is the creators of Halo, and how they actually have different priorities for different packets that arrive to actually implement their multiplayer server functionality. Like if someone drops a grenade, this is just me talking rambling, but if someone drops a grenade and that grenade is on the other side of the map, that packet is not going to be delivered. It's going to have a different priority. So they have all these priority mechanisms, but probably inside their engine, they have a really sophisticated priority mechanism that allows different threads to have different priority levels of execution. But I'll link all of these things into it. But this is the tour of the language done, and we are at the end of it. I'll now finish with closing remarks. This has been really fun to speak about. I'm super happy with the project, although it's not finished. I'm now going to conclude with closing remarks, if my pen works. But before concluding, I forgot to actually show how the heap is actually initialized. We have the NoC thread object, which has a reference to its own private heap right here. When we actually schedule that NoC thread for the first time, we initialize the heap. We just ask the OS, hey, do exactly the same thing, allocate the free list, and then you return a reference to that heap. Once that heap is referenced, it's called a local heap. Then we just assign it to the thread exactly, and that's how the heap is actually initialized. So now I'm just going to conclude with closing remarks. Okay guys, these are the closing remarks of the entire video. I hope you enjoyed it and I hope it was really useful. You can have a look at the compiler.pdf. It's in the source code. The source code is, of course, going to be linked in the description, and it includes this PDF, which is a complete documentation of the NoC compiler internals. Things that we did not get to study in the video are referenced here. And of course, this book was finished writing in January 27th. You can have a look at the table of contents along with some of the disclaimers for this book and what this book does not cover, but basically it covers everything that we spoke in the video and some more things that I did not have a chance to actually explain. At the end of the book is the future work that I might intend to do as part of this project, but I don't have the time to work for it anytime soon. So if I do have the time to work on it, I'll do all of this stuff that I intend to do. By no means is NoC finished by any means. I decided to release it even in this dodgy state of code because I'm not going to be working on it anytime soon, and I wanted to actually release the source code as well as this video because I do think it's of value to understand how things work. And also in the references you can see all the literature that I read to understand how to build this compiler. There's many things that I read, and they're all listed right here. Yeah, they're all listed right here. I'm just trying to see if I got one more thing. Yeah, they're all listed right here. And please, yeah, and if this video has been good, then please do let me know. If it reaches an audience, then I would love to hear some feedback for it. Thank you so much for watching.